Okay, so we are back here at the bench camera, and we're just going to take a look at some couple FETs here. And now, unfortunately, most of the FETs that I use are all surface mount, so I don't have a lot of through-hole FETs unless they're big power FETs. So we'll look on the computer for some, but I just want to show you some of these packages so you can kind of take a look at them. So first thing here is let's take a look at this one under the zoomed camera. So this is a TO92 package, and this is one package that you'll find FETs in. Now this is actually a transistor. This is a 3906 transistor, but this is a popular package for FETs, and I wanted to show you that. So this is the TO92 package, all right? Now, here I have a couple surface mount FETs. And again, because they can be so small, because of their low on resistance, you're going to find a lot of these in surface mount now. Now this is a FDC 606. This is a P-channel FET, and it's in this package right here, which is this is a I believe it's called a SOT23 or an SOT6. In any event, it has 6 leads. So what's going on with this? Well, because it can carry so much current, it has more than one lead that's the same. In this case, it's got drain, 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 gate, and source. So more than one pin has the same function. They're all electrically tied internally to the same thing. And that way you can get more current flow, all right, instead of just going through a couple little pins, all right? And here's another field effect transistor. This one is a FDV 305, and this is an N-channel FET like we were looking at. And again, very small. And this is an SOT23, it's called. And again, you have to solder them on these little boards so that you can experiment with them and you can see source, drain, and gate. All right. So there's those packages, and there's just many packages when they come small and surface mount. Now I wanted to show you this. So here is, this is an N channel, this is an IRF 7030, and uh, again, I'm saying these as if they're very specific. They're not. There are tens of thousands of FETs and transistors. In fact, I think there's about 120,000 different transistors on DigiKey and about 60, 70,000 different FETs. So there are countless. So really, when you want to use these things, you have to go into the data sheets, you have to go through the search engine on DigiKey or Mouser or wherever you would like to buy your parts, put the parameters in that you're looking for the performance characteristics you're looking for, the price, and then start looking at the parts and downloading data sheets and reading. And then over time, you start to use certain parts and they become kind of your go-to part. And that happened with the 3904 and the 3906 from the transistor world. But in the FET world, it hasn't happened as much. There's no clear, your, go-to N channel and P channel FET. So I'll talk about a couple that are sort of the go-to, but just not really, not really. Anyway, so here's how some things come. So this is this package right here, and you can see right on here, bring it in if it stays in focus, is a TO220 package. And these are really big, and they can dissipate a lot of heat. All right, so that's what that looks like. And if we look at the, data sheet and the specs of it, this one's a 400 volt, 5.5 amp N-channel MOSFET. Let's look at it on the zoomed in screen. So we can see that there. All right, and you can see the part numbers right on there. All right, and then now, so this is interesting. So this thing, you haven't seen this before. This is a heat sink. And so after you solder this into your board, and typically these pins would be bent. So they would be bent at a right angle. And then there would be a hole in the board, the PCB. This would be mounted onto the board, typically soldered onto the board, and then a screw would go down into it. Now, if it's not soldered and it's just mechanically held there, there will be conductive grease, thermal grease on there, and then that'll make a good contact, and then you'll screw this down, and then the heat will dissipate into this metal tab and then into the printed circuit board so they can get rid of that heat because it's going to be dissipating a lot because this is a 5 amp FET, for example, right? Okay, so that's kind of what they look like. Today we're going to be using these guys for our experiments. All right, so just pretend that they're through hole. And they're just mounted on these little adapter boards, these little breakout adapter boards, which many companies make them. If you type in SMT or surface mount to dip adapter. You can find many companies that make these, and in the section 1 in all our resources, there's a list of actual websites that you can get these adapters, and they're very expensive, as I mentioned before. All right, so let's go ahead and we'll just put this away. And then, one thing is, excuse me, one thing is when you're messing around with this stuff, you want to put things away and put them back and keep track of them, or you just lose everything. And then, and I had one more I wanted to show you here. So if you can read that, this is an FDA 69N25, and this is a MOSFET 250 volt, and this is 69 amps, 70 amps of current this bad boy can flow. So let's take a look. I haven't even opened this up. This was for a power project one time, and I didn't need to use them, I guess. I must have used something else, or I didn't use all of them and I had more packages of them. So look at those. How awesome is that? 70 amps each, basically. So let's take that out and take a look at it. And this package is called a TO3P. And again, there's countless packages also. These companies, practically make these things up, and so you'll just find package after package. Let's look at that under the zoom camera. So there it is right there, FDA 69N25. That is pretty awesome, huh? Look at that heatsink. So, that level of FET you could use for big motor control, so you could, 70 amp, this could be for an electric, a small electric car, a motorcycle, something of that nature, and you could control it with this. All right, so very, very cool part. And, they make these things that can, tolerate 1,000 amps, if you can believe that. All right, so let's go ahead and put this away. Fun. And let's go back to the computer and let's start drawing some circuitry here, and then we'll come back and start building stuff. So you can see this little thing here. I'm not going to tell you what that is yet until we go over to the computer and start drawing some circuits. So let's draw our first circuit and let's get right back here. First, we're on the computer here. You can see we've got this 2N7000. So this is an N-channel enhancement mode MOSFET. One of the most, kind of popular go-to MOSFETs for hobbyists. And let me get up its data sheet here. And you can see it's got the TO92 package and then like an SOT23 like you saw of the other package. All right, you can see the symbol here, gate, remember it's that little L. And then we've got the 3 little flat little feet thing here, feet things, and then we've got the arrow pointing in. All right, and then these are connected together, and then we have this diode, this body diode here to remind us that there's a diode there, so you don't want to forward bias that. So you want to make sure that current flows in this direction and downward direction. Okay, so anyway, so the 2700 2N7000, and this is a good, all around get the job done, and it comes in a TO92. And let's see, let's look for its RDS on. Remember we talked about that, so let's just look for RDS. All right, and this is the static drain source on resistance. And so this is going to be at different, and again, with these data sheets, you got to bear with them because some manufacturers put information that's useful, some put that's not useful, and they put it all over the place, and you got to take your time and go through it. So this is saying at VGS equals 10 volts, ID equals 500 milliamperes, and then we're showing a number of different transistor variations. The one we're looking at is the 2N7000. And then it's saying what the typical on resistance is here. So if we're at 10 volts, then we're getting about 2 ohms of on resistance. If we're at half of that, 4.5 volts, and we have less current, then we're getting these values here. All right, and then so forth. And you just kind of read through here, and it's always partial information, and it's half right and half, missing and all that as you go through these data sheets, and it's always the same. And then of course we've got the various curves here that show, like for example, this one is the I sub D as a function of VDS, and those are like those characteristic curves that we looked at with the other drawings and so forth. Anyway, this would be a good field effect transistor for you to pick up some of. So 2N7000, get 10 of them, get 20 of them, and then you can play with these things. and they go 400 milliamperes. You can probably do 500 milliamperes fine, and they'll go to 2 amps pulsed. All right, so there's one right there. And so that's an N-channel enhancement mode. Then another one, let's see here, that I like for you that has a TO92 package is this BS170, which is very similar to the 2N7000. And again, same thing. And now you got a slightly different symbol here. Drew it a little bit different way, right? The voltage stuff is the same, but now you can see here the continuous current on this one's a little bit higher. So this one is 500 milliamps, right? And then the pulse current is a little bit less. This one's 1200 milliamps instead of the 2 amps of the one we were just looking at, right? And so anyway, so this is another good one. So you could get either one. Me personally, I would just get both so you could play with them and have extra units. Okay, and let's see, what else do we want to take a look at here? Let's take a look at, all right, and here, the transistor that we're going to use for our experiments, we have an N channel, which is this FDV 305N. This is an N-channel power trench MOSFET, and that's just a marketing word and registered trademark, and it's a certain kind of construction technique that they use to make the MOSFET. Anyway, you can see here's the labelings of things, but what I want to bring your attention to here is this. At a 2.5 volt VGS, we've got 300 milliohms only of RDS on. That's pretty good. And then at 4.5, if we increase that even more, it drops down to 220 milliohms, right? And now what we're really looking for is 0 milliohms, right? That would be ideal. But to get that, it's more money. However, if we go over to, let's see, and I want to see what else we got here. And I've just picked a few for you here. That was the one we were looking at, that big one, right? That IRF 710, we were looking at that, the 220 package one, right? And so this is another power MOSFET. But if you wanted to get a power MOSFET, what I would probably suggest is this one, the IRF 510. And this one here, it's got an RDS on of 0.54 ohms at a VGS of 10 volts, and it can handle 100 volts from VDS. This other one, this IRF 710, what's good about it is it can handle 400 volts, but it's got a much higher RDS on, but it can handle a much larger voltage. And that makes sense. If you think about it, how's it handling that large voltage? Well, it's got, the silicon is larger, the geometry is bigger, so it can handle larger fields, larger currents, and because of that, it's just going to probably have more resistance. It's going to take more work to move charge through it because it's just bulkier and bigger, and of course that's why the RDS on is different. But if you need that, then there you go. So if you're going to be playing with big motors, any of these IRF series, 510, 710, 500, 700 series, just look at them, read all the data sheets, and these will do what you need to do. All right, and let's see here. Let's look up another one. Let's actually use the tool here. So, oh yeah, I was looking, and there are 67,666 different MOSFETs here. So FDC 606, this is from Fairchild. This is one of my favorite. This FDC 600 series from Fairchild, and they have both N channel and P channel. And what I like about these are logic level gates, meaning these things can be turned on and used as a switch just with logic level VGSs, and this one is 1.8 volts. However, look at the drain to source voltage. So they can only withstand like 12 volts, right? So you can't put a lot of voltage across the drain to the source. But look at these RDS ons, 26 milliohms. That's crazy. Very cool. So, and then here's the data sheet for it. Just pop that up and open this up a little bit for you so you can see it. And there we go again and again. You can see there's drain, 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 source, gate. It doesn't have multiple drains. They're just electrically connected together in the package. That's all. So they could put it in the larger package so it could dissipate more heat as a surface mount device, and you get some more current pass going into those ports or leads on the actual device inside of the package. All right, and now look at this one right here. Look how crazy this is. 6 amps. This thing can flow 6 amps. All right. Now, one thing you're going to notice, and I don't want to get too hung up on this right now, is when you are looking at parameters for N channel and P channel, as a convention, they'll use negative numbers on the P channel devices. And so VGS is minus 4.5 because we have to use a negative voltage to turn these things on. So these negatives, it's not really flowing negative 6 amps, right? Current is positive or negative just depending on which way you want to use as your convention. So it's not like uh, sucking current out of something. It's still flowing 6 amps. It's just saying that because of the convention of how they like to make these data sheets, they just say it's minus 6 amps. That's all. So don't get hung up on that. Don't get all crazy and think there's something weird going on. So we're going to use this one and the other one, where to go, this one here, and we're going to use this in our circuits that we're going to hook things up. So we're going to ignore kind of what they look like in their package, and we're going to use them in the abstract. All right, so let's start off. Why don't we start off with the N channel, and let's draw a circuit with that. So let's go over here, okay, and let's get on our drawing thing here. All right, and let's go ahead and, so N channel, let's pick orange. Okay, so first we got to draw our field effect transistor. Okay, all right, and we'll draw our three little guys here, like so. And I'm going to be honest with you. It's like I've been drawing transistors so long. You get to the point where, let me show you how I really draw one of these transistors. That's it. I'm done. That's it. I don't even get into all this other stuff, but you'll just, after a while, you'll start to get very, very lazy, and you just don't care anymore. All right, there's that, but we want to draw these correct since we're learning it. All right, and then we want our arrow in here. Okay, so that is my rendition. All right, and that's the gate, and that's the drain, and that's the source. All right. Okay, so, and we can put little circles here. All right, and let's say what this again is. This is an N channel. All right, and then we'll say E mode for enhancement mode. Just means that a positive voltage is going to turn it on and it's already off. It just means it's off and we turn it on. Enhancement, if it's depletion mode, it's already on and we turn it off. N channel, E mode MOSFET. Okay, and all I want to do is use this thing as a switch. I just want to use this thing as a switch. Okay, so what we're going to do in this is when you have an N channel device, we're going to use it as a switch, and we're going to basically connect the source directly to ground, like that. All right, we're going to connect that to ground, and on our gate here, we're going to apply some voltage, so we'll get to that in a second. Now on the drain right here, we're going to connect our load. All right, and for now, I'm just going to represent the load like this. And then here, this is going to go up to we're just going to call this, this is not V sub D. This is going to be V sub, we're going to call this V sub CC. In our case, we're going to set this actually equal to 5 volts. Okay, we're going to set this equal to 5 volts. All right, so now this right here at this node, right there at that node, that would be V sub D. And then here at this node right here, this would be V sub S, which is equivalent to ground. And then here at this node right here, this would be V sub G, but since it's relative to ground, it's V sub GS also. All right, so it's right there. Okay, so now we want to use this thing as a switch. We have to apply a positive voltage between VGS. So our goal is to get VGS greater than V threshold. All right, that's number one thing that we want to do. And then the other thing that we want to do, if you remember those graphs, we want to push this thing all the way so that VDS is equal to nearly 0. So on the graph, there's the cutoff point at one end, and then up at the other point of the graph, there's the point where VDS is almost 0. We don't want anything to drop over this MOSFET. We just want it to be absolutely 0, just like a dead short. So what we're going to do is we're going to drive VGS really, really, really hard. So we're going to drive it all the way up to the 5 volts. Okay, so what we're going to do is we're going to put a switch here, like this, momentary switch. And then we're going to take this and we're going to connect this directly up to 5 volts, like that. All right, and so when we put this 5 volts on here, this is going to turn this thing on. All right, once it's on, VDS is going to go down to 0. I sub D is going to go to its maximum amount that it'll flow. RDS will go almost to zero, right? The resistance in this junction. And then we're going to get a current flow right here, right? And we're going to get a current flow like this to ground. And that's going to be I sub D. And that's going to be basically this resistor right here, this resistance, this RDS on, will become nominal, and whatever the load resistance is will dictate what the actual current will flow. Now, one more thing. When this MOSFET is just sitting here, to turn this on, we have to put a positive voltage. VGS has to be greater than V threshold, which is a positive voltage. However, when there's nothing on the gate, it's just floating around. We don't want it to float. We want to do something with it, right? So we don't want it to float, so we want to put a voltage on it so we know it's stable. So what we're going to do is we are going to take a resistor, and we're going to put it down to ground, and we're going to call this, how about we can call this R off. And all this is going to do is create a voltage, because no current is going to flow. No current is going to flow, right? Because remember, no current flows into the gate. It's just like a capacitor. So we can make this very, very large, all right? But we don't want to make it so large that other disturbances can modulate it too much. So you want to make it stiff enough, is the word, so that if something else comes on here, it can overtake that. If noise comes on this, it'll maintain this zero, all right? And then only when we put this full 5 volts, then we're going to get 5 volts here. But then what happens is we complete the circuit in 2 ways. When we close this 5 volt, then we're going to get current flow down through this resistor. We're going to get 5 volts at this node, but then we're going to get current flow. So if we make the resistor too small, making the circuit really nice and stiff, we're going to burn a lot of current when we turn this thing on by pulling it high. So we got to balance that, right? So let's just set this for a nice number is 10K, okay? 1K to 10K is what you want to use for your pull-up and pull-down resistors. Anything higher than 10K, it's just too weak of a pull-up or pull-down. Yeah, you may even get away with 22K, maybe 47K, but I wouldn't do that. 22K is kind of my limit, and I like to stay around 1 to 10K for pull-up and pull-down resistors, which is something you probably just heard the first time, but it's when we want to put a weak signal on something to make it stable, and then we're going to put a different signal on it, a really strong signal at other times, but we want it to be stable. Okay, so let's look at our circuit. When this thing is off, when VGS is 0, and VGS is going to be 0 when the switch is not depressed. VGS is 0, it's less than the threshold voltage, the MOSFET is completely off, there's going to be no current, there's going to be no I sub D, and then therefore there's going to be no current through here, and then this load is not going to do anything, right? It's just going to stay off. Now, we press this momentary switch. The moment we do that, now we've got 5 volts. 5 volts is right here. We're actually going to get a current flow down here. What are we going to get? What are we going to get? We get V equals I times R. In this case right here, so we want to compute I. So I equals V, which is what? 5 volts over R, which is 10K. All right, get out your calculator, right? What would that be? So 5 volts divided by the 10K, right? If it was 5 volts divided by 1K, what would it be? Think about that for a second and see if you can start to do these in your head. And and the answer is 0.5 milliamps, of course, or 500 microamps, okay? All right, so not a lot of current, but if you're doing a battery-powered something, this might be a lot of current, right? So then that's going to be on, whenever the switch is closed, we're going to get that current through here and burn a little bit of current. All right, then we're going to get a massive current when this thing gets turned on, a massive current through here, which is going to be dictated primarily by the load resistance, because this on resistance here, this RDS, is very, very, very small. It's on the order of milliohms, right? 50, 200 milliohms, all right? So let's build this circuit. So all we need to do is take our load, and we're going to take our load with our N channel, and we're going to take our load through our MOSFET from drain to source to ground, and then on the gate we're going to take a 10K to ground, and then we're going to put a momentary switch, and then we're going to turn this thing on, and we're going to turn this thing off, right? So let's go over to our bench camera and let's build this, okay? Okay, so let's do this. All right, so the first thing we need is our transistor, and we decided we're going to use the N channel first, so we're going to use this FDV305 NFET, N channel FET. So let me zoom in as usual here a little bit so you can see things. All right, and then I've got my hookup wires. I got my long ones, got my short ones. I got a bunch of resistors. I got a couple switches here. I've got my meters over here. I got everything that I need. Okay, so first thing is let's go ahead and let's place this into the board. All right, place this someplace here. So we'll put it right here. Okay, and then we said we're going to take the source is going to end up going to ground. And remember, since this is an N channel, it's the source of what? Electrons, and that's why it goes to ground. That's where our electrons are coming from, the negative. So we're going to hook this to ground. And let me make sure power's off here. Yep. All right, so the power's off, and then I'm going to show you something else I built, but right now we're going to just hook it up. So now we've got our load, and here's our load right here, and it's a coil of wire, right? It's a coil of wire. So let me show that to you on the zoomed camera. So it's a coil of wire. Can you see that? There you go. It's a coil of wire, and I made that coil of wire, and it's like this coil of wire. And this is made out of nichrome wire. All right, nichrome. And I don't know if you've ever heard of that, nickel chromium wire. And it's a type of wire that heats up. And it's the basis of many, many heating elements, all right, is nichrome. And so what we have here is you can get these spools of this wire. And this one is from this company called Wiretron. And I bought probably, I don't know, 50 different alloys I use for different kinds of heating element construction. But anyway, this is copper nickel 294, right? And so anyway, nichrome is a nickel chromium wire. And there's countless alloys that you can use for heating things. So anyway, this is actually nichrome, the big, thicker one here that I made. It's just too big, I can't heat it up enough with the current from our power supply. But this right here, this copper nickel 294, I can heat up enough, and we can actually get this to turn red if we can put enough current through it. Now, what I was going to do was just do another experiment and then do a motor. Power a motor, right? But we kind of did that in the last one twice, so I thought let's do something that requires even more current. So this is going to take at least an amp to turn this red hot, an amp to turn it red hot. If you remember the previous thing, I think we did 200 milliamps, 300 milliamps. Now we're going to go for an amp with the MOSFET instead of the transistor. So let's see if our MOSFET can get us this power level that we want, which is an amp through here. Now, this particular one I think will flow a couple amps. We'd have to look back at the data sheet. I think it's 2.5 or 3 amps, and then the other P channel can do I think 5 or 6 amps. All right, so let's keep doing our circuit. So what do we need? We need to go from the positive, so V sub CC, which is going to be up here. All right, and that's going to be, we're going to just set it at 5 volts. All right, now we've gone through our load. All right, and now we're connecting the other end of the load to the drain. All right, and now this is called a low side configuration, low side. And the reason why it's low side is the load is up here, up here high, then the switch is down here low. So it's low side. The switch is switching down here low. And so you'll typically use N channel FETs in low side, and then P channel FETs up at high side. The switch will be up high, and then the load will be down low. All right, and that's where that comes from. Okay, that's all we need there. And then on our gate, we need to take our gate, and we are going to pull that down low through a 10K. So what's 10K? Brown, black, orange. Brown, black, orange. There it is right there, brown, black, orange. Okay, and we're going to put that right here to the gate. Okay, and let's zoom in a little bit more, a little bit more, a little bit more. All right, so there we go. So you can see that's into the gate. Okay, source drain gate. Okay, and then now let's take a switch. And what do you think here? White switch, blue switch? Let's do a blue switch. So here's a blue switch. And we want to take this, and this is going to give us our plus 5 volts. So we're going to drive VGS all the way up to 5 volts, right? So we just need a wire here. Let's find one that'll reach. That's not too long and gangly. Yeah, this one will. All right, so kind of bend that up, get that going here. And then, you know, you got to pull these things up and see what's what. You got to wear your glasses or your magnifying lenses or work under magnification. Like some people, what they do is they just put one of those big magnifying lenses and they work through that, right? So either way, just, you know, don't strain your eyes. If you're going to start doing electronics in 20 years, you'll be blind. So don't push it. Now the other end of this is going to go also to the gate. All right, and again, let me get a piece of wire here. All right, this one's a little bit long, but it's just going to have to do. A little bit long. We're going to put this right to the gate. Okay. Okay. All right. Now, when I turn this power on of the power supply, and we've got it set for 5 volts, we should see nothing. Nothing should be on because we've got this thing pulled low. So VGS is 0 right now. Okay, so I'm going to turn it on. All right. And everything's good. 0 volts like we expect. Let's check it. Let's get out a meter, right? And I know we're going to do a lot of things that are obvious and simple, but you know, that's why 747 pilots have a checklist. They go through the checklist and then they know what is going on, and that way that there's no human error ideally. Okay, so let's put this into voltage mode. All right, so let's check our voltage here. Okay, so we're looking at the voltage on the gate, which is right here at this resistor, and sure enough, the voltage is 0. All right, so the voltage is 0 right now. What's the voltage from the drain to the source? Drain to the source, what's the voltage? All right, you got your answer? So let's take a look. So drain to source, these two guys right here, all right, on the left here, and I'm going to get in here so you can see it. I'm going to put a ground at source since it's already a ground. I'm going to go to drain. It's 5 volts. Right? It's 5 volts, and that's exactly what it should be. There's no current flowing through here. When this thing is on, that drain to source will go to 0, right? Because this MOSFET is going to have 0 resistance when this thing is fully on, right? It's going to be flowing a ton of current, okay? All right, so everything's good. So now what we're going to do is I'm going to actually turn this thing on, and when I do, this coil is going to get red hot. Now, just a little bit of mechanical stuff here. So what I did is I coiled this, I suspended it up on these 2 posts. We got this plastic, and then the 2 posts are going into here. This is going to get a bit hot. Probably, I don't know, 150, 200 degrees maybe. It should be okay. It's not going to melt this plastic, but I'm not going to hold it on here for hours, right? Because it will sooner or later melt the plastic. All right, let's zoom in. Here we go. Zoom in, zoom in, zoom in. All right, and there we go. And now I'm going to turn off some light here. All right, and hopefully you can see this. And here we go. We're going to turn this on, and let's see if you can see it. And there we go. Can you see it turning red? How cool is that? And the power supply is showing 1 amp right now is going through it. And then I'll let it off. Then I'll turn it back on, and I'll turn it back off. All right, and I already burnt my finger during when I was, checking this and testing this. I touched it there accidentally. All right, let's turn the light back on. Let's put an ammeter in here so we can measure the current and make sure we're getting what we think we're getting. So we'll take this meter, we'll put it into amp mode. We'll get one of our little connectors. All right, and then why don't we just we'll put it right here in this leg. Okay. So go right here. Oops, careful. Don't want to damage that coil. That wasn't easy to wrap. Careful, careful. Okay, trying to keep this all on the camera. All right, then we'll put our amp meter in there, and then we'll connect our leads here. All right, that's number 1. And while we're at it, let's also, why don't we measure the voltage from the drain to the source? Now, since the source is at ground, really, if we just measure drain to ground, that's the same as drain to source. So let's watch that go to 0. So let's get another meter. So I'm going to get another meter out here. All right, got another meter. And let's get another connector. So here we go here. And let's get this voltage. So here's the drain. And let's get a long wire. Here we go. So here's the drain right here. And there's the drain there. And remember, we don't have to take the drain right from the IC because there's a wire there. So electrically, this is all connected the same, yeah? All right, so now we got that. And now let's get to a ground. So here's a ground. Okay. And, okay, I just bent this up really bad. Now I'm mad at it. So guess what? It's done. Move it away. All right, let's try this. Ah, that went in nice. You know what? If things don't want to work with you, don't work with them. All right, now we're going to go in there. Let's get our voltmeter set up here. Put it on voltage. And I'll bring this into view in 1 second. I'm going to ground one end, put positive in the other end here. Okay, all right, now we're going to Bring all these things in close, and we're going to see what happens. Okay, we're going to zoom this camera back out here 1 second. Let me get these cables so they sit still. All right, move this up. Okay, so the meter on the left is current, the meter on the right is voltage, and as you would expect, right now there's no current, and the voltage across from drain to source is 5. When we turn this thing on, this should go to 0, and this should go to the maximum value of about an amp. Ready? And is the power on in the power supply? Yes, it is. And here we go. There's 1 amp and 240 millivolts. And the coil's on. Let me turn off the light. There you go. Let me move this so you can see it. There we go. All right. And it's not a special effect. Watch this. So I will take this is a piece of napkin, all right, and I'm going to take a little teeny tiny bit of alcohol. This is alcohol right here for cleaning, for soldering. We're just going to put a little bit of alcohol in here. If we can get it, there we go, a little bit of alcohol. All right. And now we're going to turn this on, and it should flame this up a little bit. So there we go. Let's watch it. There it goes. And I'm going to touch it. And you can see how that kind of enhances it. You can see it. And it just started on fire, but it burnt the alcohol. Isn't that cool? All right, now let me show you something. When I have this on, right now it's pulling 1.25 amps, right? Now if we blow on it, well, we can't really do it, but what we could do is if we cool this down, we can make the system work harder, all right? So anyway, that was a big load, 1 amp, 1.25 amps there. We powered it through this this MOSFET. It's totally cold, like it never even happened. Didn't even phase it. All right. So let's go ahead and do this again, but let's do it with the P channel now. All right, and just do a P channel. So let's go back to the board and let's set up the P channel and see how that works. Okay. So we're going to do a P channel now. So we're going to do the P channel version of this. So we'll just let's just put a line here. All right, and then we're going to say P channel MOSFET enhancement mode, E mode. All right, and so everything is almost the same. So let's draw this first. All right, so the switch is going to be up high and the load is going to be down low. So let's draw the switch first. All right, so the MOSFET first. All right, so again, we're going to draw it like this. And now what we're going to do is we're going to kind of flip this thing around a little bit because the source is going to be up at the positive side. So we're going to go like this. We're going to draw our little guys right here. All right. Then these two are going to go together. These two are going to go together, and yeah, this is really horrible because I just never draw these like this. Okay, there we go. That's a little bit better. And then we're gonna, now the arrow goes out. So the arrow goes out when you're doing the P channel. Okay. Okay, so this is the source, this is the drain, this is the gate, and we've got a P channel here, right? And then this attempt at what it should look like. All right. And like I said, and that's why I do this when I draw these things. All right, so, okay, so this is going to be a high side switch, high side switch. So the source in this case is what? The source in this case is the power line. So this is going to go right to V sub CC, which again is going to be 5 volts. All right, now we're going to put the load down here. We already know what the load is going to be. It's going to be this coil, so let's stop being coy. So here's the coil, and then this is going to go to ground, all right? And then this is like nichrome or some other heating alloy, all right? And so there's a source, there's a drain, there's the gate, and so this is good. And now, okay, so now to turn on a P channel, we want to create, put a negative or low voltage on the gate. All right, so we will put a negative or low voltage on the gate, and that's going to create the channel, and that's going to allow the current to flow. Okay, so to do that, we are going to ground this. Okay, so in this case, we're going to go and we're going to put our switch here. There's our momentary switch, and we're going to go to ground to turn this thing on. Okay, so this is the on switch. When it's not on, we need to keep it off. Remember, we did the pull down, we need to do a pull up. So we need to pull it up high to keep this thing off. All right, so again, we're going to put a resistor, and we're going to put that up to V sub CC again, up to the top rail, which is going to be 5 volts. And again, we're going to just make that 10K. All right, so when the switch is not on, this will be pulled up high. So now we're not going to have a low voltage or negative voltage on the gate. We're going to have a positive voltage. All right, we're going to have a positive voltage on the gate. And where that voltage comes from, if you look at the source, so basically the gate minus the gate voltage relative to the source voltage. If G minus S, if VG minus S is a negative number, that's where the negative comes from. So say this is at 5 volts. So if we take V sub G and we put it at 4 volts, right, then we're going to have a negative differential here. And we put it at 3 volts, and then we have negative 2. And we put it at 2 volts, we have a negative 3, and so on and so forth. So relative to this convention, this is a negative voltage. So when you put it at 0, it's kind of like a negative 5 volts, right? And that's why when we go look at the data sheet, it'll have negatives for VGSs, okay? So when we put it at ground, this is going to turn this thing completely on. When we put it at 5 volts, by pulling it up high, when we don't have our finger on the button, it's going to keep it completely off. All right. When we turn it on, what are we going to do? We're going to get this current, right? We're going to get this current right here, all right? And that current is, what do we call that? We call that I sub D, and that's going to be, full on. And this voltage here, right? The voltage here, which is V, DS or VSD, right? Typically we'll call it VDS, not VSD. That we want to be, it'll be, nearly 0 volts when this thing is full on. When it's off, what's it going to be? It's going to be the 5 volts here, right? Okay, so this circuit is what we're building. So let's take a quick look at that. Memorize it. So basically we're going to use the P channel. Source is going to go to power, drain is going to go through our load to ground, then gate is going to be pulled up, and then we're going to put a switch on it, and then we're going to turn this thing on. We should get the exact same behavior as the other one, and maybe we'll get a little bit more current because this one will flow a little bit better. Okay, so let's see what happens. Let's go over and do it. Okay, so we're back here on the bench. So I've kind of taken everything apart. I've taken our N channel FET and I've moved it away and put it over here. And I've got our P channel and I've got it inserted here so that the source is up towards the positive rail here because the source is going to go to positive. This, remember, the P channel is a P channel because we're going to create a P channel and the majority charge carriers are going to be holes in that case, right? And so that means we're talking about positive. So source goes to whatever the majority charge carrier is, which in this case would be the holes or the conventional current. And it's a high side switch. So that means it goes to the high side, and then we go from source to drain through our load to ground. All right, and then what we're going to do is we're going to actually put our amp meter in here so that we can measure the current. So let's do that. All right, so here we go. So let's hook the source up to a plus, and we're going to again put +5 through here. All right, then we're going to go from our drain through our load. All right, and remember there's 4 drains on here. They're all electrically connected, so we just need one of them. If it was a circuit board, we would connect all of them up in the circuit board so we'd get all that nice current going through all those different leads. Might as well use them on the body of the IC. All right, and we've got our amp meter, and we need to go to ground now. So this drain goes through the load down to ground. All right, and the switch is up high near the high side. All right, can't say that too many times. And on the N channel, it was low side. The switch is by ground. All right, so we've got our source drain circuit of our P channel MOSFET good to go. We're using that FDC 606. You can look at the data sheet again if you like. Okay, now let's get our switch going here. So to keep this thing off, we want to pull the we want to pull the gate. We want to pull the gate high. All right, so we want to pull the gate high. So we need a high voltage on the gate. So what we're going to do is I'm going to put this resistor right here, this 10K, and I'm going to pull this thing up. All right, so that'll keep it off. All right, that'll keep it off. And so now if I were to turn this on, this thing will be off. So let's just do that real quick, just to show you this kind of variation of this. All right, Let me kind of get everything on here so you can see it. All right, let me stop that from shaking. All right, let me turn that off, turn off the light. We're going to turn the power supply on. So the power supply is now on and nothing is happening here. You can see nothing is going on. All right, so let's keep going here. We're going to turn the light back on. All right, let's get back to our circuit here. All right, so what do we got to do? We have to finish our circuit. So now to turn this thing on, we need to put a negative voltage relative to the source here. Relative to the source, we need to put a negative voltage. So we're going to ground the gate. And we're going to do that with this momentary switch. So one end of the momentary switch is going to go to ground. And the other end of the momentary switch is going to go to... So here is that wire that was giving us trouble, this crazy wire. So let's just straighten this out and see if we can bring this back to life. Bring this wire back to life right now. So I'm going to straighten this out. All right. Not happy with this wire at all. I'm going to throw it away if it gives me one more problem. All right. So, and it's too short, just too short. All right. And we need to get into here, and I think we can. So here is the gate. So we got our wire there. We got to our switch. Our momentary switch is going to turn, which is going to turn the circuit on. Okay. There we go. We got our amp meter good. All right. So everything is good to go. Everyone is happy. All right. And okay, let's go ahead and let's put our meter here so we can see it. Let's zoom back out. Not too much. Okay. Zoom back out. You can see the coil. Let's turn off this light. We got our power is still on, and I'm going to press the button. This thing should turn on, and we're going to expect some current out of here. Okay, here we go. And there we go. We got 1 amp and some change, 1.1, and you can see the coil is red, hopefully, and turn it off. All right. Now, remember, between the drain and the source, we can kind of play around here, and if we can get it, so between the drain and the source, we can actually put an LED here. And let me show you something. So between the drain and the source, it's real high because that's going the whole 5 volts. So when this thing is off, we got this whole 5 volts going. Now, but because we put a diode over here, we're forcing the transistor voltage across the drain to the source to be pinched or to be latched to this diode. So see, that's another effect a diode has. Remember, the diode wants to be at like 2 point something volts, this green one, right? And because it wants to do that, it's forcing the transistor to flow some current. That's why we're seeing 140 milliamps here. So if I now turn this on, now it'll go all the way on and it'll work as it should, and you can see it getting red again. All right, but that diode across that junction, the diode is going to force it to stay at that voltage of the diode voltage. So that's another use that diodes can be used for, is they can latch voltages. They can force a voltage to stay around something as protection or just as something that you want to do, right, in your circuit design. So that's getting a little bit hot, all right? And so, so that's that. Okay, so we've seen the N channel and the P channel. We've seen that we can flow an amp of current through these things or more. We can see how to turn them on, turn them off. We got P channel. P channel is used in high side switching. N channel for low side switching. We could have used it as an amplifier, but it's complicated to get that all working, so we're not going to see how to do that. We don't really need to make amplifiers, and if we do, we're going to use these things called op amps. All right, so that's about it. So I think we're done with the MOSFETs, and so I will meet you in the next lecture, and we're going to take a little bit of a break, take a breather, and we're going to look at just some easy equipment and some of the equipment that we played with here before, and we'll go from there. Okay? All right. Bye-bye. All right, welcome back, and we are through the first very hard part of the course, kind of the introduction to most of the electronic components, and I know it's been tough, especially diodes and transistors and FETs. We did a lot of experiments and a lot of theory leading up to this point. So this lecture is going to be probably the most hands-on so far. We're going to look at a bunch of different test equipment and fabrication techniques, and even things that we aren't going to use. We aren't going to be soldering that much in this course. We're not going to really solder anything, I don't think, unless I decide to do that later on. But I still want you to at least have been, introduced to a soldering iron so you can kind of see what's going on if you've never touched one before, and some other things to be able to construct circuits. So what we're going to do is we're going to look at some electronic equipment, test equipment that we've seen much of it before, but we're just going to do it again in case you skipped over something. And then we're going to look at ways to build things. And then we're actually going to build a couple circuits with our hands, not on the solderless breadboard. Well, in addition to the solderless breadboard, we're going to do that so you can see how you do this. And then I'm just going to show you some different things so you've seen them once and kind of see what they do. So it's going to be a lot of fun, and we're just going to see what happens, all right? And this is probably going to be one of the most dangerous lectures, so hopefully I don't cut any fingers off or anything like that. We're going to be doing some cutting and playing with the soldering iron, so let's see what happens. So anyway, looking up here on your screen, so again, the notes are just, I just use them, the notes from my book, just as a loose guideline to kind of have something to anchor to as we talk, and we usually go off script all the time, but this is just kind of a nice way for you to see something on the screen as I'm kind of talking, and then we go over to the bench or different things. All right, so we've already talked about power supplies, and you know, a power supply is a device that sources power to your circuit. And you could use batteries, you could use a wall wart, something like that. But when you're doing electronics, we want to be able to have control over this. So typically we want to have an adjustable power supply. All right, and right here, for example, this is a BK Precision. This is a company that makes you know, good power supplies, good high-end power supplies. But again, these days you can get a brand from China that's just as good as this, as long as it tests well, as long as it has the same uh, uh, manufacturing quality and so forth, and you know, and Google it, check it out. There's lots of reviews online. So if you're considering buying something and it's too expensive, and you can find something that's kind of a Chinese lower cost version, you know, go ahead and take a look and see if it'll work for you. So when we are using these bench power supplies, what we ideally want is multiple channels. So if we just have one channel, that means we can just supply one voltage to our circuit. Two channels, two voltages. Three channels, three voltages. So typically, when you start really building into things, you're gonna need one channel, obviously. Two channels is gonna get you pretty far. You might have, say, a 5-volt system that also requires 3.3 volts, right? There's your two-channel system. But you also might have a 3-channel system where maybe you want to have 12 volts to control motors, and maybe you have 5 volts for some interface, and then maybe you have 3.3 volts for some of your low power digital. So anyway, it's really, really good to have a good benchtop power supply. And again, there's lots of manufacturers, so there's really there's so many different ways you can go here. So, you know, real quick, I'm going to go onto Amazon and kind of do a quick search and just let you see in real time just, you know, some of the power supplies. But I want you to realize that, again, these days, you know, you have to look at reviews, you have to see what people think, and then, you know, and kind of make a decision for yourself. So anyway, so bench power supply. And then if we go here and we go to Amazon, and you just put in benchtop power supply, right? That's kind of, or bench power supply. You can see a number of these things pop up here, right? And the first thing, now, of course, depending on what country you're from, Amazon is usually in most countries, so you can at least search using Amazon, use it as a search tool to kind of see some of these different manufacturers, and then you could see what you could get locally in your country, but many of these are worldwide manufacturers. So if we take a look through here, some of these are completely no-name brands. You never heard of them. I've never heard of them. But like there's the BK Precision. This Tech Power is a good power supply company. I like this good power supply. This Corad also good company. And then you can see they have here's a one channel. This is another one channel right here. You can control voltage, you can control current, you control voltage, you can control current, and so forth. And so what you're looking for in these things is what's the maximum voltage they can supply, what's the maximum current they can supply, right? And then you're looking for the kind of display that they have. Is the display going to give you what you need? So, for example, let's go just take one of these for example. Let's take this Tech Power bestseller. And things can be a bestseller just because they're low price, so be careful of that. So in this one, we have a current and voltage, so we could control and put this into constant current mode or constant voltage mode, so we can control both of these, all right? And so we've got power right here, and then we've got our output. But one thing, and of course the display, voltage and current here display. And then if we look at this is 0 to 30 volts and 0 to 5 amps. So this is pretty good. Now, this company, so, and again, this is a whole story here, but Mastech is a company that both manufactures and resells other power supplies, Mastech. Remember that. So they're really good, and these guys are engineers, so they actually know what they're doing. They build power supplies, they resell power supplies, and if you go to Mastech's actual website, you can buy power supplies. And then many of these power supplies will look alike, but they've just been rebranded. So a lot of times companies will purchase power supplies from an original equipment manufacturer, then they'll add value to them, and so they're a value-added reseller, and maybe they'll add some clips to it or some alligator clips, some other parts to it, and then they'll put their logo on it and so forth. So again, you're going to see Mastech a lot. Now, what bothers me about this power supply, it's got good voltage, good current, but it doesn't have an output enable. And so what that means is this: when you connect this power supply to your hardware that you're working with, there is no way to turn the thing off other than pressing this on and off button. So basically, when you're working, what you'd like to do is you'd like to keep the thing on, adjust something, and then turn the power lines on, and then press another button, and then turn the power lines off, but you want to keep the thing on. If you turn it on and off every time, these power lines are going to potentially spike up and down. If you've got them connected to your hardware, that could be really bad. So what you really want is a an output enable switch. So that's one thing I always look for, is an output enable switch. All right. Okay, so anyway, moving on, and then we go down here, and then we have something like this, a Tech Power, and this is a 4-channel, and here's a, looks like a 3-channel. So let's take a look at this, this 4-channel right here. So 4-channel, and then now typically with some of these, so this has got 4 different output channels. A couple of them are fixed, meaning they might be at 0 to 5 volts or just 5 volts, or may not go to the full range, okay? So if you look up here and read through this, 2 0 to 30 volt, 0 to 2 amp, okay? And then 2 auxiliary outputs with fixed current of 2.2 with a fixed current of 2.2 to 5.2 volts at 1 amp, or an 8 to 15 1 amp. Okay, that literally made no sense to me. So let's look here. All right, and this will probably make it easier. Okay, so what this says, like channel 4 can go 8 to 15 volts and it maxes out at 1 amp. And then channel 2 is 0 to 30 volts and it goes 0 to 2 amps. Okay, great. And then channel 1 is 0 to 30 volts, 0 to 2 amps. And then channel 3 can go 2.2 to 5.2 volts at 1 amp. So that would be great for our 3.3 volt supply maybe. And then it looks like we've got another 5 volt, 2 amp USB port right there. Now, if you look, this has got this output on off. And let me, here we go. So this has got this output on off. So there's that button that I'm talking about that I like, right? That button right there is going to allow us to turn the output on and off without turning the entire system on and off with the main power. So this looks like a nice supply. So I might try this supply and see if I liked it and work with it and so forth. All right. So those are your power supplies, and you know, like any tool, you get what you pay for. So you want to buy this once and you know, and use it. All right, so let's take a quick look over to some of my power supplies, and I've got many of them all over the lab here, but I'll just show you a couple. We've looked at them before, but let's just take a quick look again so you can just make sure we're talking about the same thing here. Okay, so right here we've got this 9-volt supply. Let me steady that camera for you, sorry. We've got this 9-volt supply right here. All right, and so I've got voltage adjust coarse, voltage adjust fine, and then I've got current adjust, and then I've got the main power, and then we've got the DC out. So this is that enable switch that I like. All right, so that's important. Now over here I've got another power supply, and again we can just turn this on. All right. And same thing, we've got current and voltage adjustment, we've got high and low scale, but what I'm missing on this is that output enable. Now the reason I got this is because I liked the voltage and the current of it, but it doesn't have that output enable, and so I'm really not as happy as I could be. Now it was my fault, I bought it and I knew I bought it, and I bought it exactly for that reason. Because of I needed this supply to do something else. Now take a look here. One thing I want you to notice, and I don't think you can see it with the camera, but this says 3006B, right? And this is ProTech, and then this is Mastech, and it says 3006D. So see how they use the same numbers? They almost look alike, and that's why I say this Mastech, ProTech, many of these companies are resellers or OEMs or VARs, and they're all using the same stuff, all right? But they have different qualities and so forth, so watch out. All right, then up here, Now this is a 3-channel supply, and we've got 3 channels, 1, 2, 3 channels. It's all digital. We can adjust everything. We plug everything in here, and then we've got output enables and so forth. So this is a really, really good supply. And again, this is not manufactured by this company, Circuit Specialists. They're resellers of this, and this could be a supply from another company, but they check the supplies and they warranty them and so forth. So this is a really good supply, and I really love this supply. So anyway, that's the kind of stuff for your benchtop power supplies. And then, I use all of these simultaneously many times because I need so many different voltages, okay? Okay, so let's move back here and let's go through the material a little bit more here. All right, so the other thing that we've talked about before are the digital multimeters. We've been using these a lot, and this is measures resistance, voltage, current, can measure capacitance, it can measure all kinds of things, sound, audio levels, light levels. It might have different adapters. It can measure AC, it can measure DC. Again, you get what you pay for with these things, and you can get a low-cost one that's really good, but you can get a low-cost one that's junk. So what I want you to watch out for, again, is if you're going to pick something, find a price range you're comfortable with, and then just start Googling and searching on Amazon, looking at reviews, and then look for the features that you want. And that's the best thing that you can do when you're looking at multimeters. So again, let me show you a few multimeters here. So, here's a meter, and again, we've got current, we've got voltage, we've got, this one measures capacitance, there's resistance, this one measures also transistor gain, so you can do that. This meter will measure up to 20 amps, so there's, one of your concerns. This is a BK meter, for example. DC and AC. In AC mode, I believe this will go up to, I think this will go to 750 volts. It's pretty good that way. It also acts as a logic analyzer, which we'll talk about in a second. It'll also measure frequency. See that kilohertz? So it can measure frequency. Let's see what else. And I don't think this one does inductance. I don't think this one does inductance. It does just capacitance. So again, this has got a lot of features on it, all right? And so, maybe that's what you want, right? Then you can go down and this is a nice meter right here, and this is a Sinometer, I believe it's called Sinometer, and I'm just looking at it, and this is MS8229, MS8229, and 5-in-1. And why I like this meter is it's nice, it's robust, it's got voltage, it can measure resistance, capacitance, diodes. And temperature also. A lot of meters have what's called a thermocouple. You can plug it in to the probes and measure temperatures, all right, with two dislike metals put together, it creates a thermocouple. But I think the reason I bought this is because you see this dB and lux. So I needed another meter to measure, and this is audio, sound. So this is dB pressure. So this is sound pressure level. So this can actually measure sound pressure level. And then if I'm right, if we look here, right here at the end here, this is the light meter, and then this is a humidity meter right here, and then I believe, yeah, this is the sound meter right here. So how cool is that? So built into this, it can measure light, and it can measure humidity and temperature, and it can measure sound. So for example, if we put this thing on lux mode, all right, and I point it up at one of the lights, see that? 450 lux. Lux is a measurement of light. And then if I put it at another light over here, let me see, there we go, 500, right? And then we could put it on dB, all right? And then you have to see how to measure, how this measurement exactly relates to sound pressure level. But so I'm just going to not talk for a second, and we'll let it calm down. Let's see what it does. Okay, so 42.9 was kind of the average sound pressure in dB right there with no talking. Now I'll make a constant tone. All right, and I put it up to 86. So anyway, so how cool is that? So it can measure sound, it can measure light, and a bunch of other things. So if that's what you need, then you could get a meter like this. And then I think the other thing I like about this is, I believe, does this have a backlight? Maybe, maybe not. I like backlights. So this is an LCD display, obviously, but I like when they have backlights. I like lights. What can I tell you? All right, so anyway, so that's a great meter there. And then going up the ladder, a little bit more expensive, but not all the way to a fluke meter. So this is kind of one of my more expensive meters, and this is a couple $100s. And let me back out just a little bit so you can see it just a little bit. And this is by a company TPI, and they have a whole range of meters. This is the TPI 192 2, and this is a smart meter. And you've seen me use this. We've used this before, right? And this has, you know, all kinds of features. Again, it's got all the features of the previous ones. In addition to this, it also can measure inductance, which we like. And its ranges are higher and lower than many of the other meters. You know, for example, this can handle up to 1,000 volts DC, 700 volts AC, and so forth. So this has got some large ranges. And this, I believe, this one's a true RMS meter for measuring AC. So this is calculating true RMS and not cheating. The other feature I like about this is on the back here. And let me see if I can get that to focus. This is an IR link. So if you have a piece of hardware, you can link to the computer and you can log data. Now, I don't actually like the IR link. I'd rather have a physical cable to plug in here, either USB or a serial cable, an RS-232A. But on this model, they don't have it. They just have the IR link. So I do have the IR hardware, but I prefer just plugging in a cable. Anyway, this is a very nice meter, and if you've got the $200-300 to get something like this, this is an instrument in itself. There's a big, thick manual, and it has all kinds of functionality. I haven't figured out half of it. I've had it for years. Okay, so that's that meter. Okay, so let's keep moving here. So, all right, we've talked about multimeters a little bit, and yeah, so this is some good review right here. So, and to use the meter, we do a couple things with it. We measure things with it. So, if you want to measure resistance with it, and you've got your meter, you need to remember you need to take that resistor out of the circuit. So, if you've got the resistor in a circuit, right, pull it out of the circuit. And the reason why is the component might be connected to the power supply. It might be connected to other impedances or resistances. So, you need to pull it out, or at least pull out one end of it so that one end could be connected and the other end can be free. All right, then we can get a true reading. All right, and then here's measuring voltage. So now the circuit is active. The circuit's doing whatever we want. We put the voltmeter or the amp meter or the multimeter, right, multimeter, and that's why it's called multimeter, into the voltage mode with the proper scale, whatever we anticipate the voltage being. And you're not going to hurt the meter if you put it in the wrong scale. It just won't read right. And then you can switch scales, and you put it in parallel over the component, right? Let the component do what it's doing, and then you measure the voltage and kind of sense that voltage without disturbing the circuit. Okay, so that's how you do that. And last little thing here is measuring current with a multimeter. This is the trick. This one gets everybody. When I was doing my electrical engineering degree, I don't know, a long time ago, I would see graduate students not know how to measure current. And it would be funny. We'd sit there and we're in a lab, and there's a graduate student sitting there, and I'm like watching him, and I'm just laughing, and I'm like, what are you doing? And he's like, I don't know. You really don't know what you're doing yet? You've got a degree in electrical engineering, and it's surprising because electrical engineering is a lot of theory, right? And if you don't do stuff, you just don't know what to do with any of this stuff, right? And so that's why it's really important what we're doing in this class is hands-on, that we actually know what we're doing and we actually touch things. So measuring current in this diagram right here, we've got a circuit. The circuit's, it's online, it's active, it's doing whatever it's doing. To measure current, we need to break the circuit open, right? And then insert the amp meter into the circuit, and then we could turn the circuit off to do this, and then insert the amp meter and then turn it back on, right, to be safe. Or if you know what you're doing, then do whatever you want to do. But the amp meter needs to be in the circuit, serially in the circuit, in series in the circuit, and that's what you see here. So now the current normally that would be flowing around this loop now goes into the amp meter, comes back out of the amp meter, and then goes on its merry way. So we sense the current in the amp meter and then push it back out and let it go on its merry way. Of course, this affects it a little bit, right? And there's a small little tiny voltage drop in the amp meter, right? So we actually disturb the circuit by reading the current. We also disturb the circuit by reading the voltage because we're an impedance on that resistor. That's why the quality of the multimeter is important depending on the level and size of measurements you're going to be making. If you're going to be dealing with volts and milliamps, any meter will probably do. But when you get down to millivolts and microamps, right, then you're going to have to be sure that your meter is accurate enough to get what you need measured. Okay? So, and again, one thing, Just like when you're doing voltage, if you put the probes the wrong way, you're not going to hurt it. It's just going to show a negative number, right? If the current's going in the opposite direction or the voltage is in the opposite polarity, okay? All right, so let's see what else we have here. Okay, this is a useful tool. So as we get into digital electronics more, which we're going to push into after we do some analysis and theory stuff coming up, a logic probe is simply a device where I want to know on my circuit board, I want to know, is that a 1 or a 0 on that pin, a 1 or a 0? In other words, is there a 5 volts or a 0 if we're using 5-volt logic, or if we're using 3.3 volt logic, is there a 1 or a 0, which would be 3.3 or 0 volts? Either way, a logic probe is a device that does that. So let me show you one. Let's go over to the bench. So this is a logic probe right here, and let me see if I can get the camera to, yeah, there we go. So that's a logic probe, and this one's WaveTech, and this is an LP10, and there's LP10, LP20, LP10A, just different versions of them. And what this thing's main purpose is, you can see this little tip right here. So if we had our circuit here, and we had a chip in here or something, right? And let's just kind of loosely populate a chip in here real quick. And let's just say that this was a digital chip. So we got a digital chip, and I wanted to know what signals are happening here. I would put the logic probe on here, and I could measure them either ones or zeros. Now remember, in digital electronics, everything is either on or off, 5 volts or 0 volts or 3.3 volts and 0 volts, depending on what your logic levels are, right? So that's what the logic probe is for. And this little light would glow red if it was high and green if it was low, and then see TTL and CMOS. So we put it in which logic levels are we using, which logic family, transistor logic or CMOS, and that kind of changes what the voltage levels are. And then this one also can inject a signal, that's what this pulse is, and this memory is to record pulses. And then it hooks up very easily. You just hook it up to the power. So this would go to ground, and this would go to the same power like the 5 volt or 3.3 volt supply, and then you have this probe, and then you just use it as a tool. So this is just the tool to read a single digital signal, and you can't record it on video or on the screen or anything. Just it's like printf, right? If you're a programmer, this is just a printf statement basically, and I can just see what's going on. Okay, and that's all that does for us. Okay. All right, so moving on, what else do we have here? We have got, so that's a logic probe. All right, the oscilloscope. So the oscilloscope is a device that allows us to measure voltage in real time. So we can measure signals in real time, and these signals can be from hertz to thousands of hertz, kilohertz, to megahertz, to even gigahertz, and even higher. And so it allows us to see these signals. We record them or digitize them or play them in real time on a screen. All right, now the original oscilloscopes were analog in nature, and I talked about this before. And basically, there's a screen, and on the screen, there's an electron gun scanning, right? And so it would be scanning back and forth, and then the voltage would modulate the vertical axis, and then we'd have a timing circuit modulating the horizontal axis. So the beam would go across, turn off, come back, come back, come back, and then whatever was happening with the voltage input would modulate the vertical axis of it, and you would see it. Okay, that's what an oscilloscope is. So there's still analog oscilloscopes, but now there's also digital oscilloscopes that digitize the signals, then do everything in digital signal processing in digital space, and then render it on an LCD, or they could be USB and connect to the computer and use the computer as the compute. So here's just a generic. This is an Agilent, a very expensive oscilloscope. Agilent is a very expensive equipment company, and just kind of showing what one looks like. And we use this in a couple experiments, and I'm going to show you a couple in a second here. And yeah, so let's stay there. So now a couple, and this I want to talk about a little bit here. So so for example, let's go back to Amazon here, and we're just going to use this as a search engine, and we're going to type in oscilloscope. All right, and I want to show you just some things that you might consider if you're going to get into electronics. You really do want to get an oscilloscope, and you kind of get what you pay for again. So again, you can get used ones off eBay or whatever, but you know, they cost a few $100s if you want to get a benchtop oscilloscope. Now you can get a USB oscilloscope that's much less costly, right? So again, it's what do you want to do in your budget, right? If you want to start playing with electronics, you do need equipment. So a couple that I really like are Rigol and Hantek. And let's see here. We'll have to do a search for Hantek. So here, for example, is this Rigol DS1054. This is a 50 megahertz digital storage oscilloscope with 4 channels. Let's take a quick look. All right, so digital storage oscilloscope means it digitizes events and you can record them and then see them on the screen. Now, 4 channels mean 4 different things you can look at simultaneously, 4 different analog signals that you can look at simultaneously. So that's really useful, right? If you're building amplifiers or whatever, right? But this has a limit, and that limitation is this 50 megahertz. So that means the input bandwidth to any of these channels is limited to about 50 megahertz. And what does that mean? So that means if I want to look at a signal that's 100 megahertz, I can't. And it means if I look at a signal that's 50 megahertz, I barely can. So that's what that input bandwidth is. And so we really want that high. The higher it is, the more expensive the piece of equipment. All right, so now if we type in, for example, Hantek oscilloscope, and Rigol has oscilloscopes that go much higher as well. I just wanted to show you this other manufacturer. So here's some of the Hantek, and this is another good manufacturer. And let me show you. Let me see if I can find one that I like. Let's see. I think this is almost, yeah. I think this is 5202P. Almost. This is almost the one that I have on my bench here, which we're going to take a look at. So you can see here it is here, and it's got 2 channels and a very large LCD screen, a little USB port, and this way you can record and pull out the data as you do experiments. You can pull data out, you can connect it to the computer, that kind of thing. But what I want to bring your attention to is this is a 200 megahertz oscilloscope, meaning each one of these channels can support up to a signal of 200 megahertz, which is really cool. And then it shows 1 gigasample per second, and that means the bandwidth is 200 megahertz. So that's the input bandwidth before the signal just attenuates down. And it can sample 1 gigasample a second. So that basically means we can sample about 5 times as fast as the maximum bandwidth of the oscilloscope itself. So this is a great piece of equipment. And you can see it's got, well, 6 stars, 6 reviews of all 5-star. So anyway, this is a great piece of equipment right here. But it's just an oscilloscope, and the other one's an oscilloscope. Now, if you don't have that budget, you can do you know, things much less. For example, this is a good one. This PC-based USB digital source oscilloscope. Again, this is a lower bandwidth, 50 megahertz, but it's only $139. And in this case, it uses your PC as the compute engine, and you plug this thing into your PC and then use a piece of software. And we can take a look here, and the software kind of looks like this. So you hook it up to the PC, you got the piece of hardware, you don't have to pay for all the screen and all that, so now use the PC. That's another way to go. And I've been doing this for logic analyzers. I won't buy any more desktop logic analyzers, but I do like desktop oscilloscopes, okay? And we're going to look at those in a second. Now, before I go from this topic, and again, we can go even cheaper. Here's another Hantek. This one is this one's 8-channel digital oscilloscope, and I'm not sure what the bandwidth is of this one. We could look here and let's see, vehicle testing. We'd have to look, but the whole point is that you can really, you know, depending on your budget, find something to get the job done. But remember, for $200, you can probably go on eBay and get something, one of these desktop models, you know, that's just used for much, much less. You might be able to find this $300 one for half the price because it's used. So keep that in mind, but you do need an oscilloscope of some kind, all right? Or you're just going to be blind doing electronics. Okay, let's keep going. So what do we have next here? So we talked about the oscilloscope. We took and we're actually going to look at those in a moment on the bench here and see some of those. But I first want to look at another similar piece of equipment, and this is the logic analyzer. And we may have talked about this before. I think we did. But logic analyzers are like oscilloscopes, except they deal with digital signals. So instead of having analog signals that you're inputting that could vary from anything to anything, they're looking at digital signals from 0 to 5 volts, 0 to 3 volts, 0 to 1.8 volts, whatever the digital signal levels are, that's what it's going to be monitoring. So how these things work is instead of digitizing the entire signal, they're looking for the highs and the lows for a digital system. So here's a benchtop version here, and I believe this is an HP. I've got one right here in HP as well, and this is a 1650A. I'm not sure which this one is. I can barely see it. Product page image, but 1650A. This one is a black and white, old school, and this bag up here is a bunch of pods which have a bunch of cables on them, which then you meticulously connect to all your different signals on your digital circuit, your processor, your this, your that, whatever, and then you set this logic analyzer up so that it can read these signals. So let me, as a matter of fact, let me see here. Yeah. So this is a company called Bitscope, and they make USB logic analyzers. So again, instead of the big screen and the housing, they throw all that away, use your computer for it, and then they reduce the cost, and then all the devices is a data acquisition device, and then the computer becomes the rendering device. So here's what a logic analyzer looks like when you get an output from it. Now this looks overwhelming at first, but it's really not. It's actually very cool. So let's kind of just look at this, what's going on here. So in this case, this user has a number of different channels connected from the logic analyzer, and some of these are single signals and some of them are more than one signal. So even though we're not going to learn about this in this course, there are protocols in digital electronics for communicating serially. One of them is called SPI, Serial Peripheral Interface. Another one is called I2C, which stands for Integrated Circuit Communications, and there are a number of other ones. And the pins and the signals on those protocols, for example, I can see them up here. So what this user is doing is, he said that I want this one pin to be master out, serial in, this other pin is going to be master in, serial out, and so on and so forth. Then what's happening is the logic analyzer itself understands the protocol, so it's as it reads in this MISO and this MOSI, this MISO MOSA, and this is master in, serial out, master out, serial in, and this is S clock or serial clock. This is a SPI interface right here that's on the screen. Not only will it show you the data, but it actually decodes it for you so you can see what's going on. So this is called a protocol analyzer, which is really cool. And then some of the other signals are just pure digital. This control signal, who knows what that is? It's just showing here it's high, here it's low, here it's high, here it's low. And then there's a couple other things up here, phase, timer, this and that. And then see this sensor signal up top here? This is an analog signal, so this particular Bitscope device probably has 1 or 2 analog channels in addition to all the digital channels. So you can watch a couple analog channels too, so that's great. So you can kind of see what's going on, and here's all your digital electronics operating, and here's your analog signal coming in maybe as you're processing it, and then all these different channels are representing things that you're doing inside of your hardware. This is a tremendously important tool and useful tool for engineering and building things. So even if your interest is in just to play with Arduinos, the only way that you can talk to the Arduino is through software. So you can't ask it questions really, right? So to ask it questions, you have to be able to debug it. So that means you would have to use a debugger. And the Arduino tool is not a debugger, the tool that you use to program an Arduino. And if you don't know what I'm talking about, then this won't mean too much. But you need a tool to be able to communicate to the processor and see what's going on. But those tools are always going through standard communication protocols built into these processors. What hardware debugging allows you, logic analyzers, oscilloscopes, logic probes, we actually go onto the hardware, onto the pins themselves, and we see what the signals are. There's no cheating, lying, evading. We know what the signals are, and that's how you really debug something. All right, and that's why these pieces of equipment are very important. Okay, so that's a logic analyzer. Like I said, these pieces of equipment can be very, very costly, and ready for this, up to $100,000 easily. $100,000 if you want a really good benchtop, high frequency, multiple channel, crazy logic analyzer. A good logic analyzer will cost about $1,000, $2,000, and the word good is relative, $1,000, $2,000, but you can get USB logic analyzers just for a few $100s. So let's take a look at those real quick. So let's go back here, and what we're going to do is we're going to say Handtech. Take a look here. Let me show you this. logic analyzer. And so again, here is a PC base. This is only $79, and this one's got 16 channels. All right, and you know, there it is. So you hook it up to your PC, and you do what you do. And then on the back here, let me show you. So on the back here, you can see here's kind of a couple connections, and this is probably, it's also probably got the oscilloscope functionality, but here's where those digital channels are. And so it looks like it's A, B, C, D, whatever it is. There's 8 or 16 channels here and grounds, and then you'll have a big cable. And let me see if we can see the cable. Yeah, so here are the cables, and these are just like those little cables that we have for hookup wire. And then you can see the little clips on them. And these little tiny little clips are what you clip onto your digital signals. And there you go. There's a logic analyzer. And you know, it's for $70. And you know, the customers sort of like it, whatever. Again, you got to kind of do everything yourself. You know, see what you think. Read about things. There's lots of reviews online. But what I like are these. These are dual devices. They're both oscilloscopes and logic analyzers. And for example, this one right here, and this is called a mixed device, MSO5202D. And this one is really cool. It's an oscilloscope, 2-channel oscilloscope, and it's a logic analyzer. So if you back out here, it's a 16-channel logic analyzer. So it's 2-in-1, and it's 200 megahertz. We lost 2 channels. The other one had 4 channels. This one's only got 2, but we've got 16 logic channels. All right. And then we need, then you need to get the probe kit, which is right here. All right. And then, I'm not sure if this particular listing comes with this, and you can see this plugs into that port up front, and then there's your logic analyzer pins, and then there are your little clips. So in one fell swoop, you can get this device, and it does everything you need it to do, and then just plug your logic analyzer. That's what I recommend if you have the money, is to get one of these mixed devices that have both oscilloscope and a logic analyzer, and then you're kind of good to go. But if you can't, then go ahead and just get a USB logic analyzer. Now, one of the ones that I like, if I can see it here, is that Zero Plus logic analyzer. And it's a USB logic analyzer. And so here's a 16-channel one. And okay, look at these prices, and they seem to be wildly different. They're both 16-channel, but one of them says 128, one of them says 32, 16032 and 16128. The difference is how much memory that it has, what's the depth of the digitization buffer, so you can record events. So the one that I have, I'm not quite sure. I'm looking at it right here. And yep, so I have this 16128, right? But you know what? This one right here is just fine. The 135, it's still got 16 channels. You just have much less of a recording buffer, so you get to record less events. Either way, again, you know, there's the channels on the device. They look like that. You plug in, they're color coded, all right? And then there's a piece of software that you use, and the software runs on the PC and then connects to it, and then it's just a logic analyzer, except it's not on the desktop, all right? So so that's that. Okay, let's see here. What else do we have? All right, that was a logic analyzer. Okay, so now what I'd like to do is let's take a quick look at the oscilloscopes over here. I'd like you to see things, and on the screen is fine, but I want you to see things. Then we're going to come back and talk about building materials, and we're actually going to build some stuff. All right, so let's go onto the bench here, and let's take a look at a couple of these oscilloscopes and whatnot, just to take a quick look again. Even I know you've seen them, but let's take a quick look. All right. Okay, so what we're looking at right here, we've got 2 oscilloscopes. And the top one is a LG, like Life is Good, the manufacturer television sets. And the bottom one is a Textronics. And Textronics is one of the major brands in electronic test equipment. And so both of these are analog oscilloscopes. And the top one has 2 channels, channel 1 and channel 2, and the bottom has 4, 1, 2, 3, 4 channels. And in this case, what I've got is each one of these have a calibration point, and this little probe, this little tip right here, that's got a, in this case, it's got a 1 kilohertz, I believe it's 1 kilohertz half volt signal coming out of it, square wave, and we can put that probe on there to test things, and we just get a good connection here, and all these probes are touching everything. All right, and let's get this nice and grounded. All right. And so that's how we can kind of calibrate and mess with it. Same thing with the bottom. In the bottom case, we've got this Textronics with 4 channels. Now, The top scope is fairly simple. We can control the gain or the amplification on each channel, so that's scaling it, right? Then same thing with the channel B, right? They're identical. Then the horizontal time sweep, this is how fast we're sweeping this electron gun, so we can change the frequency of this. And then if we look here, this is how many milliseconds per division. So right now if I put it here, it says it's 1 millisecond per division, 1 millisecond per division. So here it's 0.5 milliseconds per division. So if we were to move this signal around here and align it, and then we count how many divisions. So each one of these complete cycles is 2 divisions. So 2 divisions times 0.5 is 1 millisecond. And if you take 1 millisecond and put it on your calculator and invert it, that's 1 kilohertz, right? So if the period is 1 millisecond, the frequency is 1 kilohertz. So in fact, it is 1 kilohertz. And then it says it's 0.5 volts peak to peak. Okay, so if we look on the vertical scale, how I've got it right here, all right, and then we can position this and move this around. All right, and we'll open this up a little bit. So it looks like we've got from this bottom to the top, we've got 1, 2, 3, 4, 5. And it's set at exactly 0.1 volts per division. And this says it's 0.5 volts. So 5 times 0.1 is 0.5. So that is correct. So that looks calibrated. All right, now on this bottom one, this is kind of, the Cadillac of oscilloscopes at the time that that this was manufactured. So this is 100 megahertz. It's got 4 channels, and then it's got on-screen cursors for measurement and whatnot. You can do all kinds of things. There's lots of buttons to press and measurements that can be made, and then operating this thing, and it's measuring. So this one puts out the same thing, 1 kilohertz at 0.5 volts, and it's measuring it here for us. So you can see 0.504 volts. And again, we've got all 4 channels. We can adjust the vertical amplitude here and so forth, and the sweep frequency, right? So we can see more or less and say, oh, now that's an interesting thing. So hopefully you can see that. The reason it's flickering because we're drawing this on the screen. This electron gun is moving back and forth, and it's refreshing in such a rate that we can see this happening. And that's another reason why digital scopes, people prefer them, because this doesn't happen. All right, so anyway, there's 2 analog scopes that I use a lot. And one thing I like about this is because it is analog, it's showing you exactly what the signal is doing. There is no digitizing going on here. The analog signal is being amplified by analog hardware and going right in to drive these rendering guns, the CRT gun. So watch this. So as I change, look what I'm doing. I'm changing the sweep. So it's going, I'm just looking at one waveform. Now I'm looking at one edge. That's the edge of that square wave. So that perfect square wave that you think is perfect really looks like that. So I'm able to drill into it that much and see what's going on there, and that might matter for something that I'm designing. Okay? So anyway, so that's that oscilloscope, those 2 right there. And again, these analog scopes at the time, they were manufactured, were pretty good, and they do what I need them to do still. But I'll usually go over to the digital scope. So let me show you the digital scope again, which you've seen. Okay, so over here we see this Hantek digital scope, and this is a digital storage oscilloscope. This is 2 channel, 200 megahertz, and 1 gigasample per second. And this is kind of what I prefer to use now. And let's do the same thing that we did over there. Let's get one of the test probes here, and we'll connect this to this output here, which in this case, this one is 5 volts, 1 kilohertz, I believe. So we'll connect it there. And then if you look at this, let me see if I can get this in camera here to focus. So it's got this little clip, all right? And we'll put that there, all right? We'll ground that just as an extra ground. There's always a ground with each one of these probes because you need a voltage reference, right? Otherwise you can't measure anything. Okay, and so we've got the scope on channel 1. We see channel 1 there. We could change the horizontal sweep here, and it stays purely digital, right? Purely digital. And then we see different things here. It's saying it's 1 kilohertz. It's saying the sweep is 800 microseconds per division, this kind of thing. We can measure things now. So if we want, we could measure. And this is what's cool about it. So if we press this button measure, all right, so it's telling us what the period is, what the frequency is, and all these different things. We can push these buttons and get different kind of values here. And for example, let's see, go back up here and we could say what is the frequency, all right, and 1 kilohertz, and then we could put some cursors up and measure things ourselves. So say we want to actually, do this ourselves and measure it. And you see me, I'm just lots of adjustments on oscilloscope. This is the vertical, this is the horizontal sweep, this is the voltage amplification, right? The gain. Okay, now we're going to put cursors down, and we're going to say we want to measure time. We want to measure channel 1. All right, and then there's start and end. So let's just play with the start. Then this little knob here becomes our adjustment, and I'll put it to the left here of 1 signal, of 1 cycle. All right, then I'll press this button, and then I'll adjust this to the end of the cycle, and this should be exactly 1 millisecond and 1 kilohertz. And if you look down here, look at that. 1 millisecond and 1 kilohertz exactly. Let's see, what's the voltage now? What's the voltage level? So we'll change the cursor types to voltage. All right, and then we'll adjust the end cursor here to the bottom, because we want to measure the amplitude of this thing to the bottom. And then we'll, go here. And you see, this looks crazy, all these buttons, and it is. You just play with it like anything, and then you get the hang of where everything is. All right, and the amplitude, there we go. And look at that, lo and behold, the amplitude is dV 5 volts, and that's exactly what it should be from this little signal coming over here from the right. So that is an oscilloscope, a digital oscilloscope, and then what's cool is if we press this button, that stop button up there, this is the storage aspect of it. And we recorded the signal. So now we can print it out, we can do anything we want with it. It's in memory. And then we can turn the thing back on again, and now it's operating in real time again. Okay? So that's kind of cool. And then let me do, let's just do one last little fun thing. I'm always just kind of trying to make stuff up to make things fun and interesting. All right, so one of the cool things you can do with an oscilloscope, of course, is analyze signals. So, but we need a signal, right? So let's get an audio signal. All right, so what I could do is I'm playing music in the background here real lightly so I don't go crazy. But we could take that signal and bring it in and analyze it. But instead, why don't we do this? So this is a speaker, a really small speaker. It's a real small speaker. And a speaker is basically the same as a microphone. We can use it the same as a microphone in the opposite direction. So instead of putting a signal into it and letting it move air in and out, right? That's what a speaker does. It has an electromagnet, a coil, permanent magnet, an electromagnet. As you apply a current, it moves in and out proportional to the signal, the audio signal, and it makes music, right? But we can use this in the opposite direction. We just got to make a lot of noise, all right, because this thing's big. So what we're going to do is we're going to hook it up. We're going to hook it up to our oscilloscope here, okay? And then we're going to first adjust our oscilloscope to do a 4 millisecond event. We're going to lower, we're going to turn the gain up here so that we're looking at 200 millivolts. And we're going to turn this cursor off right here, all right? And then we're going to see if we can see something here. All right, so I'm going to talk into this really, really loud right now. All right, so I'm going to kind of cover the mic up a little bit and scream into this. All right, so let's turn this up a little bit more. And let's turn it up even more. So you can see that. And let me open this up a little bit. Okay. And then, hello, hello. So you can see it's playing back my voice, right? So now let's see, can we digitize a word, right? So what we're going to do is, and this is always a little bit harder said than done in real time, but we'll give it a try. All right, so what we want to do is, if I can find my trigger level here, okay, and when you want to record something, you need a trigger. So how that works is the oscilloscope reads the channel that you're triggering on, and it waits for that event to occur, which is usually just a voltage amplitude. When that voltage amplitude hits, then it'll start recording. So you see this green line moving up and down? That's the trigger level. And what we're going to do is we're going to set the trigger level above the noise so that it's not going to trigger until I speak into it loud enough to cause a trigger. Okay? All right. And then we're going to put it into trigger mode. Okay, so we have the oscilloscope adjusted so that we can get it to sample my voice and record and trigger and all that. So here we go. Hello! And do it again. A, B, C. And it's not as easy as it seems because we've got to do it loud enough to get the impulse. Let me do the A again. That seemed to work. A. Okay, so now that we have a signal, now we can scroll it back and we can open it up and we can look at it. And you can see, so in general, when I say A, right, it's the frequency looks like it's fairly constant, but there's a modulation on the amplitude. So it looks like a constant frequency and the amplitude is modulating, and that's kind of what makes an A, at least for me. All right, and now there's another interesting thing that oscilloscopes can do, especially advanced oscilloscopes, is they have math menus. All right, and like this channel 1 right here, we can go ahead and we can do things like a fast Fourier transform, and we can actually look at the frequency content of the signal. And in this case right here, it's showing the peaks and so forth of the signal, and it's saying that, hey, at a, we can scroll this over and to the position and read the values and read these things off and see what the different frequencies are that make up the spectrum of that sample. And you can do that with any signal as well. So we'll just take that back off and go back to that. Anyway, so that's an oscilloscope. That's a digital storage oscilloscope. Very cool device, very useful, and absolutely needed if you're going to do electronics. Okay, all right, so let's move on to building some stuff now, and kind of some hands-on stuff with putting things together, and let's see how that goes. All right, so I'll meet you in the next lecture, so get ready and we'll go do that. So I'll see you there. Bye. Okay, welcome to the next lecture. We're continuing on with our equipment and tools and fabrication and construction of electronics. And like I said, as we build things, we'll always add more and look at more different things, but it's nice just to have a bird's eye view and take a look at some stuff briefly. So we're going to talk a little bit more, and then we're going to go on to the bench, and we're going to start taking a look at some actual equipment to build things. And so this is going to be a lot of fun. All right, so look on the screen. And again, just to follow along, it's just something to follow along and anchor ourselves with. So we're going to be talking about basic tools and wire, right? Because that's what we're going to be building things out of, right? So, and we're going to look at these on the bench, but you're going to want to have some wire cutters, wire strippers, so you can cut, so you can strip the wires, some needle nose pliers, and any other small electronic tools that you might feel that you need to grab onto things and do things with. So there's like little kits that have a couple different needle nose pliers and parts, and that's a good thing to get. And again, quality does matter. So if you get things that are junky and cheap, they won't fit right. So like if you have some needle nose pliers, when the jaws come down, they may not close flush, and you want things to close flush and be nice and tight. So you want to get good equipment. All right. Another thing is we're going to need wire to build stuff, and I'm going to show you some wires in a little bit. We've been using those little yellow wires, but I want to kind of exactly show you what gauge those are and all that. I'm going to talk about that in 1 second. The experimenter boards, we've been using these solderless breadboards, and we looked at a bunch of different ones of those. So we'll take another look at those also. Let's see here. And, those make it very easy to put things together. Take a look at this little circuit right here. We're going to do something like this. We're going to actually build this, momentarily. So that'll be a lot of fun. And let's see here. Wire wrapping. So we've built things on solderless breadboard with just pre-cut wires. Now there's another technique called wire wrapping we're actually going to take a look at. I just want to talk about it right now. And so this is wire wrap board, and basically what this is, it's a PCB with a bunch of holes in it, and sometimes it has different art and different kind of patterns and footprints to help you place your components. And then in this case, it's got ground rails all around the edges, in fact. Then on the other side, it's every one of the pads has some solder on it and some copper, so you can actually solder things to it. But how you actually connect the circuit up is really interesting. And so there's what something looks like put into this solderless breadboard. All right, this is a little 6809 video game console I made a long time ago for fun. And now let's look at the back. The back is where the action happens. Okay, so now how crazy is that? So every one of these little wires is connected, and if you look here, we can actually zoom in a little bit. Zoom in a little bit here, and you can see each one of these wires is actually curled around each one of these posts. And there's a tool, and you basically take these wires and you go point to point, you cut the piece of wire, then you go from point to point, you twirl the wire around, pull the wire, twirl it around, and cut it. So you have to have all these cuts, and you have to do this in a very, very clean fashion. And then you can see you also have to do everything upside down, backwards. So there's these little labels here that I purchased or created. Sometimes you can just print them out on your printer, and you put them on the back here so you can figure out what the pin numbers are from your design. So when you need pin 20 to pin 18, you don't have to keep turning the board upside down or counting. You can just see what they are because it's very easy to make mistakes. But the other thing that you can notice is that there is method to this. So you can see all these orange wires and these purple wires. These are buses. These are probably data buses and address buses because this is a single board computer. And yellow is probably control, red is power, black is power. And you could see that that as I did this, I tried to keep this as neat as possible and as flat as possible within time constraints and all that. So this is wire wrapping, and I know this looks insane. This is nothing. This is a tiny little board. This probably took me a couple days to wire wrap. Now, typically when people used to design circuits, integrated circuits, they would first make a model of it on a wire wrap board using discrete components. And for example, say if you wanted to make a new chip, a VLSI chip that did something, first you would work it out, and it would just be easier to build it than to simulate it because it was just too hard to simulate. So you might put hundreds of small chips on a big board like this, connect them all up, and then basically that big giant board, which could be 6 feet by 4 feet, for example, could be as big as a table, would have all the components on it, all wire wrapped together. Then you could verify the functionality of it, use the chip and all that, and then of course, then it would be converted into a format that you could actually put onto an integrated circuit. So this is nothing. This is super simple stuff, and this is what electrical engineers have to do all the time. So this is just one construction technique. Now, you could have just built this on a printed circuit board, but then you would have to design the printed circuit board, send the circuit board out, pay for the circuit board, or you could just do this in hours or days for no cost at all other than labor, yourself doing this labor. So it's just a different way of doing something, and it's fairly robust, and if you do it right, you could put this in a box and it would work. All right, so that's wire wrapping, and I'm going to show you that. All right, here's this wire wrapping tool. And one end is used to put the wire on, twist it on, and the other end is used to twist the wire off. All right. These tools are not cheap. They're actually about $15 to $30 because they're made very well and they have very high precision and tolerances, and they're made out of steel so they don't wear down. And you can see there's this like little slit here, and that's where you strip the insulation off the wire wrap wire, which is very, very thin. I'm going to show you some in a moment when we get over to the bench. Now, another thing that we're really not going to be doing any of in this course, at least I don't think, is soldering. And here's, a typical soldering iron. So you may or may not have ever soldered, and this may be something that terrifies you or not. But soldering iron is how we, connect circuits together. And so even if you were to wire wrap everything, you can see there's soldering here. Some things have to be soldered. These sockets have to be soldered in so they're stable, right? Because if you look at the top side, all these mechanical components are here, and they have to be soldered so that they are not going to get pulled out. And all these integrated circuits, instead of wire wrapping them into the printed circuit board, they go into sockets so they can be removed, right? So no matter what, you have to learn to solder. And like anything, you can buy a $1,000 soldering iron if you want. That's completely digital and has all kinds of features and functionality, or you can buy one that's $5. So what I suggest you do is buy something somewhere in the middle. Maybe spend 50 bucks, 100 bucks, 20 bucks if that's only your budget. Something that has an adjustable temperature or power. You can see in this one, this is a Weller soldering iron here on the screen, and I've got it set here for 806 degrees Fahrenheit. You can see it's got a little adjustment right here, and so I can see the temperature that it's at. This is called a pencil soldering iron, and because it looks like a pencil. And we're going to look at this right now. And then another thing that's really cool about these kinds of more advanced soldering irons is you see this cable plugs into the soldering iron. If the soldering iron goes bad or you want a different soldering iron, you can unscrew this and put a different one in here. So you have the base and you have the soldering iron itself, which gives it flexibility. Another thing is the tips of these can be exchanged and interchanged, so you can change what kind of tips you have for different kinds of soldering applications. All right, now these soldering irons, they can go very high wattage. Now, really cheap little soldering iron you might get from Radio Shack here in the United States, might be 15 to 25 watts. But I suggest that you use 40 to 60 watt soldering irons or higher, so that you have enough heat to maintain a stable temperature, and so that as you touch things, the temperature isn't going up and down all the time. And I suggest that you have something that has a tip that can be removed in exchange for smaller, finer tips or larger tips. And ideally, you should have a soldering station and not just a soldering iron. But I'm going to show you both, and both work just fine. Again, it's all about whatever your budget is and how far you want to get into this. But we're going to take a look at that stuff also. When you solder, a material called solder. We're going to look at that in a moment. But solder is typically, there's a couple kinds of solders, big, primary classes of them, leaded and non-leaded. And the typical solder that you'll use, and I'm going to show you on the bench, is made out of tin and lead, and like usually a 60-40 percentage. And then it also has what's called flux inside of it. And the flux is used as a lubricant. It also helps with heat flow, and it helps with deoxidizing the surfaces as they're soldering to keep them clean. So as a matter of fact, I want to show you. Let's go here. So here's solder on Wikipedia. You can take a look here. There's what a little spool of solder looks like, right? And I'm going to show you some. But and you can solder like pipes and stuff. We're not going to be doing that. We're soldering electronics. And there's another little roll of it. This one is tin 60%, lead 40%. And like I said, there also can be lead-free solders that have no lead in it. There can be silver-based solders for higher conductivity. Of course, they're expensive because they're literally made out of silver. And all kinds of different alloys. But typically, the one you're going to find the most is this tin leaded solder. So this means you don't want to be breathing this in. You want to have ventilation. And if you really want to, go crazy, you could wear a mask when you solder and all that. But at least ventilation, blowing it away or sucking away the fumes, right? Then another thing about solder is they have what's called a flux or rosin core. And so this is what we were talking about just a moment ago. The rosin or flux is used to help with heat flow and keeps the joints clean, makes a good electrical contact, and then helps them not oxidize. And this flux or rosin, it's actually from a tree, or it can be from a tree. And so rosin, you can actually look it up on Wikipedia, is a solid form of resin, obtained from pines. So a lot of times this is used, this is where the basis is of solder flux and resin. So of course now they synthesize these and various different chemical combinations are used to make it. But the whole point is that's kind of where that word came from, rosin core. All right, so ideally when we solder, we're going to want a good soldering iron with a tip. We're going to want to be able to control the temperature. We're going to want it to have some flux in it, a rosin core ideally, so that as we solder, the solder itself melts, and then it cleans up the surfaces so they make a good bond. And so that's kind of where we're going to start there. All right, and let's see here. Let's go back here. And then there's a number of different manufacturers of soldering irons. Hakko is a good one. You saw Weller just a moment ago, Weller, Hakko, and then there's all kinds of off-name brands as well. So anyway, let's go now to the bench and let's go take a look at some of these things and let's start building some stuff. So let's go over to the bench now and see what we see, all right? Okay, so what you're looking at here is the Hakko 936 or Hakko 936 soldering station. So this one's not digital, but it has a dial, and you can see I've got it about 800 degrees, I believe. Uh, Maybe 700, 750 degrees Fahrenheit. So this is a pencil soldering station, and this is actually on, and that little red light means it's powering up and powering down. It's maintaining the tip temperature. So this is hot right now. So one thing is when we mess around with soldering irons, make sure that you have your eye protection on, and if you want to wear gloves, you can do that too. But for eye protection, something like these polycarbonate glasses, or these right here, a little bit lighter weight. So if solder shoots out at you, it's not going to hurt your eyes. You can, withstand getting a little burn on your hand, but you surely can't withstand solder in your eye. That's very bad. So another thing you can wear is you can wear kind of like latex gloves or rubber gloves if you want. I don't wear them, and I rarely burn myself, rarely. Or you can wear some tighter fitting gloves if you want. But as long as you're careful, you're pretty safe. So I'm going to show you a few different things, and then we're going to kind of come back here and kind of focus on this a little bit more. Oops. I'm going to show you a few different things, and we're going to kind of come back here and focus on things a little bit more. But I just wanted to show you, there's what the tip of the soldering iron looks like, and it's hot right now. It's 700, 800 degrees, and this is a sponge, and it's actually got water in it. So now listen. So you can hear it burning. You can actually see the steam. And so as we solder, we use the sponge to clean it off and keep that tip really nice and clean, right? And this whole tip can be removed. You can see there's this little ring here, which you unscrew and then pull this assembly apart, and then you can put a different tip on that. All right, so that's a soldering iron. That's a soldering station. And then we have another soldering iron over here. Let me kind of slide this over just a little bit. And we've got this other one here, and I'll pull this out. Now this one is not on, and I'm going to double check that. All right, so this one is not on, and you can see this one right here. And again, we're going to take a closer look at these things in just a minute. But this is just a soldering iron, and it comes in such a way that you just plug it in. All right, and this one I believe is probably a 40 or 60 watt, and I believe this is a Hakko also, but I've had it for long enough where the part number is rubbed off of it. But again, you can see that this has got this adjustment right here that we can remove and change the tip, which I'm going to actually do that. And then this holder right here is just a generic holder and a sponge so that I can use this soldering iron. So now why do I have two? Well, I like to have many of everything, but specifically, I've got a very small tip on this one right now for fine work, and then a larger tip for heavier work, so if I have to solder something heavy. So I have both soldering irons on, and then I can do my fine surface mount work maybe with this one, and then I can do my heavier through-hole work with the other one. All right, and that's why you might have two soldering irons. So let's remember, this iron is hot, and respect it. One of the worst things that'll happen with the soldering iron is you'll accidentally, here's the cord to it, you'll grab it with your leg or your knee, and it falls, and then it falls on your leg. All right, so if you're wearing shorts or something, many times I've got burnt on my knees by the soldering iron falling off. Right, so that's a standard, really good quality soldering iron. I'd prefer if it had a digital display, but that was probably an extra $100, so I just said, I can just deal with that. All right, now before we continue on with some construction stuff, I want to show you a couple other soldering techniques or devices that are pretty cool. So let's go over and take a look at those. Okay, so what you're looking at here is this is called a hot air soldering station. And a hot air soldering station is exactly what it sounds like. It uses hot air to actually melt solder. And so when you're doing surface mount soldering and whatnot, you can actually use the hot air. So this guy right here, this attachment, hot air blows from this tip here, and you can change what the tips are, and they can have different diameters. And we can control the temperature of the hot air, which is down here. So this is what the temperature is, and then we can control the air velocity. And then also in this particular model, it also has a soldering iron in it as well. So this is a very, very useful device, and this is what you can solder and desolder surface mount devices with, and you can even do through hole if you want. So the nice thing about it is you can apply the hot air to a surface and the whole thing gets hot at once. So you're not just soldering single pins at a time. And now it might be kind of unbelievable that you could melt solder with hot air when you need to get something up to hundreds of degrees, but you surely can. And I can show you, for example, here, a little experiment we'll do. And let's make sure this is on camera here. So this pad is made of silicon, and this will withstand very high temperature. All right, and what I'm going to do is I've got some solder right here. Hopefully you can see that, and I'm going to turn the air up. All right, and then I'm going to blow this air across this solder, and hopefully you can see this. I think so, yeah. All right, and I'm going to blow it across this solder, and let's see if we can get the solder to melt. And sure enough, that solder is melting. And a hot little piece just went off. So if we were on a piece of circuit board here, we could actually melt that onto the circuit board. All right. So anyway, so that's a hot air rework station, and typically used for surface mount soldering, desoldering, and whatnot. Comes with a soldering iron and the hot air gun. Also, many times these will have solder suction, so you can suck solder off. So anyway, super useful device, absolute must if you're going to be doing surface mount soldering. All right, so let's turn that off right there. And this brand, Xtronic, is excellent. It's a low-cost brand, and nothing wrong with it. Works great. So now, again, when we're soldering, we might be able to solder everything piece by piece, component by component. All right, and like for example, if we take a look at this circuit right here, there's a lot of parts that go on there. This is all through hole in this example. But another way that we solder things together is we might put all the parts in here and one by one solder them with a soldering iron or this hot air. We could do it like that. But another way is we use what's called a reflow oven. And we put all the parts in, and then typically we put all the parts in with what's called solder paste. And solder paste is kind of a paste that has solder suspended inside of it along with some flux. And then we just put the parts on, and then we'll put it inside of a reflow oven, and this is actually an oven that heats up and melts the parts down, melts the solder and melts it all down. So imagine if this was all surface mount mostly, we'd put all these surface mount parts on here and then use this reflow oven. So let's take a look at that. Okay, so this is one of my favorite devices. So this is a Chinese reflow oven. And if you look online, you can find on Instructables and different websites, people will make reflow ovens out of toaster ovens, and then with maybe some control to control the temperature. You can do all that, but frankly, they don't cost that much. This was $200 or $300, and frankly, if I'm going to spend 6 to 10 hours building something, I'd rather just buy it and get a good one. So what is this thing? So what it is again, say we have our circuit board, and we would put solder paste all over this. And what's solder paste? I'll show you when we go back to the other bench. But it's just a paste with suspended solder inside of it. And then we would put all the parts down on the circuit board. All right. And then we open this device up, and it's basically an oven, and it's just a very special oven. So we'd very carefully put the printed circuit board with the solder paste, with all the components on there, and we would push it inside. And then what we do is we go and we set up the reflow oven. And so it's got Chinese here. You have to be careful but which button you press. But F3, I believe, selects the different profiles. So when we press F3, we go into these different profiles. Now, depending on the kind of solder that you're using and the components that you're placing down, this is a heating profile. And this is minutes in the bottom axis and temperature in Celsius in the y-axis. And so you can see that the curvature of this, so basically it ramps up and it kind of stabilizes, then it ramps up and then it kind of falls down. That's one profile or soldering profile. And we can go forward here or backwards, so let's go look at some other ones. There's another one, there's another one. and so forth, and each has kind of different properties, or you can make a custom one yourself. All right, so typically I will use like this Wave 3. And when you go to solder something, you'll look at the chip manufacturer, you'll look at the various chips you have, and you'll look at what their recommended soldering profiles are. And what you want to try to do is, because you might have 20, 50, 100,000 different components on a printed circuit board, so you have to make everyone happy at the same time. So you want to use a profile that's not going to damage anything, but it's going to solder everything down, and it's also going to be consistent with the kind of solder that you have. Anyway, once we've selected the profile that we like, we would go and press F4, and this is a little touchy. It goes to Chinese and then back, so you got to be careful. Now it's programmed in, it's selected which profile we want to use, and then we say F1 on this particular model. And then we say press F1, and then it's actually heating up, and this lamp means there's an infrared lamp in there, and then there's also a fan. And then now it's going to start following this curve. And in 7 minutes, our circuit would be soldered. That would be it. In 7 minutes, we let it cool off. We open up the drawer. Things all done. So we just press S for stop, assume it would all be done. We open this up, and we would have a soldered board. And then we just take the board out, of course not with our hands because it'd still be hot. All right, with the gloves or something, and then we would pick our board up, and sure enough, it would be all completely done. That is what a reflow oven is, and that's a very, very useful device, another soldering kind of device that you need inside of your lab. All right, so very useful. So let's go ahead and let's turn that off. All right, and now let's go back to the bench, and let's do some soldering and some wire wrapping and some other things. Okay, we're back here on the bench. So the first thing that I'd like to do is we're going to look at soldering, and we're going to look at wire wrapping, and we're going to look at building something. We're actually going to build something. So this will be a lot of fun. So the first thing that I want to do here is maybe take something apart so that you can kind of see what is in here. So I said, so let's get our soldering iron. We got our cold iron here, so I'm going to be careful. I don't want to burn myself. So here's our cold iron right here, and I told you that this tip is removable, and so I just want to show you that. So you can see here, there's that tip on the zoomed in camera, and then there's that little ring there, all right, and we can just remove that. So if we get a tool here, and we're going to look at tools again in a second here. So get our tool, and let's just go ahead and take this thing off. So now a wrench actually would fit on this, and it's probably better than grabbing onto this because over time you're going to strip it, but it'll be okay this just a couple times. We're not going to do too much damage. So we'll pull back the sheathing a little bit. We're going to grab it, and we're just going to break it loose, and it's broken loose. And now since I'm doing this cold, I'm going to touch it with my hands. All right, and then we do that. All right, and then this comes off. And then here is our soldering tip, and we take that off, and you see that. And this white thing is the heating element. Let's look at it under the zoom camera. There we go, there's a heating element, and here's the tip that we just removed, all right? And now we could replace the tip with any other tip for depending on the kind of soldering that we want to do, all right? So for example, we could put this down, all right? And let's put this down here on the table. Okay, so here are a bag of tips, and they may or may not be for this particular soldering iron, but we'll just take a look for fun and just show you. So we have all these different tips, and then depending on what I'm going to be soldering, right, I can use one of these tips, okay? So for example, right now we have this tip here that's pretty big, but maybe I want to do something that's smaller, or maybe has maybe bigger, maybe this big blunt tip right here, right? This big kind of wedge, all right? So anyway, we would find the tip that we want, and then we would go ahead to the soldering iron, and then we could just replace it, put it right back on there, okay? And it does look like it's this model, all right? And then we just screw it back on. So just like that, carefully, and then we'd screw this back on, like so, and then we would tighten it with our pliers there. Now in this case right here, see how it's not holding here, so this is the wrong kind of tip for this particular model soldering iron, so this probably goes to the other soldering iron. All right, so but anyway, that is the idea of it and what you would do with these tips. So we'll put on the previous tip there and leave it at that. So we'll put this back on and solder, turn this soldering ring here, get it nice and tight, all right, and put that back, and then we've got our soldering iron. So anyway, that just kind of shows you the flexibility of these soldering irons and you know, kind of how they kind of go apart. All right. Okay, so now let's put this away. All right, so now what I want to do is I want to show you kind of a couple tools, and then we are going to actually get into some soldering, which, like I said, is not a big part of this course at all, but still it's going to be something fun to do and to learn how to get good at. So let's go ahead and give that a try. All right, so the first thing that I want to talk about real quick again, and is that you know, tools. So again, wire cutters. These are wire cutters and strippers. So they cut here and they strip here. All right. So you know, you've seen us use those maybe a few times, but again, say if we had a piece of wire, we can cut the wire right there. All right, and then we can strip the wire by placing it in one of these holes, whatever we feel the diameter is right to get the insulation off, but not cut through the wire. And again, there's techniques to all this, so I like wrapping my fingers sometimes, and then there it goes, nice, and we got that, and we have our nice wire, and then we can strip this side off here. So now we got a short wire and a long wire. All right, and again, you know, there's a technique to this. You get good at it after a while. All right, so and again, you know, keep a garbage close. We have some needle nose pliers. They're just called needle nose because of these needle noses. All right, needle nose pliers, very useful. And then we can just have some other cutters, and then you can have all kinds of variations of things. But get a nice little kit of electronic tools to make your life easier. All right, and I'm going to show you a couple other things in a minute once we get to it. All right, so let's take a look at the the wire wrapping stuff, because that's kind of interesting. So let's go look at that again. All right, so I'm going to show you a couple different things here. And all right, so for example, these boards right here, these would be good for wire wrapping. All right, so we could wire wrap something with this. Now, this can be soldered in as well, so we could use this for soldering or wire wrapping, and you know, depending on how we want to connect things. This is a good board because we can solder components to it, and then either wire them point to point with pieces of wire that we solder, or wire wrap them. All right, this board right here, this is called perf board. It's very simple, it's very cheap. It has no metal, it has no copper, and again, you could use this for wire wrapping, but not so much for soldering. It'd be difficult because you can't really, the components, you can put them in here, right? So, you know, there's no reason you can't take a diode, for example, and put it inside here. No problem, works, that works fine. And then on the other side, you have the wires, but you can't anchor them to the board. So you could, you know, go ahead and you can do point-to-point wiring, and we could put another component here and solder, and then we could actually use pieces of wire to solder, right? You know, but you're not anchoring anything to the board, okay? So whereas in this case, with this kind of material, right, that has these, there's metal and there's copper, all right, and the board is laminated, we can take our part. Okay, now it's getting kind of bent up. Now remember, we don't like that. So we're going to take our pliers and we're going to straighten this thing out. We'll take our needle nose and straighten this thing out. Okay, there we go. All right, and then we put it in here. All right, and now what's nice about this is we can solder this on the back. We can solder and anchor down, and then now we don't have to worry about it pulling out. Now another thing, another little trick, you see this component here is not going in all the way, right? So, you know, you can nudge it in, maybe put it in some wider things, and then you can use the pliers. That's another use for these pliers. And with one thumb on the back of it, gently pull it through just a little bit. There you go. All right, and then grab it here, pull it through, and then bend, and so now that part is not going to come out. It's kind of stuck there, and now we can solder it and do whatever we need to do, and it's nice and flush on the front side. Okay, so that's kind of you know, how we might put something in there, and then we could either point-to-point solder it with wire, or we could wire wrap it. All right, so now let's talk about the wire wrapping stuff a little bit, because this is really interesting. All right. And then here's another example of off-the-shelf a kind of perf board, and this is again got the solder areas on it, the copper that you can solder to, And you know, this company's probably out of business. I've probably, you know, I've got hundreds of these boards and boxes, and I've bought them. Well, at least internet was around, right? It says www, right, dot Twin Industries. I think this is probably still around. But anyway, so anyway, you would buy these, and maybe I'm going to build a big board, and then I would start with something like this, right? So, but we're going to use these little boards for our what we're going to do today in this little experiment that we're going to do. Okay, all right. So let's put those over there for now. Okay, and so now what I want to look at is I actually want to look at this wire wrapping stuff. So first thing, let's put this back down here, give the camera something to lock onto. Okay, so we've got our wire wrapping tool here, and this is OK Industries, this WSU30, and these are, you know, these are not cheap. They're like $15 to $30 for this tiny little thing because it's very precision made, and it has to have very tight tolerances because the wire wrap wire is so small. So let's take a look at it under the zoom camera so you can kind of see some of the features of it so I can kind of show you. And before we do that though, what I want to do is this is actually wire wrapping wire. Hopefully the camera can get on it there. So this is yellow and it's 30 gauge. And then here's, for example, is orange. Again, this is 30 gauge. And then here's, what is this, purple. And again, 30 gauge. So the gauge, remember, is the thickness, the diameter of the wire. And in a moment, we'll go on the computer, and I want to just show you that a little bit so you just have seen it one time in your lifetime if you haven't ever heard of wire gauge or have a feeling for it. Anyway, so this is the kind of wire that we're going to use. So what I'm going to do is I'm just going to lop off a little piece of this right now. All right. And I'm going to cut that with my cutters here. So I have that, and we'll just put these back over here. All right. And this is actually what's going to go into the tip of the wire wrapping tool. All right, so let's go take a look at the zoom camera and see what I'm talking about. All right, so here's the wire wrapping tool, and a couple features that are important here is in the middle here you see this little notch. This is a cutting notch. All right, so this is what's used to strip the insulation off of this wire. Now, this camera doesn't do this justice, but I assure you this is small. This is, you know, very small. 30 gauge wire is very small, and I'll tell you how small once we go on the computer and we'll look it up for its diameter. We can measure it also, and we're going to do that. Anyway, but let's go back to this tool. So the tool has three different things. One is to strip the wire. So we cut the wire with something else. It doesn't have a cutter, so we got to cut the wire with something else. So there's our piece of wire that we might want to connect from one point to another on a circuit board. All right, then the tool itself has two different ends. All right, and again, this is going to be very challenging to get this to focus on here, but I'm going to try and see what we can do. Okay, so this end right here is the end that is used to do the wire wrapping, and it's a bit hard to see, and I really want to try and show you this. So let's see if we can get the light here right. All right, there you go. So there's a hole in there in the middle, all right, and then there's another hole, a tiny hole. The hole in the middle is going to go on the post of the device or the IC or the socket that you're wire wrapping. The other hole is where we put the actual wire wrapping wire, all right, and so then we twist it around it, okay. All right, so how that works is like this. So the first thing we do is we take our wire wrapping wire and then we're going to remove some of this insulation. All right, so let's go here and hold the tool like this. And this takes a while to get good at. So we're going to go like that, and you get a feel for how many wraps this is going to wrap around some diameter post. Okay, so I'm going to put my finger here about there, and then I hold it, and I pull it down. Okay, now it's engaged in that cutting area. All right, and then I'm going to kind of rotate it, and I'm going to pull this way while pulling this way, not too hard. I don't want to break the wire because it will break, it's so thin. And then I'm just going to gently pull, and there we go. And no metal shaving, so I didn't cut the wire. All right, so you can see how thin this wire is. All right, now that we have a wire, now we're going to go, and again, let me see if I can get this camera to cooperate with us. This is so small. All right, and then there's two holes in here. One's going to go in the socket, and the wire is going to go in one of them. So here we go. So I'm going to put the wire in here. All right, and there it goes. And now it's just engaged in the little side hole, and it goes out down the slot. And then we push it not all the way in, just back it out just a little bit, and we're going to fold it like this. All right, we're going to fold it like that. Now this is ready to wrap, to do a wire wrap. So what do we wire wrap around? All right, well, any post of any device that's inside of our circuit board. So let's just hold that there for a second. It'll survive. And let's go ahead and let's get, so here's a piece of circuit board, right? Perf board with the soldering pads on them. And now, so what would we, build? So maybe we've got some components, all right? But say we want to have a bunch of chips. What would we put the chips into? These are what we put the chips into, and these are sockets. And you can see they're all different kinds of sizes, and big, small, and whatever. So here's one right here. And let's just pull that out. And these are wire wrapping sockets. They're specifically made for wire wrapping. That's why they have these really long posts. So if you count 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, this is a 14 pin socket. So this is a very common TTL IC size, has 14 pins. Okay, and then the IC would go inside of here, right? So first we put this in our board like this. So, and we're just going to put this in here randomly. Now, see how it's just kind of sitting in there right now? Right? Just sitting in there. That's not going to do too good. That's why we solder it. So we would put it in here, and then we would solder it down maybe to the two corners. That corner there, and then the other opposing corner. Now it's not going to go anywhere. And we could solder all of them if we want, but those two would do to keep it still because it's going to be all over the place. But let's pretend we did that. All right. And now I'm going to wire wrap one of these pins. Okay, so I'm going to hold this. All right, and then I'm going to put this in here. All right, now I've got that, and this is a process. All right, let's get the camera and get the lighting here. Okay, and now I'm going to kind of hold this very carefully. I'm going to start twisting this around, twisting, and as it twists, it's kind of riding up, and I'm going to push down a little bit, tighten it, twisting, like that, and then I pull it off when I feel like it's done, and then amazingly, take a look here. And this is pretty cool. So I'm going to zoom in for you. Let's see if we can get that to focus. And I'll try and hold it really still. How cool is that? So there's like 1, 2, 3, 4, probably 8 or 9 turns of wire on there. So we just wire wrapped that point. Let's say that this connection had to go to maybe the third pin on the other side. So what I would do is I would first pull this around to kind of get a feel for how long I needed it. And there's the third pin. So I kind of do that. And then I kind of might pinch it right here. So that's kind of the length I need for the insulation. And then I'm going to have to cut this. So I'm going to cut it. And I'm going to probably cut it, right about here. Okay. Now it's cut. Now I'm going to take my wire wrapping tool again. And I'm going to put this in here. And I'm going to take off this insulation up to my point here. Right. Take it off. There it goes. Now I'm going to put use the tool here, and I'm going to put this into this little hole here. And I'm actually doing this through the camera, so this is not the easiest thing. Okay, and then we said we want to do it to the third pin. So we could come in the middle, or we could come back. We could come around because it's a little bit long. So we'll do that. We'll go around this way. We got it on the third pin. All right, and again we just get a good angle on it. Careful. Turn. And then we hold it and push it down, tighten it all up, and look at that. Very nice. So now no solder, and we have this nice connection here, all right? And that's going to work. And now the nice thing about it is we can build the whole board like this, test it, verify it, then we can start soldering all these actual wire wrap connections down and make them permanent. Now, we don't want this here because we want to use this board maybe for something else. So now we want to get rid of these connections. So how do you undo these things? So this side of the tool, the short side of the tool, right? If you look at its end here, and again, this is very hard to see with the camera. I'm going to tilt this up and see if I can get this for you. Okay, you see that? See how it's got that flat side in there? There's a flat side. So what's going to happen is that flat side is going to catch the wire, the tip of the wire, and it's going to start untwirling it. All right. So anyway, we put it on one of these. All right. And then we just hold some pressure, and then we just go counterclockwise, and there it goes, and it's off. All right. and that's it. So if I zoom this out just a little bit, and then if I get something, get my needle nose pliers here, or my fingers, and just pull it out, there we go, and that's that. And then that wire is off there. And then I could use the tool, or I can sit here and untwirl if I want. But you know, what happens if you start doing this, you might actually break it on there, and then you might have to, you know, go in there and get it. So that's what the tool is for. It just makes it easier. And then there comes our socket, and we can reuse everything, and then that's that. So that is wire wrapping. Okay, so that's wire wrapping, right? Now that we see that, let's go ahead and let's take a look at some soldering stuff. All right, so let's do a little bit of soldering here and see how this goes. All right, so the first thing is to solder, we're going to need a few different things. So one of them is we want to solder on something. So right now I've got this blue sheet here, and it's making it very hard for the camera to focus. And so I think what I'm going to do is I'm just going to remove this, and we're going to come back to our grid here, which is much easier. I just don't want to damage our surface here. All right, and then what we're going to do is we're going to put something down that we can solder on. And so typically you could, again, you could put something down that would protect your table or whatever, which I highly recommend. And so we're just going to put down this piece of paper here. And again, hopefully it can focus on this paper a little bit. All right, so we're going to do a little bit of soldering here. And so let's back out a little bit. And then this is just like a piece of cardboard paper that I solder on a lot, and I can burn it. I don't really care. It doesn't start on fire. All right. And so I've got the soldering iron here. And so there it is right there. And I'm just going to put this, I'll just put this right here so you can kind of keep an eye on it. All right. And so a couple things. So first, here are some solders. All right. So here are a couple solders, and some things about the solder. If you look at this, all right, first this manufacturer is Kester here, and then on the solder you can see the percentages. So right here it says this is 63% tin and 37% lead. All right, so it's 63-37, and then this number right here is the diameter, so this is 31 thousandths of an inch. All right, and then again here's another one. This one is so, and you can see this one is pretty thick, and that's 31 thousandths of an inch. And if we were to get our calipers and we were to measure this, we would get, and there you go, it's exactly what it should be. I'm crushing it, right? I can crush it because it's soft, all right? Okay, and then this is when you want to do finer work, and what's this? This is again 63-37, and this has got you know, flux in it as well, another Kester, and this one is, let's see, 10 thousandths. All right, so this is so small and it's so soft, I probably won't even be able to measure it. It'll just crush, but we'll give it a try. All right, oh, it did. There you go. So 10, 11 thousandths, exactly as we would expect. Okay, so we've got these solders right here, so I'm going to use the thicker solder. Now this solder, I believe this one may have flux in it, may not. Yep, it does, rosin core. So it says rosin core, so this is good. So this does have flux in it, but I always like using extra flux as well. So let me show you a couple of those. All right, and one of the manufacturers of these is MG Chemicals. There's many manufacturers. This is no clean flux. What this means is you use it, you solder, you don't have to clean anything off. It's not going to erode anything or cause any damage. Normally, solder flux is acidic, and it's supposed to be because it cleans everything, but if you leave it on there, it can cause damage. So you always want to clean everything after you do your soldering. And here's another one, rosin flux, but this one is not, you have to clean after this. All right, and there's all kinds of fluxes that you can use. Again, these are very, dangerous chemicals. You don't want to breathe them, you don't want to drink them, you don't want to eat them, and you want to have everything ventilated. So you might have a ventilation system or whatever if you're going to, do soldering. And I do. I have a ventilation system running right now, and there's fans going and everything, cleaning, keeping the air clean. Okay, so we've got our solder. And I'm just going to show you a couple little tools here of the trade. So see this is just a bunch. It's a metal sponge basically. And what happens is as you solder, this soldering tip is going to get very dirty and junky and get you know, carbon on it and all kinds of yucky stuff. So as you solder, you'll see people kind of do some soldering, and then they'll clean the tip off on the sponge. And then this is another way to clean things. So we'll take some fresh solder here, and we're actually going to put it on this tip. And you can see that smoke, right? That is the flux burning. It's not the metal burning. All right, and I don't want to breathe this. And you can see the smoke's going, right, because I have ventilation. All right, so what I'll do right there is I'll just put it right in here, right in there. And my goal is to make this tip real nice. So see how nice that tip is? We got nice metal on that tip, looks real good. I'm going to show it to you on the zoomed in camera. Let's see if we can get it to do it for us. There we go. So that tip is real nice. Okay, now let's actually do a close-up of putting solder so you can kind of see that. So now typically soldering is we could do a whole class just on soldering. So what you're going to do is whatever we're going to solder, we're going to apply the heat to the thing that we're going to solder. We might even put some flux into it. And then slowly we're going to press the solder into it. Now a lot of times what we'll also do is kind of put a little bit of solder on the soldering iron and then do that so that the soldering iron's already got some solder on it, right? And but other times what we'll do is we'll just put the soldering iron on the joint, and then we'll slowly start pushing the solder into the soldering iron and the joint all simultaneously until it starts liquefying and flowing. And then it's an art form, and you'll be able to kind of gauge the surface tension of the solder as all the flux burnt away and all that. And it takes a while to get good at soldering. I'm going to tell you right now. So be patient with it. Just don't burn yourself. Just be careful. Wear your goggles. All right. So we are going to basically build a circuit, and we are going to solder and wire wrap it together. So that's our goal right now. We're going to build a very simple circuit and solder and wire wrap it together. All right, so we're just going to move this out of the way for a minute, okay, and give ourselves some space here. And when you're soldering, you want to be super, super careful because it is messy and things are hot. You can drill holes and things real easy. All right, so we got our workspace here, okay. And let's go ahead and let's get our solderless breadboard. Let's zoom in a little bit so you can see what's going on here. So now this is getting fun because now we know enough to be able to build the circuits, right? And now we're going to construct the circuit in a couple different ways. So the circuit that I want to build, let's go take a look at the computer and let's draw it out on the computer and do a little bit of math, and then we're going to come back here. So let's go back to the computer, meet me there. Okay, so we're at the computer here, and let's draw the circuit that we want to construct, all right? So all we're going to do is solder together, build, wire wrap, an LED, a resistor, and a power source. Okay, so in the abstract, what we want is we're going to have a battery. We're going to have a battery. All right, let me draw our little symbol for a battery here. So here's a battery, and this is going to be plus to minus. So we're actually going to use a 9-volt battery, and then we're going to have a resistor, and that looks like a heartbeat. Let's make a better resistor. All right, sort of. All right, and then we're going to have an LED and make our symbol for our LED. And then going down, and then we're going to close this off. And then we put a couple little arrows going outward. And this is the positive side and the negative side. What do we call this again? This is called the anode. And this is called the cathode. Cathode. All right, and when we turn this thing on, we're going to call this R, and this is a current limiter, and we're going to actually set this 220 ohms. I kind of tried and is nice, and we're going to get a current. Let's actually make that current in a different color, and then we're going to get a current like this. All right, and that current, we're just going to call that I. We could call it I sub R, I sub LED. And what is that current going to be? Remember, we've got V equals I times R. What's that? That's Ohm's law, right? Ohm's law, and we want to compute I. So it's V, which is 9 volts, over R, which is 220. This will be the current limit, right? Once the LED turns on, it's going to drop some voltage. It's going to change that a little bit and be a less current, but this tells us our limit. So we use our calculator, 9 divided by 220, and then we convert that. That's going to be 40 milliamperes. So 40 milliamperes. And it'll be less because the LED, once it turns on, it's going to have some dynamic resistance. It's going to drop that down. But anyway, 40 milliamps, we're going to drive this thing pretty hard because we're going to put this 9-volt battery here. And by 9-volt battery, I mean one of these prismatic 9-volt batteries. And just for fun, that's what we're going to kind of hook up here. And they look like this, right? Like that. That's what the 9-volt looks like, and we're going to use one of those. This is the circuit that we're going to build, all right? So power source, resistor, anode, cathode into our LED. Now, one problem that we're going to have is we're going to use a through-hole LED, we're going to use a through-hole resistor, but how are we going to get this battery connected? So we'll take a look on the bench to see exactly how we're going to do that, okay? So let's go take a look at that and go back to the bench. So let's go ahead and let's build our circuit, a model of our circuit that we're going to actually construct. All right, so let's start there. All right, so what do we need? We need an LED, we need a resistor, we need some wire. All right, let's get our wire cutters and whatnot so we have all the tools that we need here. Okay, so let's get our power supply. I've got our bench power supply set for 9 volts, and I'm just going to plug that in right now. And the power supply is off, the output enable is off, and that's why we like that output enable, so we can turn it on and off. Okay, so we've got an LED here. All right, we got a resistor, our 220, so we're going to go directly from the top rail down. All right, and we're making a model of what we're going to make. So we're making a model, and this is going to be a very easy model. All right, and here's the anode, down, and then we got the cathode, which is going to go to ground. So we're going to need a piece of wire. Let's get a piece of wire from our little box here. So I've got that. So now I've got a little piece of wire, and I'm going to connect this down to ground. Okie dokie. All right, so there's our circuit exactly as we modeled it. Let's turn the power on and see what happens. And sure enough, the LED turns on. Let's do a test. Let's verify what our theoretical current should be. So we're thinking it's going to be under 40 milliamps. So we'll put our meter into a volt mode here. And let's see, we'll just get this in a way so you can see things again. All right, so we've got our meter in a volt mode. Okay, so let's measure the voltage across the resistor. We could put it in amp mode and put it in line, but it's just a kind of a pain. So let's measure the voltage across the resistor. There we go. All right, 6.55 volts. All right, 6.55 volts. All right, so let's do a calculation. So V equals I times R, I equals V divided by R, so 6.55 divided by R, which is 220, plus or minus the tolerance of that resistor, which is 5%. Just always keep that in mind. And we get this value right here, and move the decimal with the engineering mode, and we have 30 milliamps. Can you see that? 30 instead of the 40. All right, so that's good. 30, that's nice. It's not going to burn out that LED. It's going to run good. Okay, so we're happy with that. So now we need to start building this thing together. All right, so now here's where the fun part comes. So we're going to put something together. So we're going to need a circuit board to build this on. All right, we're not going to use this because we can't solder to it. So that's not going to happen. All right, what we want to use is something we can solder to. So we're going to use this right here. Now this is a big piece of circuitry, and we got this teeny tiny little circuit here that we're going to hook up. And I want to keep this here so you can kind of see it, and so that's our model. Now, one thing is that another thing we need to do is we want to power it with a 9-volt battery. So how are we going to do that, right? So let's think about it. So first, let's turn this power off, okay? And so what we're going to need to do is we're going to need to fabricate a connector. So we got to go into the connector fabrication business now, all right? And so let's see if we can find, so here is a bunch of cables that I've already fabricated just to show you. All right, so sometimes what I'll do is I'll put a male end on them, right? And then so that could go in there, right? Now what I want here is I want to be able to unplug this connector in and out. So I don't want to leave it connected there, okay? So now we've got, so we found what we need. So here's a 9-volt battery connector, and then we've got leads on it here, and then here's a black one here, all right? Both the same, just different color. What I like this though, because it's got this nice little plastic retainer, and so when I connect this to this, that's pretty cool. This is a rechargeable 9-volt battery. This is super cool. All right, so I like that. Let's use this one. And I like this so much I don't want to damage it. All right, so we want to make sure that we can reuse it. So we're going to have to put a connector on it, right? So we can either put a male or a female connector, and then we can put the opposite into the printed circuit board. So here's like a female connector. So we could put a female connector on here or a male connector. All right, and then that can go into the board. So we need to think about that. All right, so let's put this away. Okay, so we got our connector here. We got our clip, battery clip. Now the first thing we need to do is we need to expose these wires. Let's zoom in a little bit here. All right, so I'm going to get my wire cutters. All right, and very gingerly, I don't want to cut through this and break it, so I'm going to go into the smallest hole here for the smallest wire, and I'm going to kind of look what I'm doing here, and just I'm going to kind of feel this out, kind of bite it down, okay, and that might be a little bit too small. Let me try the second. Yeah, I think the second size will do for us. And these have numbers on it which say the gauge of the wire, but I don't really know the gauge of the wire. I can only guesstimate it. And so, but the second is about right. Now, you see me biting down on it a little bit. I'm not just punching down on it. I'm just easing it so that I can get it without losing anything. All right, and we throw those wires away. So now we have our two wires. Okay, so the first thing you're going to do is I want you to twist these wires. All right, you can twist them either way, but typically you'll twist it depending on how you want to look at this, right? You can look at it like this or like this, but you can twist them towards you, twist them away. I tend to twist away from me like this, all right? And again, twisting these, and then these are stranded wires, so these have strands, so these wires are stranded. And we can look at that on the zoomed camera if we like. And very carefully, you can see all those little strands I just twisted around. All right. So now what we're going to do is we are going to tin the wires. We're going to tin these wires to make them strong. All right. So I'm going to need my soldering iron. So I'm going to bring down my little soldering surface here so we don't damage too much. Bring our soldering surface down here. Here's our wires. All right. And then I'm going to hold these wires down with something. Right, and then you can get, all kinds of tools. You can get clips and devices to hold things to help you work and all that. You can do all that, and that's all fine and dandy. But we're just going to kind of hold this right here and see if we can get the camera to lock in, and it's not cooperating at that distance. So let's see if it cooperates there. Okay. All right, so I've got my soldering iron. All right, and I want you to see what's going on here. All right, and I've got my little thing here, so I'm kind of cleaning that. Let's back out some more. This is just not going to work. Okay, there we go. All right, so got that. All right, now I could put some flux on these two guys, but I'm just going to hope that there's enough flux in here. So first thing I'm going to do is I'm going to tin the soldering iron itself, which I just did, and can get that hot and get that going. And then now I'm just going to solder these. So what I'm going to do is I'm going to kind of put the soldering iron behind it and then push the solder into it. All right, here we go. And you can see I'm kind of going up, going down. I'm done. Okay, I'm going to go do this one. And again, there's, this is like art, and you'll get good at it after a while. At first, you'll be horrible at it. All right, and then I'm going to clean it on the sponge. Cleaning that on the sponge over there so the soldering iron's nice and clean. Okay, now, so we look at this, and now this is nice and tinned. Let's zoom in a little bit here. Nice and tinned. All right, let's move this stuff away. Okay, get back to our little zone here. Okay, now we've got our battery clips, so black is going to go to ground. I'm going to just very carefully put that in there because we're going to need these leads. Good. And we'll put this in here, into the plus, and if we have a nice charged battery here, all right, if we have a nicely charged battery, when I plug this thing in, this thing should turn on just like it did with the power supply. And there it goes. So that works, right? So that's the circuit that we want to build. So we want to build a battery operated circuit. Okay, now, so now what we're going to need is we are going to need something to build it on. So we're going to build this exact circuit. So I've got another copy of the components right here so we can keep an eye on what we're building, all right? Other than this clip, which we're going to pull this clip out and use. We're going to use this right here, all right, to build this on. So obviously we don't need a whole lot of space, okay? So we need very, very little space. We need enough to put the connector for the battery. So let's talk about this real quick and let's make a decision on what we're going to do here, okay? So we've got to do a little mechanical design here and figure out what we're going to do. All right, so I have countless headers here. So I've got boxes and boxes of headers, and these are called headers. And there's male headers, there's female headers, there's all kinds of things. So here's a female header, for example. And now the only problem with this is if I were to put it in here, it's just not going far enough to be wire wrapped, right? So maybe we could put this, so we could put a female header on here, right? We could connect that. We'd have to cut it, right? So we got to cut it. And then we could put one of these male headers. We could cut off two of those posts. We could put that through the PCB, and then we could wire wrap on that. We're going to have to still make this a little bit longer. So do we have any longer ones? Okay, so here's some longer guys, except this is on a two header right here. So what we can do is we can pull those out, and we can, yeah, so we're just going to do that. Okay, so what we're going to do first is we are going to carefully, we are going to pull out and cut. All right, so we're going to cut. First, what I'm going to do is I'm actually going to pull these two guys out. All right, so I'm going to pull these out right here. Pull out that one, and I'm just going to put that in there. I'm going to pull out that one and just put that in there. Now I'm going to pull out these long ones because I want these, and pull one out and pull the other out. Okay, so I got those out. Now what I'm going to do is I'm going to actually insert them in here. And be careful when you're doing this stuff. You will impale yourself. So if you push hard and nothing happens, you're binding. So be careful, please. All right, so I'm going to put that right in there. So that kind of goes in there. And then the same thing here. Put this one here. And so those are going in there pretty easily. All right, then I'm going to cut this right here. Careful. Okay, so now I got that. All right, so now I'm kind of done with this thing here. All right, so now we need to cut two of these off, and we're going to use those to connect our clip to. All right, so this is a little bit more difficult. All right, again, make sure you have your eyewear on because things are going to go flying. All right, so what I'm going to do is I'm going to use these cutters, and I'm going to cut into this, except I'm not going to cut right at the seam where the 2 is. I'm going to kind of go where the 3rd pin is, because as I crush through this, I'm going to mechanically destroy everything, and I don't want to damage these 2 right here, so I want to kind of go over a little bit more, and I'm going to, destroy this 3rd one, but I don't care. All right, so ready? I got it on there. I'm, nice and straight and flush. Do it like you mean it, and I'm going to cover it with my fingers so it doesn't go flying. 1, 2, 3. Okay, there it is. Okay, I cut right through it. And then you can see there's a little bit of it left over. Let's go to the zoomed camera so you can see what I'm talking about. So you can see that. We got our nice thing there, and then we've just got this. We got our nice 2 connectors there. We could cut this off or sand this off. So what we're going to do is we're just going to take these cutters right here, and we're just going to cut a little bit of this off, just a little bit of it off, and kind of make that a little bit nicer. And this is why you want to have different tools so you can kind of do this. So now in this case right here, what we might want to do is just sand that a little bit, right, with a file, okay, just to make that nicer. So if we have a file, and let me grab a file. So let me get a file here. And again, we're really rushing here to try and, keep things so that we don't take forever, but I want you to kind of do things neat. All right, so we got our little file here, and all I'm going to do is just kind of file this down. All right, and we could have used a file, we could have used a sandpaper, a lot of different things. Just file that down a little bit. All right, and you see how that's flattening out a little bit, and that's a little bit better. Just makes it a little bit nicer. Okay, and then we'll chamfer this top here a little bit. Okay, so now I'm kind of happy with that. So now we're going to solder these 2 pins to our battery clip. All right, we'll put our file away. Okay, now before we do that soldering, what I want to show you, so now we can put all this away. We're done with the sockets and the headers and all that, so we can put that away, trying to keep things clean. Okay, now what I want to show you here is that so we got this guy right here, and we're going to the goal here is to solder this onto here, right? That's what we're trying to do here, right? We want to solder it on, but they're going to be so close, these things might touch each other. Now, you'll notice, and if I can find where the box is of the other samples, which probably just disappeared into hyperspace someplace, and this stuff happens all the time. Where did it go? Where did it go? Where did it go? All right, let me find another example so I can kind of show you what I'm talking about. Now, what I wanted to show you is when you make one of these cables, see here how I soldered these 2 wires onto the switch, and then I put this rubber stuff on here. Now, you may or may not have ever seen this. This is shrink tubing. All right, and so that's one example of shrink tubing. Here's another example. So this red and black is shrink tubing. Now, shrink tubing is a kind of tubing that when you apply heat, its diameter changes, and it's rubber, and it can be used for insulation. So shrink tubing, you can buy it at the store, and for example, here's a box of it here. All right, let me zoom out so you can see this. And a box of shrink tubing here, and this is a Tektron 899 whatever. All right, and you open this up, and what's in here are all these different sizes and colors of shrink tubing. And so you pick something that's bigger than what you're putting it on, you know, like this size or whatever, but not too much bigger. And then you know it'll shrink to about half that size when you apply heat. All right. So what we're going to do is we want to protect these two leads. So we're going to get, you know, something that we could use. We could use red and black because it's consistent with the colors. So here's a couple pieces. This may be too small and too big. So let's see if we have something else that just is a little bit better. Maybe this green one. The green diameter doesn't look too bad. Maybe we can use that, give that a shot, and then they'll both be green. So we can use this green right here. So what I'm going to do is I'm just going to cut off a, in fact, you know what? Let's use yellow. And okay, so we're going to use yellow, and we're just going to cut it to about this length right here, and this length right here. So I'm just cutting exact same piece times 2. All right, and I'll get this in focus for you in a second. So we can get shrink tubing. All right, so there's the two pieces right here. All right, there's our two pieces that we're going to use. And then the trick is, okay, the trick is this. What you do is you put the shrink tubing on the wire like this, and be careful because I've done this 1,000 times. I solder it and then remember I forgot to put the shrink tubing on it. So you put the shrink tubing here, and remember heat is going to make this shrink. So you put it all the way back. Now what we're going to do is we are going to make our cable here. And so we need our female. We're going to be using this this thing right here, right? Our female. And so we're going to solder these to this, and then we'll pull the shrink tubing on top of it. So now to do this, I'm going to employ, and again, you're going to have to be really good with your hands. You're going to like learn to be an octopus with your hands. But this is a little, you know, helper. And so what we're going to do is we're going to, and this is exactly what this is for jewelry making or electronics or whatever, you know, figure out a good way to kind of put this in here that still exposes those connectors and so that it's good and tight. So I'm going to leave it just like that. All right, so that's good. And then I've got my wires here. And so now these wires are pretty long, so I'm going to cut these about half as long here, or I could fold them over and get a little extra strength there. So I think I'll fold them over. All right, so I'm going to fold that one over, and I'm going to fold this one over. And again, you know, no one really teaches this stuff. How do you build things? And you just got to kind of learn, and it's tough. It's tough to learn. You got to do it by trial and error. All right, so we got these two right here. All right, and now what I want to do is I'm going to tin these. Again, remember the tinning just means putting some solder on it. So we're going to tin these. So we're going to get our solder here, and I'm going to actually just put some solder on the soldering iron because you know I've only got so many hands here, and then I'm going to run it across, and I'm going to put some solder on there. That's nice. Clean the soldering iron. I'm going to go get some more solder and put it on here. There we go. Okay, good. And then I'm going to tin this red one good. Okay, and get that solder to flow across there. Okay, good. All right, so I got those two guys right there, nice. Okay, let's look at the zoomed in camera real quick so you can see that. See that? We just got the solder on there. That's all we're looking for. Now we're going to solder these guys right here. Now, one thing that you might have seen when we were doing some of the pyrotechnics before is we have this alcohol here. So sometimes what I'll do is I may flux something, but you know, I'll also kind of clean it. And to do that, we're going to just clean it with some alcohol. And so typically you can use one of these little canisters here. And basically it's just a canister, and as you push down on the top, fluid will come out. And I don't want to squirt the camera, but there you go. And then you can just put, you know, a Q-tip in there like that. That's all I'm going to do. And I just want to clean this, just clean this a little bit, you know, just do that. And then if I wanted, I could go and dip it in this flux right here. And I probably should, but I don't have anything to clean it right now. So we're just going to do it like this. So let's just solder this together, and let's see what happens. Okay, so the first thing that we're going to do, so let's zoom in a little bit so you can see a little bit better, hopefully. Okay, and so we're going to tin, we want to tin the this connector too. Now remember, this is plastic and metal connected to plastic. It's going to melt if we do this for too long. All right, so be careful. And we're just going to get that going. I got some on there. I got some on there. Okay, good to go. All right, so now I'm going to basically got to do this, quickly. All right, so let's confirm we got our shrink wrap on there. Good. All right, so I'm going to do the first one. I'm going to get my solder ready, and this rosin, this flux is burning away every second. So you got to do this quick. So I'm going to just kind of get some solder on there. Now remember, everything's already tinned up pretty good, so we don't need much solder. All right, so we're going to go in there very quietly. All right, so that one's good. And holding your breath, being very careful. I'm going to get a little bit more solder. I'm going to try not to burn my table. All right, hopefully you can see this. Yep. Okay, and I'm going to solder this one. Okay, nice. Okay, now there's flux on there, right? And we're going to clean that off. So I'm going to just get some more alcohol here. All right, and then I'm just going to clean this. So I just want to make this nice so that over time this doesn't get all yucky, because this is acidic actually. Okay, there we go. Okay, nice. Now we're going to pull these over here. Pull right on there. How nice is that? And now we need a heat source. Now we could go use our hot air gun and turn that on and do all that, but I don't want to move the camera. So all I'm going to do is I'm going to use a soldering iron. I'm not going to use the tip, but I'm just going to use the barrel, the long part right here, and I'm just going to just kind of touch it. Just kind of touch it. I don't want to touch this plastic. All right, just kind of touch it. And as I do this, it actually, and be very careful, we don't want to touch the plastic there. And very careful, very careful. And we really should do this with the hot air. That would be much better. All right, just touching it with the barrel. And I don't know if you can see it, but it's shrinking. It's shrinking. There it goes, starting to get really shrinky now. Okay, and I'm going to touch it just a little with the, I want to be careful, I don't want to burn it. Okay, and it's almost down to as small as it's going to get. All right, and I think that's good enough for now. All right, and there's our connector. So now we've got our connector. All right, so now we've got kind of all the pieces. So now we're going to go and start putting the circuit together. All right, so let's do that. All right, so we're continuing on with our construction and fabrication, and we're building a printed circuit board with a little tiny circuit on it. And the circuit that we're going to build is something like this. Something like this. We're going to have a 9-volt battery. We're going to have a resistor for a current limiter, and then we're going to have a light emitting diode. Now I've actually decided to add a couple little things to this, and I'm going to show you that in 1 second. But before I do, there was one thing that I wanted to kind of show you last time that we didn't go over, and that's this right here. We were talking about wire gauge and thicknesses of wire and whatnot, and I wanted you to have kind of a feel for this. So now if you just Google a wire gauge or AWG, American wire gauge, then you will find many, many charts and graphs that show this, but the Wikipedia page is not bad. But before we look at that, I want you to take a look at this. And this is just a picture kind of showing some of these gauges, and you can see 0 gauge here on the right, and this is stranded wire, and then 0 gauge, 2 gauge, 6 gauge, and then so on down to 12. Like these 12 gauges, this is what you would find in electrical wiring in your house. Now the gauges that we're using are down at 22, 24, 28, 30 gauge for these these wires that we're using to connect our circuits up. So they're very, very small diameter wires, or have a large gauge number. All right. So now what you can do is, if you want to figure out what the gauge of something is, and then another thing is, if you want to, say for example, you have a current that you want to flow through a wire, you want to know how much current would flow through that wire, or what's the current carrying capacity of the wire, then you can Google something like current carrying capacitor per gauge, and then there are tables that can show you how much current can flow through a wire given a gauge, and if it's copper or silver, gold, or whatever. Typically everything is copper. Okay. But what I wanted you to look at, and there's a formula to figure all this out and so forth, but if you just go down here to the AWG table in the Wikipedia page, for example, and there is all kinds of really cool, colorful versions of this, and like I said, you can Google them. The gauge number is up here on the left, in the left column. So if we just have a gauge that we want to figure out, say like this 22 gauge and 24 gauge, these are 25 thousandths, this is in thousandths of an inch, or 25 mils, and then for 24 gauge it's 20 mils. All right, so if we go to the bench real quick and we were to measure a 22 and 24 gauge wire, we would find that it's 25 thousandths and 20 thousandths. So just real quick, let's go do that, and so we can kind of see that process. We're over here on the bench right now, and on the camera here, you can see I've got two spools of wire, and one of them is 24 gauge, some brown wire here, and then another one is this yellow wire, and we've been using two different versions of the yellow wire. One of them is thicker. This is the thicker 22 gauge, and then most of the time I use 24 gauge like this when I'm using the solderless breadboards because it goes in a lot easier. If I want to have a little bit more current, then I'll use the 22 gauge. But let's measure these. So the first thing that we need to do is sheath off, remove the insulation. So I'm going to use the wire cutters here and strippers and kind of put it in the second notch here, and then see I'm wrapping with my finger to get some leverage on it, and there we go. Very easily it came off. I didn't cut into the wire at all, and that's what you want to make sure you don't do. Okay, so let's turn on this set of calipers here. It's in inches, and let's go and measure this. And we did this on the solder, so this is 25 thousandths, exactly as it should be. So that's 22 gauge. So good. And these calipers that you see me using, you know, you can get really, really good ones that cost a couple $100. You can get some cheaper ones that cost maybe $20, $30, but you get what you pay for. It's a precision instrument, and so this is a very useful instrument when you start doing anything mechanical. All right, and then here's our 24 gauge. So let's strip some of this wire off. Again, I'm kind of picking the second notch here, and again, I kind of wrap it with my finger, get a little leverage, and there it goes very easily. Comes off, and we're looking for this should be about 20 mils. Oh, and there it is, 20 mils. All right, 19, 20 mils. Perfect. All right, so that's just what that American wire gauge thing is all about, and I wanted to make sure that we covered that. All right, so now what we're going to do is we are going to build a circuit. We're going to solder and wire wrap a circuit, and here's what we're doing, this circuit here. And we've got a resistor, an LED, and a wire, and we've got our power source, which ultimately we're going to use a 9-volt battery, and we're going to use this clip, which we've created this female socket here. We've created this female socket, and our intention is to plug the female socket into this male socket, which will then be inside of soldered inside the circuit board. Very cool, and we can switch it either way. So that could be good or bad. So this is non-polarized or non-keyed, and so it could go in either way. So that might not be a good thing, or it might be a good thing if you want to flip the polarity around. All right, so I've been thinking about this, and I thought, you know, let's add a couple features to it to make it more interesting. So since we're going to assemble it, we might as well make it useful, right? This little green LED is not very bright. It's not going to really do much of anything. So then I thought, well, what we could do is we could put two LEDs in parallel. We could put two LEDs in parallel, and let me show you that idea real quick. And we put them in parallel, but we put them reverse, all right? And we'll put them reverse so that when one is on, the other one is off, and vice versa, depending on the polarity of the voltage. Okay, so right now we've got the two LEDs there, and you can see the green one is on. But if I reverse the polarity, then the red one turns on. All right, so that's kind of cool. All right, and let's make sure here. Okay, and this now what's interesting here is this red one. We got to be careful. This is one of the red ones that have so ground is the flat side, but the large pedestal is got the positive anode. So again, usually the flat spot is the cathode. So if you go by that, but I always test it, because on this green one, in this case, the large pedestal is ground and the flat spot is ground as well. So that indicates that. But what I thought was, okay, we could do the two LEDs like that. We could use a bicolor LED, and this means depending on which way you apply current, you can see both pedestals look exactly the same, all right? So there's two LEDs in here actually. So if we put this here, now it's red, so you can see it's red, and then we'll flip it around, and now it is green. So if we were to switch the battery around, we could get that action, but I don't know, it's just not bright enough. So then I thought, what about using a white LED, which is very, very bright? So let's get a white LED in here. So we'll get a white LED. Now look how bright this is. So we'll get a white LED, and that is really bright. So that's like a flashlight. Look at that right in there. So we'll use a white LED in the forward direction, and then we'll put a red LED in the reverse direction, all right, like this. So we'll put two LEDs, and if you put the battery in backwards, then it'll turn red. If you put it in the forward direction, then it'll turn white, okay? All right, so that's what we're going to build, all right? Now I thought, well, let's make it more like a flashlight, so why don't we add a momentary switch to it? All right, so if we want to add a momentary switch, we can add it anywhere we want here in line, but to make it simple, maybe just for the schematic, we can add it right here, for example, and go like this, and we'll put the momentary switch right here. Okay, and there we go. And remember, this is just our model, all right? And now when we press the button, okay, so the LED turns on, and then if the polarity was reversed, the LED, the red one will turn on. Okay, so that's what we're going to build. So let's go back to the computer and let's go to the drawing program and let's kind of draw what we're building here just to make sure we're all on the same page here with our circuit. Okay, so let's do that. Okay, so we're back on the computer here and we see the circuit that we started with here, and so we're just going to make some changes to it. So let's go ahead and let's get the eraser, all right, and erase some stuff here. So the first thing is, let's just kind of erase this anode and cathode notation. We already know what that means. All right, and then we're going to add a switch in here, and the switch can be anywhere that we want. So we're just going to kind of put this, let's just go ahead and we'll put the switch right up here. All right, and then we're going to add another LED. Okay, so first we're going to put the switch, and here's the symbol for a momentary switch. So that's our momentary switch, and we'll call that SW1. All right, and we're still going to use just one LED, one resistor, but we're going to use two LEDs. So now we're going to put another LED here, and we're going to reverse the direction. All right, so that this gets forward biased when the power is in the opposite direction. And again, so now we've got minus and we've got plus, and again, we can put the little arrows. And we're gonna, when this thing is in the forward direction, this one will be the white LED. So this will be the white one here, which will be very bright. And this one will be the red LED right here. All right, so this is the circuit that we're going to construct. So now what's interesting is we're going to get two different currents depending on which polarity this battery is in, and we'll be able to reverse the polarity. So in one case, we'll get a current, and I'm just going to, let's actually draw them. We'll draw it with white. If we have this LED forward biased, right, then we're going to get this current here. All right. And we could call that, say, IW. But this LED will be off, right, in that case. Now, if we reverse the polarity of the battery, then what are we going to get? We're going to reverse the polarity of the battery. The current's not going to flow this way. The current's going to flow this way in the opposite direction because the polarity would be reversed, right? And we're going to get that kind of thing. It's a little bit messy, but bear with me. And that we'll call I red. So those are the two different cases here. So that's what we're going to build. So very simply, that's what we're going to build. So we're going to build a power source, and then ultimately, what's this thing over here? The battery is really just going to be, we're going to have kind of two posts, right? And that's going to be where our battery connector connects, right? We're just going to have two posts, and those posts are going to be separated, have a separation of 0.1 inch, which is very common. So we're just going to use two posts there. So we're going to have two posts, we're going to have our switch, we're going to have a resistor, we're going to have two LEDs back to back, opposite directions. We're going to close the circuit. So we just need a few wires, and then we're going to build this. And it's going to be pretty small, so we don't want to use up a lot of space. Okay, so let's go back over to the bench, and let's start fabricating the circuit board that we need to build this thing with, all right? So let's go over there. I'll meet you back there. Okay, so we have our model here, and this is kind of what we want to build. All right, so what we need to do is we need to build this on something. All right, now I've showed you this printed circuit board material before, and it's got the copper pads, and this is really nice to work with. It's a bit thick though, so I mean it's very strong and robust. This is another material. This is just called perf board. It has no metal on it, so if you can design on this and build things on it, but it's very hard to solder anything down because there's nothing to solder it to. However, it's very easy to work with. So if you want to cut it, there are a couple tools that you can use, and I want to show you. Now again, I want to make sure you have glasses on, goggles on, and if you're not real comfortable with tools, make sure you have gloves on, and maybe have someone who is comfortable with tools show you, because I don't want you cutting any fingers off, because you can actually do that with when you're cutting something like this. Now, this PCB, this perf board, could be cut with you could cut this also with a bandsaw or a scroll saw or a jigsaw. And typically I'll cut these things with a bandsaw or a scroll saw and make nice cuts in them. I'll draw the cuts how I want and then do that. But if you have strong enough scissors, or if you have tin snips, you can actually cut it. So let's start with the scissors. All right, let me show you something. So these scissors right here, these are titanium nitride. These are Fiskars, and these are very, very strong scissors. You can cut a finger off with these. These are no joke. They're very serious scissors. And so let's assume that I just wanted to cut a piece of this off for something, right? And just, maybe a little circuit I'm going to do. So very carefully, I maybe go right there on the edge, and I'm going to cut down along this line right here of these perforated holes and get a good grip on it, and very slowly, calmly, and I'm just cutting through, and it's going to shoot off. There we go. And then we've got it, and then you can see there's some breakaway material here. All right, and then I might sand that down and clean that all up. All right, so I just literally cut the piece of circuit board off. Now, another thing that we could have used are tin snips, and these are snips right here. And these are something you might find in a metals plastics class or something like that, or you've seen them at school or work or wherever. Anyway, these have different curvatures. These are straight, but they have them at different curves, so you can cut curves in sheet metal. All right, so again, we'll unlock these, all right, and they'll disengage, and then we can cut this. So again, I can come on here, and I can find where I want to cut, and then very easily just cut right through it, make a nice clean cut like that. So you can see that's how we can kind of cut this stuff apart. So I may want to use this little one right here, so I'll keep these, I'll put these over here aside. All right, now but what we want is to use this big circuit, this material here from this big larger PCB. So the question is, how are we going to lay this circuit out? So we've got a couple LEDs we're going to put in here, all right, and we've got a resistor. We're going to have a momentary switch. So what we want to do is kind of work this out. And this is something you want to do when you build things. So we'll just kind of use these two LEDs as dummy LEDs. We'll get a momentary switch. So here is basically all the components in one resistor. So here's all the components that are going to go into this design, right? That's basically about it. There's not much more than that. All right, so let me move these tools a little bit over here. All right, move our tools out of our way so we have a workspace. Okay, so and again, this is art just as much as it is science. And the question is, how do we want all these things to look? So the first thing is, I'm going to clean these LEDs up and get it so that their spacing is equal. See that? They're not all bent up. And same with the resistor. So that resistor is nice. And remember, these boards are 0.1 inch. Every one of these holes is 0.1 inch in both axes, X and Y. So we want everything to be on a 0.1 inch multiple spacing. All right, and that makes things very easy. All right, so what I'm thinking is we'll cut off a piece of this, right? We'll have the LEDs, we'll have the white LED kind of pointing forward, maybe, right? And then we'll have the red LED, and let's just use a red LED here to be a little bit more precise. We'll have the red LED pointing up. So, and we'll put it at the 0.2 spacing. All right, so if we do something like this is what I'm thinking. All right, and then let's put this right on the edge. We're going to put that right on the edge. All right, and maybe we're going to fold it over like that. Okay, so there would be our LED. So we have our LED, we have a red LED, we've got our white LED, so I'm thinking something like that. Then I'm thinking we can come in and let's see, we could put our button, maybe put our button in the middle here. So we'll put our button in the middle, and this is going to take 3, so we can put it horizontally, or we can put it vertically. If we put it vertical, we could do something like that, all right? And then we can put our power in here, right at the end here, and then we can put our resistor right here, like this on the edge. Now we're very close to the edge, so let's back off the edge a little bit. All right, so this is let's assume that we're going to make this thing maybe 5 wide, something like that. So maybe we can come over here a little bit. I'm going to come over here a little bit, and then we'll bring our button in a little bit like that, right? Okay, and then we'll bring our power in right here, so we're not right on top of everything, and then we can put our resistor here, for example. All right, so I'm thinking this is kind of what we're going to be building, something like this, right? And of course we could squish this even more, right? We could squish it up even more if we wanted to, but let's just do a clean cut. So it looks like 1, 2, 3, 4, maybe 5. Maybe if we cut this on the 5th column here, we'll have enough space. Let's go ahead and do it. All right, so let's just go ahead and do it. We're not. This isn't rocket science. We're just doing this for fun. But you get the idea. We have to kind of space things out and see where they're going to go. All right. Okay. And okay, we'll put these all here. So let's get our cutting implement, and we're going to use actually the scissors can actually cut through this, but it's a little bit difficult. So I'm going to use these larger tin snips. Okay. Now, the only problem with the tin snips is I'm going to have to make multiple cuts here to get through this thing, but that's okay. So I'm going to try and let me back this off a little bit so you can see this on camera. All right, so you can see what I'm doing here. Let the camera stop shaking. Sorry about that. Okay, so I'm just going to cut this. 1, 2, 3, 4, 5. I'm going to cut it right on the 5th. And I'm just going to try and keep this lined up and just get a good grip on this and just very carefully and very slowly cut it. All right, it's cutting good. Take another bite at it, holding this. Good, good. All right, and now I don't want to break it, so I'm going to turn this around and very carefully make sure my fingers aren't in the path of the blade here. And I'm just going to finish off this end right here. Can you see this? Yeah. Just real careful, and there we go. All right, and again, when you're using these kind of tools, and maybe you're really good at tools and this is not important to tell you, but if you haven't used a lot of tools, if you're a pure software kind of person, right, if only if you've touched the keyboard of a computer, which I've seen many, many people like that, you don't have a feel for, you cut real hard and you cut right through it and there goes a finger or something. So just be careful when using these tools. There's lots of videos on using tools, and there's lots of shops you can go get trained at and all that kind of stuff. Now notice, we're using through-hole components here, so I'm not cutting these yet, but what I am going to do is I'm going to cut them right now because they're just too long. We don't need this much to solder and wire wrap. All right, so I'm going to bend this in, I'm going to bend this in, and I'm going to cut this right now. All right, so this is our resistor we're going to use, our 220, and I'm just going to cut that in about half. All right, and again, careful. Things are usually going to go flying. All right, so we got those 2 pieces. Good. All right, now we're going to steal the LEDs from here. Okay, we're going to take those LEDs, and again, we'll straighten these out. All right, and then we're going to cut these as well. I'm going to cut that right about there. So we got that. And then we've got our other LED here, which I'm going to straighten these wires out in just a moment, but we'll cut it right now. We'll cut it right about here. Okay, all right, and we're making a mess. Let's clean this up, throw it in the garbage over here. These little shards, these will end up in your feet, I guarantee it. So be careful. Okay, so now let's put away, we have these testing LEDs here. We'll just throw those away. These are the actual ones we're going to use. Now let's straighten these out. Let's go over here and let's take our pliers here and let's clean these up a little bit. And just kind of make them nice and straight, nice and clean. Good. And then our other one here. Good. Okay. Excellent. Okay. Got our LED, got our switch, and I don't know. Let's do the white switch because it's a white light we're going to use, right? So let's use the white switch. I like the white one. Okay. All right. So we got all of our parts and we got our little posts. All right. And now we've got our circuit board here, which we just cut. And there's a lot of this edge is not really good. Let's look at the zoom camera real quick. And you can see that edge. Let me see if I can get it to focus for you. Good. Yeah, see that edge? It's a little bit jankety. So let's just take a file to that just a little bit and clean it up. All right. So let's do that. Let's get our file out. And again, you can use all kinds of different files. These just happen to be diamond files. They're very, very strong, and they're very hard. Diamond is obviously one of the hardest substances known to man, so it makes really good files, but this is very small. I'd prefer just to have a piece of sandpaper, wet and dry sandpaper, put it down here and just go like this, but I don't have it right now, so I'm just gonna do this and kind of work with it. Just kind of do this and go back and forth and just kind of clean this up a little bit. Now this is ablating particles in the air. All right, so you want to be careful breathing this, right? This is actually made out of fiberglass. All right, there. Okay, we're done with that. And we'll just put this back, and you can see all this stuff right here. So clean that up, put that up. All right, and we're going to get a little towel, and we're going to clean this up, keep our area clean, because we don't want all this particulate matter everywhere, right? All right, so now we've got all our parts. We know what our design is on the computer, okay? So now let's go ahead and put this thing together, okay? Okay, so we got all our parts, and so now off screen here, I've been getting some stuff ready, and I've got our soldering iron is all ready to go. So I've got our soldering iron right here, and it's all hot, and this is good to go. So we got that, and I've got our wire wrapping tool here. We're going to be using orange wire wrapping wire, and this is 30 gauge. All right. Now another thing, let me show you something. So you might be thinking, you know, I can't imagine cutting all those pieces of wire wrapping wire, right? And you know, you could have thousands of connections, right? And I like to do that myself. I actually like to cut the wires. I find it relaxing, but you know, they do have them pre-cut, and there are companies who make these. So here's some pre-cut wires, and this is Page Digital Ink. There's 100 6-inch wires in here, and these two different colors. You can see they come like this, and you know, and these were $3.99 each for the 100 wires. So, you know, you can do that, or you can just, you know, cut the wires yourself, whichever you like. All right, and there are many, many vendors that have pre-cut wire wrapping wires. All right, so what we're going to do is we're just going to cut off a few pieces here because we don't need many wires. So first thing is, let's just cut a few pieces of wire here. All right, we're not going to need anything very long. All right, so I'm just going to kind of cut a few of them here and just kind of get it ready. And normally what I would do is I would cut like, oh, maybe 6 inches and 3 inches and 1 inch, right? But we're like literally going to need only a couple wires, right? And we can even use the leads themselves to solder things together. That's another technique, right? So I'm just going to cut a few of these wires, and this is all we do. We just sit here and cut the wires, all right? And I'm not going to strip them yet. I'm going to do that as I work. All right, so we've got those wires right there. All right, so here's how long these are. So I've got those, and then what I'm going to do is you know, maybe I'll get some little shorter ones here, a couple shorter ones, and we'll just get those ready. There's, oops, 2 of them, and can't see that we're going to need more than 3 of anything. Okay, now we're done with that. All right, so we got our wires, we got our wire wrapping tool, so I'm just going to put those aside, a little off camera there. You don't need to see those. All right, I'm going to move this away. We don't need that, and we're just going to get here in our nice workspace and kind of work on this. Okay, so our plan is we're going to first insert the parts into the printed circuit board, all right, and then we're going to solder some of it together, and we're going to wire wrap other parts of it together. All right, so the first thing is, since we're going to be doing soldering, we're going to put down a little safety mat here. All right, so here's the center here. I'll try and keep the center there. All right, so we're going to put down our little safety mat, and the camera is going to make adjustments because it's so white, so bear with it. All right, we're going to get some solder. We're going to use a larger gauge solder. All right, there's a little piece there, and here's our solder. All right, so I'll just get a couple pieces ready, you know. Okay, another piece right there. You know, you just get things ready so that you don't have to be bumbling around as you're putting stuff together, right? Otherwise, it's a pain. We've got this right here, which we're going to clean the solder tip off with. All right, so I'll kind of have that right there, so you can kind of see that a little bit. All right, over in the edge there. And we're not going to wire wrap as of yet. First, what I want to do is just put these parts inside of the circuit board. All right, so that's the first thing that I want to do. All right, okay, so again, we're gonna let's take a look at this, and it looks pretty symmetrical. All right, so what we're gonna do is we're gonna put the cathode of this white one. We're going to put the cathode of the white LED on the right. So let's kind of remember that. So the first thing we're going to do is we're going to put it in here, all right, and then we're going to bend this down like this. And now on the back here, you can see we've got the two posts. So what we're going to do is we're going to kind of bend these out so we can solder this, all right? We're going to bend these out so we can solder it. We're going to solder this down to the board, all right? So that's the first thing we're going to do. So let's just do it. All right, so we got it down there, and we could flux this all up, right? But we're just going to count on the flux inside of the solder, all right? And I'll zoom that in there for you a little bit so you can kind of see it. All right, and let's go ahead and do this. So I've got my solder. Let me get a piece of solder here. And again, you might want to wear gloves. I've got goggles on right now, so I'm safe on that. All right. Okay, and then remember what we do is we're going to tin this thing up. So we're going to just put some solder on it. We're going to get it going. See that? Nice flux. All right, we'll let that sit on there for a second, then I'll clean it off in this thing here. All right, clean it off in here. All right, nice, good, I like it. Okay, and now let's get back here and let's do this. So the trick is, again, you're going to touch the soldering iron to the joint you want to solder, and then you're going to get that hot, and then you're going to apply some solder. All right, and it'll sink in nice, and just you got to just hold your breath when you do this. Another trick, hold your breath, and that's for the fumes, one thing, but also so you're not breathing and jiggling around. You see that jiggling? I don't want to do that. I just want to hold my breath. It's like shooting a gun. If you've ever shot a gun, you got to hold your breath. All right. Okay, there we go. A little bit more solder. And there. See that? It's about 1, 2, 3, 4. You're done. 1, 2, 3, 4. Okay, we clean the soldering iron off, clean it off in the sponge. I put it back into the little holster, right? There's a little holster there. You can see that. It's back there, back there. Okay. Now, let me take a look at this. This is still hot. It's still hot, so be careful, all right? And now I've got our two posts, so I want to straighten these posts up. Okay, so what I'm going to do is I'm going to grab my pliers here, my needle nose pliers. I'm going to straighten those up. Excellent. Okay, so we got that inserted, and that was hot. That that burnt my finger a little bit as I was holding it. You can blow on it to cool it off too. That's another tactic. All right, now we're going to put the other LED in, but we want to put it in backwards compared to this one. All right, so the cathode is on the right here, and so on this one the cathode is here, so we're going to flip it. All right, and we said now these are going to be absolutely in parallel. So what we're going to do is we're going to actually put it like this. We're going to put it right like that, okay? And then what we're going to do is we're going to actually take these, and we can do this in either direction here. So we can bend these down to here, right? Or we can solder these and then bend these and connect them. So we can actually use the wires as part of the circuit, okay? So what I'm going to do here is I'm going to actually fold these down, all right? I'm going to fold these down and let you see what we did there, all right? So they're making contact, all right? And then I'm going to get another tool. I'm going to get a little tiny screwdriver. Just going to get a tiny screwdriver so I can push on things, all right? And I'm going to kind of put that there. I'm going to kind of put that there. So now I'm going to solder this in here. That's my first job here. I'm going to solder this in here, all right? And because we've got something sticking up now, it's a little bit harder to solder. So now is where you kind of need something to hold this, right? So we can get do things like this, and you'll find yourself doing this all the time. So here I've got this little tool, and I'm just going to set it right here. So I got something to set it on. You can do that, right? Or you could get the little helping hands with the clamps to hold it, right? But let's see if this will do. All right. I don't want to get too extravagant, too complicated. All right. So here we go. Let's solder this. Good. All right, that's really bouncing around. I'm not too happy with that. Let me try it here. Try it right there. Okay. Do that. There we go. Looks good. And that's soldered. Okay, now we want to solder these interfaces where it's touching over here. Okay, so now we're going to solder those, and that's going to be like our wires. All right. Okay, that one's good. And then we're going to solder this one. And this thing's running around on me. In about 2 seconds, I'm going to get something to hold it. There we go. Okay, so just clean the soldering iron off. All right, so I'm happy with that. Okay, let's look at the zoom camera so you can see what's going on here. So on the zoom camera here, You can see that's what we got, and let's see if we can get it. There we go. All right, so now we've got our connections are all good. Now what I'm going to do is I'm going to cut off these extra pieces here because we don't need them. All right, so we're going to cut these off. So again, let's get the camera here to focus a little bit, and we're going to cut this off like so. Cut that off and cut that off. All right, and this is why it's good to have precision tools so you can really get them in there. Okay, so now we got those two posts. That's where we're going to make our electrical connection to the LEDs. Okay, what else do we need? Now we need our resistor, and we need our switch, and we need our power. Okay, so now another technique people will use is they'll put a lot of things in, and sometimes they'll put tape on the top of it to hold it as they flip it. You know, there's lots of different ways to solder things together. And so, you know, keep that in mind. All right, so we're going to bring our power in here at the end, right? So we're just going to bring our power in there, and then I want to have enough. Now, these are not very stable. These posts are not very stable. They're not sitting in here real good. And we want to have enough so we can plug into them, but we also want to have enough so we can wire wrap to them. All right, so, okay, so I've kind of got them right about here, and I'm not really happy with this, so bear with me. And again, I want you to see the trials and tribulations of everything. All right, so that's kind of what we're going to do. And then now I'm going to very gently just sit this down, and that's not going to work for me. Okay, and let's see here. All right, now that's not going to work. So now another trick is we can stuff these inside of foam. Okay, so we've got some anti-static foam here, all right? And then now what I'm going to do is I'm going to actually plug this into the foam. Okay, so now it's got something to bite into. Now I'm going to go and reconnect these here. I'm going to put them right at the end. There we go. So now we got something for the post to sit in, all right? And everything's kind of being suspended, all right? And again, you know, this is not, we're not doing this perfect. We're not doing this production quality. I'm just trying to show you how to kind of build something. And there's, you know, better ways to do this. All right, so we're going to go ahead and solder here. Let's get this soldering iron, get some solder on it. All right, here we go. All right, and let's solder this. And I'm going to kind of hold this with one finger. And again, you're going to be doing a lot of this. You're going to have to hold things with one finger and solder. And, you know, I've actually used my hands and my mouth to solder things. I've actually had to hold on to something with my mouth as I soldered something else. All right, so that's not bad. All right, so that's not bad. A little bit crooked, but I'm happy with it. Okay, so now we got that soldered in, all right, and anchored. So now we can finish. So now what else do we need here? We need our resistor, right? And then we need our switch. Okay, so let's go and we'll put our resistor right here. All right, we'll put our resistor right here and get that in. Okay, so there's our resistor. Now we can do one of two things. We can take the resistor and we can directly bend this lead down here like this. All right, we can do that, and then solder, you know, both of those right there instead of wire wrapping. So let's go ahead and do that. We might as well take advantage of the wire that we have. Okay, so we're going to hold that like that, and now what I'm going to do is I'm going to put a weight on here like this. All right, and again, I'm just trying to show you different techniques. I'm going to hold this thing down so I can solder it. All right, now let's get our solder. All right, let's tin this up good. All right, clean it. Okay, and here we go. So first I'm going to do this point right here. Okay, here we go. Okay, that's good. And now I'm going to get this where it makes contact with the post. Good. All right, and then finally, take a quick look at it, make sure nothing's moved around too much. All right, clean that off. And now my solder is getting a little bit short, but I'm going to try and still use it. Trying not to cover the camera up here. All right, and there we go. You see the flux burning away. Good, good. Clean my soldering iron off. Put it away. Now I got this little teeny tiny piece of solder. I'm done with that. All right, let me grab this. All right, so now we're getting someplace, right? There we go. Good. All right, so we do not need the end of this right here, so we're going to cut this off. Okay, and throw that away. This thing is pretty hot right now. That just burnt my finger a little bit. Okay, now we got this large post right here. You can see that, and what I'm going to do is I'm just going to cut that down so it's about as long as these posts, because we're going to, wire wrap to some of these. Okay, throwing that away. All right, so now we got our resistor, so we got power coming through the resistor, and now we need to take that to one side of this LED, and then the other side is going to come back, and we'll put that, that can either come all the way back down here, or we could put it through the switch. So right now, what we can do is let's just go ahead and let's just put the switch right here. I'm going to put the switch right there. All right, and we're going to take the resistor, and we're going to actually wire wrap. So let's leave the rest for wire wrapping. So all we're going to do now is solder this switch in here. All right, so again, I need to put the switch on something. So I could set it like this or set it like this. I need to put some weight on it, or I can bend these leads is another technique. You bend the leads a little bit so it can't fall out. So we'll do that. And then we'll kind of push it in here. So now the switch is kind of sitting there so I can solder it. So let's get our soldering iron again. Let's get our piece of solder. All right, we're doing good, doing good. All right, so we're nice on camera here. Okay, so let's get a good angle here and tin this up a little bit. All right, and there we go. All right, the solder just melted and dropped down. And again, and remember, we're touching these mechanical things. You don't want to hold this on here too long because you're heating up the post, which is then heating up the plastic. Okay, now, so now we're doing pretty good. I'm going to straighten all this out with these needle nose pliers. Hopefully you can see that good. All right, and now let me show you. There's a nice cross section, so everything's nice and straight. There's nice and straight. All right, so now what do we got to do here? What do we got to connect? Let's look. All right, so remember, our power is going to come in here, right? So here it's to the resistor, resistor to the switch, switch to the LED, through the LEDs, and then back directly to the other end of the power, okay? So that's what we're going to do on the other side here with wire wrapping, okay? So now let's do some wire wrapping. All right, so we can move the soldering iron a little bit away. All right. Okay, so the first one that we need to do here is we're going to go from the now we've already got from the power input through the resistor, so we just need to go resistor to the switch. Now we could just bend this over and solder it, but we want to do something with some wire wrapping, right? So let's use the wire wrapping tool here. All right, we'll take one of the short wires. We kind of look at that. That's going to be no problem, so that'll work. Let's go over here and let's strip this. We'll put it in the stripping part of the tool. We pull this back, and you make sure your hands are very, very dry, because if they have any oil or any moisture, you'll just slip all over the place. Now we're going to put this into the hole here, bend it over, all right, put it on the resistor's post. I'm going to hold this, all right, and very carefully, I'm going clockwise here, and it's riding up, it's making the little twist, and then I'm going to push it down, all right, nice. So that's that. Okay, so when I got that, now I want to connect it to here, to the right next to it. So I'm going to kind of give it one extra wrap, and then I'm going to look at the length about there. So then I put my fingers about there. And again, it's all about just trying to make this neat. And we're going to use the cutting tool again, right about there. And then I pull it off very gently. Now I'll put it in here. And there we go. And then we want to go here to the switch, and very gently, don't let it bind up, because it will and it'll break. Okay, done, and I'll push that down very gently, straighten these out. Now let's go take a look under the, and then again, we can use our tool here, we can straighten things out, we can make 90-degree angles, make it nice and clean. Let's look under the zoom camera real quick. So you see that? That's nice. Now we need to go, where do we need to go next? We need to go from here to this LED. All right, so we're going to the LED there, and we could we get away with a short wire? Let's see. Can we get away with a short wire on this one? We're going to go from there to there. Yeah, I think so. We can get away with a short one. All right, so, and that's why we made both the wires. So we'll take that, we'll strip it, good. Put it in here, get it ready to go. All right, we'll put it down on the other side of the momentary switch. Go ahead, there we go, good to go. All right, and give it one extra wrap so it doesn't unwind, and then now we need to go right here, right there. Okay, so I'm gonna put my finger there roughly, Okay, so I know where to strip the insulation off. There we go, insulation is stripped. Put it in our tool here, and you can see this. Now once you get going on this, you can go really, really fast. You could do, you know, hundreds and hundreds of wires a day. All right, we'll push that down. We'll take this tool right here, and it's just a screwdriver, and I'm just going to push this down, get it all nice. Now, what do we got left? We got one more wire from the LED all the way back to the power. So we use a long one here. All right, so let's go do that. So first let's strip it. Okay, there we go. And presto, bend that. Go right here to the end. Get that in there. Okay. And again, I'm trying to see this and do this. It's like sewing on camera. Push it down a little bit, and then I give it an extra turn just to make it stable. Give it an extra turn. Okay, now we're going to run it all the way straight back to power. Okay, so I'm going to roughly get how long I need it, right about there, and then that's where I'll strip it. There we go, strip, put it back in our tool. All right, and then here we go, put it on this other lead here, and I know it's hard to see with all the reflections and everything, but there we go, clockwise, clockwise, okay, and then I'll push it down, and there we go. All right, and then now we can take this tool here, and we can, you know, put this wire where we want. Maybe we can put one more wrap around here. Nope, doesn't look like it, just barely enough. And we'll just push these wires, kind of make them nice. So there's our circuit. All right, so that should work. All right, so let's go ahead and give it a try. All right, so first thing, let's move this away. Let's clean up our little area here. Zoom in, there we go. Okay, cool. All right, so where's our power supply? So here's our battery clip. Here's our power supply, our rechargeable 9-volt battery. Let's hook this thing up. Okay, and no matter which way we put it, it should work, right? Okay, so let's put it in. We'll put it with black to the right first. All right, and when I push this button, this thing should turn on. And sure enough, it does. Woo! How cool is that? All right, and then if we flip the battery around, then if we push the button, and then, uh-oh, the battery's the wrong way. So that's it. We just made basically a flashlight. Now, what you could do is you could go on the back here and you could solder all these wire wrapping posts so that they're soldered. And then you could flatten them out. You could put something on here, and then if you have a 3D printer, you could 3D print a housing and put the battery inside of it, and then you have a little flashlight. All right. So anyway, so that was good. We did wire wrapping, we did soldering, we did fabrication, we cut printed circuit boards, we built a circuit, we modeled it first on the computer. We drew the circuit, then we actually modeled it on the solderless breadboard. Then we committed it to a point-to-point wire wrapping PCB. And then now your next step would be to actually design a PCB. And of course, later when we start playing with Circuit Maker, we'll see how to do that. But we have to have enough information to be able to do those things. All right, so anyway, so hopefully that was a lot of fun. And we're going to go back to doing some more circuit analysis in the next lecture. But I think we've got through a lot of material. We learned to solder. We saw all kinds of tools and equipment. So anyway, let's go back to some more circuit analysis. Let's learn some more techniques and tactics to be able to design circuits and get them to work. And then we're just going to keep moving through this material. All right, so I'll see you in the next lecture. Bye. All right, well, welcome back to the next lecture. So we're in the next section of the course, and we're going to be talking about circuit analysis. So we're not going to go too deep into circuit analysis. Circuit analysis is a very complex field of study, and to solve different circuits, you have to use linear equations and matrices and all kinds of techniques, and it can get very, very complicated in the modeling of different components and so forth. But what we're going to learn is how to use just some simple tools so that we can compute currents and voltages mostly in our digital circuit so that we can kind of, figure out what's going on if we want to, say we need a voltage we need to compute or compute a resistor or something like that, or use a simple technique like a voltage divider. So anyway, we're just going to learn some basic techniques here in addition to the one rule we already learned, which was Ohm's law. All right, so anyway, so we're going to be following my book material just roughly like we usually do. And we're going to talk about things here, and then we're going to do some experiments on the bench as we go, like we normally do. So just kind of an overview, we're going to talk about circuit analysis again in Ohm's law. We're going to do Kirchhoff or Kirchhoff's laws, series and parallel resistor circuits, so you can kind of know how to figure those out. Talk about voltage dividers, and then we are going to end up and talk a little bit about simulation with a technology called SPICE. We're not going to go too much into this, but I do want to show you how to use simulation because it is a really cool tool, but there's nothing better than actually building it on the bench. So anyway, so let's begin here. So what is circuit analysis? So circuit analysis is simply applying techniques to be able to solve the currents and voltages in a circuit. And if we're talking about analog circuits, we're talking about potentially both DC and AC analysis, meaning we might want to figure out what the circuit is doing at steady state DC, or we might want to figure out what the circuit's doing with an AC signal. We might want to figure out what the transient response is. So if we change the circuit quickly, power it up, power it down, or a signal propagates through it, how does the circuit change in the transient response? So these are all the kinds of things that you might want to do. Now, typically, since we're building up to being able to build digital circuits properly and do the analysis there, we're not going to worry too much about things like AC analysis or transient response. We're just want to figure out how to do DC analysis for the most part, okay? So that's kind of what we're gonna work on. Okay, so let's begin with a simple definition here. So what a circuit is. A circuit is any closed electrical loop where current can flow from one source through an electrical network back to the source. So there's as many definitions of what a circuit is as there are circuits. But the bottom line is a current is going to flow from someplace through a network and it's going to come back and make a complete loop. That's simply a circuit, all right? Okay, now we're just going to use the material here just for something to anchor to so we can have some examples. All right, so we've got a circuit here in this figure, and this is something like our little flashlight model that we just constructed. All right. And we've got a voltage source. Here it is. It's a battery, right? And that's the symbol for a battery. And then some nomenclature, typically so that we can measure things in a circuit, we'll have what we call nodes. And, here's node A, and here's node B, and then here's node C. And we'll label these nodes. And node C in this case happens to be also the ground node, all right? And then we have the current flowing through the circuit here. And in this case, we have this I sub S going through this resistor here. And then we have I sub L going through this load. All right, now one of the things that we're going to learn, that we've kind of already learned, is that if we have a loop, the currents in a series circuit, right, in a loop are always the same. So IS does equal IL. All right, and then we see that we have a voltage drop over the resistor. So current is flowing to the right here, right, conventional current. And so it's a resistor, it's going to drop the voltage plus to minus, and then again we're going to get another voltage drop plus to minus, and then we're back to the source, back to the ground of this battery, okay? All right, so that's it. So the takeaway here is the word node and knowing what these things are. And that's just the point. And we create nodes in a circuit so that we can measure their voltages and reference them to other things. So for example, if we have the voltage at say node B and node C, we could compute what the current is through RL. And if we know what the current is through RL, that's the same current IS because the current stays the same in any loop. All right. So that's why the nodes are important to be able to label. All right, so Ohm's law again is very simple. It's voltage equals current times resistance. Voltage equals current times resistance. And what's important about it is you have to keep in mind the convention for the current. Are we using a positive conventional current? Are we using negative electron current? And then depending on which of those conventions, voltages are going to drop in different ways, and you're going to get sign issues with the signs and the computations. We're using conventional current, which means a current is going to flow from positive to negative. So in that case, up in this example here on the left, we've got a current I. We have a voltage drop from plus to minus over that resistor. Voltage equals current times resistance, so that current I equals the voltage divided by the resistance, and so forth. If we wanted to compute the power is the voltage times the current, right? P equals V times I, so it would be the voltage times this current here would be the power. The power would be dissipated in this resistor. The resistor dissipates power, so it would be power dissipation as heat in the case of resistor. Now, again, if we continue with our same convention for current using conventional current, if we were to flip these signs here, right, and if we said that, oh, we just want to make the voltage negative to positive here, sure, then go ahead and do that, but then you're going to have to flip the sign of the current. So the point is watch your signs, be careful what you're doing, otherwise you'll make sign errors, and then everything will not add up. Okay, so again, remember V equals I times R, Ohm's law. That's all that is. All right. Okay, and we just talked about that. All right, so now these are just some examples here. So let's just take a look at these, and let's go ahead and draw these. I'd prefer to draw them. You can read through the text here for these specific examples, but I'd rather create some new examples. So what do we have here? We've got one example where we're trying to compute what the voltage is, and then another example where we're trying to compute what the resistance is, given that we're told what the current is. Okay, so why don't we try and mimic something like this, and let's go and draw this out. All right, so in the first example, and again, it's all about repetition. You just simply have to do this a lot. So we're going to figure out what the current is in a circuit. So let's go ahead and let's just say that we have some kind of voltage source. And let's come through here and let's say we have a resistor. All right. And going back, and we could say, here's the ground. And this is plus to minus. And let's go ahead and say that this is a 5-volt. Source. Maybe it's a battery or it's a source. If it was a battery, we could draw it as a battery, but when we generalize like this, we just don't know what it is, but we know it's a source, and we know this is R. Okay, now we're going to get a current flow here. We're going to get a current coming through here like this, and we're going to get a voltage drop from here to here, and we could call this VR. Now we could also do some labels here. We could call this right here node A if we like. All right, and we could call this node B if we like, and sure, we could call this node C if we like, which is also ground. All right, now let's go ahead and let's write it down. Ohm's law. All right, and that states that V equals I times R, and we've done this enough times so you guys should start to get good at this now. So we've got a current, and this current here, let's call this current I sub R. It's the current going through the resistor. The voltage drop over the resistor is VR. First question, common sense. We've only got one voltage source here. We've got one resistor. What's VR without doing anything? What would be VR? Well, we've only got one resistor, so the entire voltage has to drop over that resistor. So VR does in fact equal 5 volts. Okay. All right, so we got 5 volts there. And so we've got 5 volts, we've got an R, but we're trying to compute what the current is here, right? And so we need to know what this resistor value is. So we actually need to set this resistor. So why don't we set this resistor to, let's say, let's make it 10K ohms. All right, so now we know what the resistance is, we know what the voltage is. So voltage equals current times resistance, or resistance equals voltage divided by current. So we want to compute R. And let's just call this, we'll call this R1. And let me just be consistent here. All right, let's get back to our green. And we'll say that R1 equals what? V over I. Oh, excuse me. We're not computing R1. We already know what R1 is. We're computing I in this case. So we're computing I sub R equals, and that's going to be V over R. And in this case, V is 5 volts, and R is our R1 here, which is 10K. So we got 5 volts over 10K. If it was 5 volts divided by 1K, it would be 5 milliamps, right? So volts divided by K ohms equals milliamps. But if it's 10K ohms, right, then it's going to be 0.milliamps. But let's do it on our calculator. Get your calculator out. So 5 divided by 10 x 3, and put that into the proper format. And we get 0.5 milliamps. 0.5 milliamps instead of 5 milliamps, and that's correct. That's good. So 0.5 milliamps, or you could say it's equivalent to 500 microamps. All right, that's it. So that's it. So we just use Ohm's law. And so what are the takeaways here? We have a current flowing in the circuit, and we can compute anything with V equals I times R, but we need to have 2 of the 3 variables to figure out what the third variable is. Let's say if we also wanted to compute the power here. What's the power? Dropped over this resistor. All right, so remember, power equals voltage times current. Now, based on Ohm's law, we can replace V with I times R. We can replace I with V over R. So we can also come up with a couple other formats here. So V is I times R. All right, so that would mean that power is I squared R. Or it's also, we can also replace, I, and I is V over R. So we would get V squared over R. So there's 2 different forms of what power is. So 3 different forms in total: V times I squared R, and V squared over R. So in our case right here, we can do it in a couple ways. So what does this say? That the power goes up at the square of the current, right? Or the power goes up at the square of the voltage divided by the resistance, and then the square of the current times the resistance. So whatever's convenient for you. So either will work. Let's do the I squared R format. So that's 0.5 milliamps times the resistance is the power. So 0.5 milliamps, and then that's going to be squared, times the resistance R, which is R1, which is 10K ohms. All right, and let's get our calculator out. In our calculator, we say 0.5 x to the negative 3, and then we square that value. All right, and then we multiply that times our 10K. All right, and we get 2.5 milliwatts. So 2.5 milliwatts. All right, and that's it. So we just computed that and did that circuit. Okay, so let's go back and let's see what the other circuit was. So in this case, what we're interested in here is, well, what if we know the current and we know the voltage and we want to compute what the resistance is? So we're going to do the circuit backwards. Okay, so let's do a circuit like that. So let's get rid of this. All right. So now let's build a circuit, and that one had 2 sources. So let's kind of do the same thing. So in this case, let's say that we had two batteries. All right, we had 2 batteries, and here they are here. And let's say that we had, and this is plus to minus, right? This is plus to minus. Let's say that this was a 9 volt, like the one we used in our flashlight. And let's say that this one was a 1.5 volt. All right, so this is just, it could be a AA battery, it could be a AAA battery, right, etc., a primary cell, right? Okay, so we've got 10.5 total volts here. All right, and then let's go through here and let's put a resistor here. All right, and let's call this R1. All right, and then let's put a current through here, and let's just say what the current is. All right, now this is a little bit tricky. It's kind of like you have to know the answer before you do it. But let's just say, we're going to say that we desire a current in the circuit, and let's say that the current that we desire is 25 milliamps, okay? 25 milliamps. Maybe this load, this resistor, is a light or an LED. Not really an LED, but maybe it's a light of some kind, an incandescent lamp, and we know that we want 25 milliamps of current to flow through here. It could be an LED, but we want 25 milliamps. So then the question is, what is the resistance value to get 25 milliamps with the source of these 2 batteries? Okay, so the first rule is that we learned is if you have batteries in series, you add their voltages. Do you remember that? All right, and if they're in parallel, basically we need them to be the same voltage and then they can source more current. So if they're in series like this, we can replace these two batteries with an equivalent battery. So if we take these like this, these basically change into a single battery like this, and then we have our circuit again. There we go. And this new battery is the sum of the two voltages. So 9 volts and 1.5 is 10.5 volts. Our current is the same, all right? So we've got this this I1 current, right, or IR1, whatever you want to call it. So we're going to put it through here, all right? And this IR1 current, we'll call it IR1, and it's equal to 25 milliamps, okay? And we've got our resistor here again, and the voltage is going to drop plus to minus over the resistor, plus to minus over the resistor. So this is our new equivalent circuit. So this circuit is equivalent to this circuit. So now we're still at the point, what is R1? All right, R1 equals. All right, well, we've got the voltage, we've got the current, we need the resistance. And what's Ohm's law? So let's go back up here. Ohm's law, all right, says that voltage equals current times resistance. So we want, what do we want? We want the resistance. So resistance equals the voltage divided by the current equals, what's our voltage? So what's the voltage drop over the resistor? Well, how many voltage drops do we have? We only have one. So at this node here, right, and we could call that node B, and we could say to ground, the entire voltage has to drop over this because there's nothing else for it to drop over, and it's 10.5 volts, all right? So 10.5 volts over I, which is 25 milliamperes, 25 milliamperes equals, get our calculator out, all right? 10.5 divided by 25, x minus 3, and we get 420 ohms on the dot. Oh, that was pretty good. 420 ohms. So we have 420 ohms. All right, we have 420 ohms, and that will complete this circuit. Now, what is the power? How much wattage do we need to be able to dissipate in this circuit? All right, so let's say that now we need to also spec out what the wattage of the resistor is. Should it be a tenth of a watt, a quarter of a watt, an eighth of a watt, 10 watts, 1,000 watts? Let's figure it out. So how do we compute power? So again, let's put the 420 here, 420 ohm. All right, so again, what's power? Power equals voltage times current, all right? And so in this case right here, we've got a current of 25 milliamperes and we got a voltage of 10.5. So let's just go straight with that. So we got 10.5 volts. We can put some parentheses around here. And then we've got 25 milliamperes. 25 milliamperes equals, let's get our calculator. All right, so 10.5 times 25 milliamperes equals 0.2625 equals 0.2625. Okay, what's that approximately? That's approximately 0.25 or 1/4, right? So that's a quarter watt. So we're right at the limit there. And remember what I said, I prefer when you are going to over design. So that's going to heat that thing right up. So why don't we use a 1/2 watt? So we would use a 1/2 watt resistor in that circuit, and then that's not going to get too hot and we're not going to have too many problems. So now in this case, what did we do? We computed the resistance based on a given current or a desired current. So remember, you can work this stuff any way you want. You can compute the resistance, voltage, whatever it is that you want, all right? Okay, so let's move on and see what we got kind of next here. See what else is interesting. All right, we've already done some power calculations. We just did that, so we don't need to talk about that. All right. Okay, and then the next section, what we're going to do is we're gonna come back and do the next lecture. We're going to talk about Kirchhoff's laws. But what I'd like to do right now is I'd like to go and let's go ahead and let's build one circuit. I like to build something each time. So let's go build a circuit, and inside of that circuit, let's just do something interesting. So let's come back here. So this is not very exciting. So why don't let's do something like this. Let's go ahead and let's take a source, which I don't know, maybe 5 to 12 volts. We'll use our power supply. And then let's go ahead and let's do something. Let's take two resistors. We'll take one resistor and another resistor, and then we'll go back to ground, and we'll call this R1, and we'll call this R2, right? Plus to minus, plus to minus, all right? And then we're gonna have a voltage drop. We're gonna have, we'll call it V1, and we'll call it V2, all right? And the question is, and then we're gonna have some current flowing in the circuit, right? And the current is gonna be the same current, all right? And we're just gonna call this, current I. All right, so then the question is, what's V1 and V2? And then how could we kind of compute that? And let's kind of put some nodes here. So we'll call this node A, and we'll call this node B. And this node down here is just ground, so we don't need to call it anything. So there's our ground. And remember, ground can be this little 3 lines or just the 2 lines. I just usually draw just 2 lines, okay? So we're gonna make this circuit right here. We'll pick a couple resistors, and then we're going to see what happens. And then we're going to learn why that happens. All right, so let's go do that on the bench right now. Okay, so we're here on the bench, and we've got our parts out here, and we've got our circuit up on the computer that we took a look at. And basically, it's just 2 resistors and a power source, and we're just going to kind of see what happens. All right, so I've just got some resistors here. I got switches, I got some LEDs, and we're just going to build something up, right? Okay, so we've got our power coming in here. And so we're going to start off and we just want to put 2 resistors to ground. We just want to see what happens, okay? So let's pick 2 resistors here. Let's pick something that are kind of multiples of each other. So let's pick a 10K and a 1K. There's a 1K and there's another 1K. So here's a 10K, brown, black, orange. All right, so remember 1K is brown, black, red. So there's a 1K, brown, black, red. And remember gold is the tolerance. And then here's a 10K, brown, black, orange. Can you see that's orange? All right. So now, common sense. In electronics, the more you can use common sense and your intuition, the better. Now, some things don't work like that, right? But a lot of electronics do, especially because they're linear systems, right? Now, quantum mechanics, no, that doesn't work like that. Common sense does you no good. In fact, it hurts you. But in electronics, a lot of times you can use common sense. All right, so we've got our power supply. I'm going to turn that off. All right, and what we're going to do is we're going to put our 2 resistors in here, and we're going to, as a matter of fact, let's go ahead and let's connect them with a wire between them. We could connect them directly, but we're just going to connect them just like this. All right, and then now let's connect one end up to power, so that's going to be our power, and then we'll connect the other end down to ground. All right, so here's the other end down here to ground. All right, okay, so now we've got 2 resistors. We've got a 1K and a 10K. So we're going to apply a voltage. We're going to get a current. The current's going to go through the resistors, back to the power supply, and that's going to be that. Now, what I want to bring your attention to, and we've already talked about this, how to add series how to add resistors. We've already talked about this, how to add resistors in series. But I want to show you something that's kind of cool. So let's turn the power supply on, and let's turn the power supply onto this. We've got 1K and we've got 10K. So we've got a total of 11K here, all right, ohms. We're not sure how it adds, but our intuition says it should add up in series, meaning we should just be able to add these numbers up. The reason why is we've got one resistor here and one resistor here. These are both physical objects. If we were just to kind of merge them together, we would have here 1K and we'd have here 10K, and voltage is going to drop over the first part, then over the second part. So we would have 11K, you would expect. So if we apply 11 volts to the circuit, we would expect we'd get 1 volt over the 1K and 10 volts over the 10K. In other words, we would get 1/11th of it here, and then we'd get 10/11ths of it over here. So let's put the power supply to 11 volts. All right, it's at 11 volts. I'm going to turn it on. And we're throwing a little bit caution to the wind here because we really should compute power so we don't burn anything out, right? But I'll tell you right now, we should be okay. All right, and let's get our voltmeter here. So I'm going to get our voltmeter. I'm going to open this up, zoom out a little bit here so you can see what's going on. And I'm going to put our voltmeter, let's put it right here to the right, okay? Okay, so I've got the voltmeter on. Hopefully everyone can see that. And let's measure some voltages. So first, let's measure the power coming in across the rails. So we should have 11 volts. And we do. Oh, And look, we've got our power backwards here from our previous experiment. So let's flip that around. All right. So let's get all our signs right. Okay. Now let's go ahead, plus to minus. And sure enough, we're showing, if we can get this on here good, okay, 11 volts. All right. All right, so 11 volts is exactly what it should be, so that's good. Now let's measure the voltage over the 1K resistor. All right, so let's measure it over here. Let's make sure that these probes are being a little weird. There we go. 0.999, 0.993, 1 volt basically, 1 volt. All right, and let's measure it over this other resistor, and we're expecting 10 volts. 10.02, right? 10.01. So there you go. So 1 volt and 10 volts. So it linearly dropped over the sum of the two resistors, right? So now, if we were to half the voltage, then each one of those would half. So now we would have 0.5 over this, and we would have basically 5 volts over that. So we've got it at 11 volts, so what's half of 11, right? 5.5, so I'm going to change it to 5.5. And I just want to show you the linearity of this. All right, so, okay, power supply is at 5.5 volts. Let's make sure I'm telling the truth here. 5.5, okay, so let's check it over the first resistor. And there we go, it's 0.5 volts, right? Almost. And over the second one, and it's 5.0, exactly what it should be. All right, so that shows the linearity of the system. All right, and then the current, we could compute the current by looking at the voltage and the resistance. We know that, or we could open up and go into the circuit and do this. All right, so if we wanted to check the current, again, we would put the meter into amp mode, or we're going to put it in milliamp mode here. We're going to move the probe into milliamps, right? Because we're pretty sure milliamps are going to flow here. We're talking about volts in case, so we're probably talking about milliamps or microamps. So we got it in milliamp mode. I'm going to turn off the power supply, and then I'm going to insert into the circuit one of our little connectors. So I'm going to put one of these little connectors here because we want to get this in series. Remember, the amp meter has to be put in series down to ground, okay? And then we're going to plug our connectors into here, and that's why these are so useful, these power supply connectors. They just work out perfectly. All right, so I got it all good to go. All right, so let's go ahead, let's turn the power back on. All right, and what do we get? We've got 0.5 milliamps, 0.5 milliamps. And let's see, does that make sense? So we have 5.5 volts and we've got 11K, and we're saying the resistors seem to add up when you put them in series. So the values seem to add up. So that's 1K and 10K is 11K. So we have 5.5 volts, 5.5 divided by 11 x 3 equals, and can you see that? 5 times 10 to the negative fourth, and if we just move the decimal place, that's 500 microamperes, or if we move the decimal place in the other direction, 0.5 milliamperes, and sure enough, there it is, 0.5 milliamperes. It says milliamperes in the bottom right there. Okay, so we got all that. So now, one little quick experiment I want to show you, just kind of a fun thing. All right, and then we'll end up and we'll move on. Let's put this in resistance mode. Okay, put this in resistance mode. We're going to actually build a resistor really quick. We're going to build a resistor. All right. So a resistor, we were talking about resistors, and we said that they were made out of carbon, right? A carbon powder, right? Mixed with different things usually. All right. So we can actually make a resistor. So we're going to make a resistor, and okay, so we're going to make a resistor. So check this out. So I just have a graph paper in front of me here, and what I'm going to do is I'm going to horizontally here, can you see this? So I'm going to draw out 1, 2, 3, 4, 5. Okay, so 1, 2, 3, 4, 5, and I believe this is 5 squares per inch. So I've drawn out a rectangle 5 long. Now remember, the current, so the resistance of something is going to depend on its cross-sectional area, right? And in this case, we've got a two-dimensional object, but it has thickness, and that's kind of how thick this lead is, and this is graphite. How thick this is as I draw it on here. So since we want to have some kind of methodology here, what I'm going to do is I'm going to go in one direction, and then I'm going to go in the other direction, okay? So I'm just going to fill this in. Just going to fill this in with lead. which is graphite. Okay, so this is conductive. All right. Okay. Okay. So now we've got this object here. All right. Now watch this. So now I've got the ohm meter. All right, and it's on resistance. And let's see if we can actually get some conductivity. So this is 1 inch of our paper resistor. 1 inch of our paper resistor. And I'm going to put it right here and right here. And sure enough, 4.4, 4.2, 4.1 megohms. Okay, so about 4 megohms. Now, let's go ahead and let's thicken up the resistor. So now what we're going to do is we're going to put the material perpendicular. So we're going to go this way, and it'll get much darker, much darker. Okay, straighten this out a little bit. Okay, all right, so we've got 1 inch of material. There we go, we got our meter back, okay? And now it was about 4 meg per inch. The question is, will it be less? And it should be, because we're gonna have more material to conduct through, because we've increased the cross-sectional thickness by, maybe a mil or 2 mils, a thousandth or a couple thousandths of an inch. Let's see what we get. And now look at that. Now we're down to K here, right? So I was really able to put a lot of material on there. So we got 260 K. Now what I want to show you is this. Watch this. So imagine that part of this is a resistor, right? So let's go ahead and let's do this. So I'm going to erase here. Okay, I'm going to erase here. Okay. So I've still got conductivity through this little channel here, right? So we'll put a little extra in there. Okay. So now we've literally drawn two-dimensional resistors. So our first resistor has a resistance of 100K, right? 100K and some change. Our other resistor should have about the same resistance. And depending on how much lead I put on there, okay, about 160K, 160K. Now, what's going to happen when I add them together? So over here we have, get a good contact, we have about 100K. So you can tell when I draw, I must put more pressure to the right. And then over here, we've got about 270K. When we add them together, what do we have? And now look at, that's in megohm now. So it's the 100 and something K and 170, 200K, and now we have this large resistance, and then plus we have this impedance here in the middle. So we've got this little resistor here, which has got very high resistance because it's got less width, all right? And you can see that right there is about 30K. So anyway, we've made a resistor. And now if we start here, look at this. So this starts off and it's 40K, and then as I move to the right, the resistance keeps going up, keeps going up, keeps going up, keeps going up. That is the basis of a potentiometer, which we talked about in potentiometers, and that's what this little device is right here. This little device is a potentiometer. Let's take a quick look. Let's zoom in a little bit with that. And a potentiometer is a variable resistor, and this is a small through-hole device. But basically, you turn this little dial, and then this particular one is 100 K ohms. And so how this works is, basically, it's got either a flat strip like this. In this case, it's semicircular, right? It looks like this. And then this is full of the resistive material, right? Like this. So this is all filled in, all right? And then what happens is there's a wiper, and this wiper, right? Or there's this rotational wiper here, W for wiper, all right? And then we've got one lead coming out here. We've got one lead coming out here, one here, one here, and one here, one here, in either case, depending on which one you have. And so if you measure what the resistance is from the two ends, that'll give you the full resistance of the potentiometer, 100K. But if you go between one of the ends and the wiper, in this case, as you move the wiper, the resistance goes up, and over here the resistance goes down, and that's what a potentiometer is. So it's basically the exact same thing. There's a material that's resistive, and this wiper is pure, it's a conductor, it's metal, it's copper, aluminum, something like that. And as you move it, if you were to take this apart, it would look like this little thing here. So if we take this potentiometer and we were to measure the resistance end to end of the 100K, it should be 100K, all right? So we can do that. So let's take our meter and let's throw away our resistor. Just throw that away. And what we're going to do is we are going to get our board here again. Is the power off? Power is off. Okay. And we're just going to put our potentiometer right inside of here like this. And then to be able to read this, let's go ahead and let's plug something in here so we can kind of get a hold of these signals a little bit easier. So what I'm going to do is I'm going to take this this header, right? And the idea of these is you can cut these, and these are little 0.1 inch headers. So I'm just going to cut that. Again, fabrication. You're always going to be fabricating, all right? And I'm going to put that right there so I can get these signals. Now, when I turn it, it's going to change what the resistance is of the wiper relative to the ends, but the two outer points will stay the same, okay? So let's get our meter here, our resistance meter, our multimeter in resistance mode, right? Okay, and let's go ahead and let's measure the outer resistance. So this should be 100K plus or minus the tolerance of the device. And sure enough, it's 92K. Now, if I change where the wiper is, so I rotate that, it still should be the same, 92K and some change. And oops. Got to make sure I got contact here. There we go. And there you go, 92K, 92.3, all right? Now, if I put it in the middle, roughly, and it's got a little detent there in the middle, and this basically, that's all the way to the right, and then this is all the way to the left. The little arrow points, basically, if you want to think about it, it's going at about 4 o'clock right there, right? And then right there, it's about 8 o'clock, right? If you want to use a clock. All right, so we'll put it in the middle. So we're expecting from the outside to the middle to have about half of 100K, about 50. There you go, 47. And so the rest of it, 100 minus 47, will be on this side. And again, I got to get a good connection. And there you go. And now if I go all the way in one direction, we'll have, what do we got here? We'll have, oops. We'll have almost the full 100K is there, and on this side we should have 0, and in this, or the remainder of it, which looks like it's about 0.5 ohms. And again, if we flip it to the other direction, now we should have 0 on this side, and sure enough we do. All right, 0.3, 0.4 ohms, and we should have the full 100K or close to it, the 92.3. So this is really 92.3. So this is probably a 5 or 10% potentiometer, probably 10%, and that's why it's slightly different. So we can use this device to change currents and voltages in a circuit and adjust them. Very, very cool. And here's another one right here. Right, and these come in all shapes and sizes and every value you can imagine. So that's a potentiometer, and that's really kind of what's going on internally. Okay, so good. Let's finish up, and I'll meet you in the next lecture. And we're going to start looking at Kirchhoff or Kirchhoff's laws, depending how you want to pronounce it, and learn some more more advanced circuit analysis that we haven't seen yet. All right, so I'll see you in the next lecture. Bye. Well, let's go ahead and let's kind of formalize this a little bit with a couple examples in series and parallel resistors, and then we'll stop and we'll pick up with another lecture. All right. Okay. So now let's talk about series and parallel circuits. Now that we have some examples. So this figure right here, and let's just take a look at this because this is kind of useful. What it's showing is that we have the support here, And all a port is, it's just a term in electrical engineering, and it just means kind of you're looking into a circuit from 2 points, usually an input and an output, because current's going to flow in and flow out. And then we don't really care what's on the other side of the circuit. We can basically excite the circuit and figure it out. So we can, we can apply a voltage to it, we can apply a current to it, and then we can kind of figure out what its equivalent resistance is inside of it. And this is kind of called, called computing like the Thevenin equivalent of the circuit. And we're not going to get into that at all. But the point is that if we can simplify the right side of the circuit here, we can compute things that we want to compute on the left side, but first we have to know how to do that. Now, we just learned how to do series resistors. So the resistors in series, the value is simply the sum of the resistors. It's as simple as that. So in this circuit right here, if we wanted to compute I, say we knew what VAB, we knew what the voltage was across A and B, and we knew what R1, R2, and R3 were. We can't directly compute this current unless we know how to deal with R1 and R2 and R3. But we do know how to deal with R1 and R2 and R3 because we can just add them together. We can call that R123 or RRT for R total or R equivalent. Once we do that, now we can compute what the current is. So the current is this resistance right here, R123, divided into the voltage, right? So if you look down here, this says that I equals VAB divided by R123, whatever R123 is. So now we have I. Now we can do other calculations. So for example, say we wanted to know the voltage over the second resistor. Well, the voltage over anything, V equals I times R. So here's I, and then here's R, it's just R2. And say we wanted to know the power. The power equals, remember, if we take V equals I times R, that's Ohm's law, we can cast it in different ways, and power is V times I. So if we replace the V's and the I's, whichever way we want, one version of power is I squared R, remember that, and the other version is V squared over R, and the other version is just V times I. So this time it's just I squared times R. Here's our I, and we just square it times R2, and that would tell us the power. If we wanted to know the power through R3 dissipated over R3, that would be the same term here because I is the same, but now it would be times R3. So all this is showing is just how to make equivalent circuits. You do a calculation, you simplify it. Once you find the value you're looking for, in this case, we're looking for this current, then you put the circuit back to the way it was. All right, so that's the whole point of that example right there. All right, so again, adding resistors in series, you just add their values up. All right, now let's kind of move on here. And okay, so parallel resistor analysis. You can read this yourself, but what I'm going to do is we're going to go through this and deal with this. So this is a pretty complicated figure. I'm not going to describe this on the screen right here. It's just too complicated. We're going to do it in the drawing. But I just want to use it for a moment just to kind of show you what's going on. So in this case, we've got a circuit, and say we have a 5-volt power supply, and we've got two resistors, and R1 and R2, one is 10 ohms and one is 5 ohms. Can we, with Kirchhoff's current laws, with Kirchhoff's voltage laws, and with Ohm's law, can we compute everything about this circuit? We should be able to. We should be able to compute what the voltages are, what the currents are, what the resistance, everything in this circuit. All right, the only problem is we're not quite sure how to deal with the resistors in parallel. All right, and that's what all this math is showing how to do this. So let's actually do this example, and you can see this is quite involved, and then the result is down here. But let's actually do this example, something like this, and inside of our drawing program, and let's see what we come out with. All right, so we've got 5 volts and 10 ohms and 5 ohms. We can use those values, but everything else we're just going to do. We're not going to follow this. It's just an example that you can read later at your leisure. Okay, so let's get in here. Let's go ahead and let's grab this. Delete it. All right. So, and again, I just like to use the notes as an anchor for us so we have something to talk about. But it's always better if we can kind of do things. All right. So here we go, and we're just going to talk about all the different things here. All right. So we're going to say that this is 5 volts. All right. And we're going to go down here, and we've got 2 resistors. And one thing is, I'm going to tell you right now, when you do this kind of circuit analysis, boy, things get really messy. And I'm a very messy drawer and writer, and it's just the way that I am. And if you are, you got to really try to be careful because things will get super messy. All right, and we're going to call this, this is going to be V1, and we're going to call this V2. And I'm not trying to follow the figure, I'm not looking at it, I'm just kind of doing this. All right, and we're going to call this R1, and we're going to call this R2. All right. Okay, and we're going to actually put some values here. So R1, we're going to make this 5 ohms, and R2, we're going to make this 10 ohms. Okay. All right. Now, here's where the good stuff comes. Okay, so what are we trying to do here? Let's write down what we're doing. We want to use Ohm's law, which is what? V equals I times R. Okay, so that's one thing. We want to use our new things, which is KCL, all right, and that's Kirchhoff's current law, right? And that says the sum of the currents, and so this symbol means sum, right? So the sum of the currents into a node has to equal 0. All right, and then we have another thing called KVL, and that's Kirchhoff's voltage law, and it says the sum of the voltage drops, all right, around a loop equals 0. So the sum of the voltage drops around a loop equals 0. So this is all we need to figure all this out, all right? So let's see what happens here. Okay. All right, so the first thing is let's start labeling some things here. And you know, and when you do circuit analysis, a lot of times there's no right way to do it. There's no right way to start it. Just start labeling things and just let the algebra do the work for you. And you'll get enough constraints going where you'll see enough, you'll have so many variables and then so many equations, and then you'll say, hey, I've got enough variables and enough equations to solve this, okay? So in this case, we know what R1 is, we know what R2 is, we know what our voltage source is over here. It's 5 volts. What we don't know is what V1 is and what V2 is, and we don't know what any currents are. So let's start writing some stuff down. All right, so very carefully. So I'm going to call the current coming out of here, right to this point right here, all right, I'm going to call this IS. Now the current coming down here, this also has to be IS, okay, because what comes out must come in. I think we can agree with that, all right. Now, this IS comes in here, and then what's going to happen is some current is going to go this way, okay, and I'm going to call that I1. And then some current is going to have to come through here. All right, and I'm going to call that I2. Now, all right, so let's hold off on the currents for just a moment here and let's talk about voltages. All right, so here's a node right here, and here's a node right here, and again, this stuff, sometimes it's just too easy. The answer just kind of falls out. So this node right here, I'm gonna call this node A, and then this node right here, I'm gonna call this node B. Now, what is the voltage at node A? Well, node A, remember, we can draw a surface like this, and anything in that surface is the same as node A. Well, look at that. The positive of the voltage source is node A, right? Therefore, node A has to be 5 volts. So, again, that surface extends all the way here, right? This surface is all this, right? So no matter what, the voltage right here is 5 volts. Right there is 5 volts. Okay? So I think you can see where this is going. Voltage at B is just ground, which is the other end here, which is 0, right? So right here, this is 0 volts. Right here, this is 0 volts. 0 volts anywhere on this node, right? And again, if you want to just draw the surface of the node, right? What does that look like? It looks like this. Oops. That was a horrible drawing. Everything here is that node B, which is at 0 volts. Okay, So now let's start seeing if we can kind of figure things out here. All right. So one thing is, therefore we have 5 volts over R1 and 5 volts over R2. We can compute the currents through there. So here we go. So let's figure out what I1 is. All right. So let's figure out what I1 is. Let's do it down here. So I1 equals, what is the voltage? The voltage over R1, right, is 5 volts. Okay, so I1 equals 5 volts divided by 5 ohms. Likewise, I2 must equal, what does I2 equal, right? Where's I2? I2 is here. It's this voltage V2, which is 5 volts, and it's over 10 ohms. All right, so 5 volts divided by 5 ohms is 1 amp, and 5 volts divided by 10 ohms is half an amp. All right, so we know that we have I1 and I2 here are these two currents. Now let's do KCL at one of these nodes. So let's do KCL at, say, this node right here. So if we do KCL at that node, what does it say? The sum of the voltage, the sum of the currents, right? The algebraic sum of the currents at the node must equal 0, or the currents entering the node equal the currents exiting the node. What are the currents entering the node? The currents entering the node are I1 and I2, and they must equal the current exiting, which is IS. Okay, so I1 plus I2 equals IS. All right, so there we go. So we know that IS equals I1 plus I2. Okay, all right, and we know what the currents are. So now we have that that solution. So now at this point, we have everything that we would want to compute. So now we could also compute what V1 is, because that's just 5 volts, right? And V2 is 5 volts as well. So now the question is this. All right. Could we combine these two resistances? All right. Could we combine these two resistances into one resistor, do this calculation, just compute what the current is, and then break them back up just like we did with the series resistors, okay? So let's take a look here. All right, so let's take a look here. So now that we have the math, let's kind of break this back up into what was actually going on. So here's I1 and here's I2. So I want to write it back in variable form. Okay, so I1 equals V1 over R1. Okay, I2 equals V2 over R2. But V1 and V2 are the same, all right? V1 and V2 are the same, and they equal to Vs. Okay, so that's one thing, all right? Now over here we have I1 plus I2 equals this Is here, all right? So we have this other equation right here. So we know that the sum of these two things equal this Is. All right. So now let's play with these two things right here. So we have I1 plus I2 equals Is. I1 is V1 over R1, V1 over R1. All right, of course, I2 is V2 over R2. Okay, all right, so now what do we have here that we can factor out and deal with? V1 equals V2, all right? V1 equals, and this equals Is. V1 equals V2, right, which equals Vs in this case, which is the 5 volts. So I'm just going to call it Vs. So I'm going to say Vs plus Vs, Vs over R1 plus Vs over R2 equals Is. Okay, now we're getting there. Now, since we have Vs and Vs, right, we can factor Vs out of this, right? So let's do that. So we have Vs, and now what do we have? We have 1 over R1 plus 1 over R2 equals I sub s. Okay? Now, we're getting there. And so now watch what happens here. So this is going to get interesting. 1 over R1 plus 1 over R2. So see this VS and see this IS? Let's take VS and let's move VS over here. All right. So then we have 1 over R1 plus 1 over R2 equals IS divided by VS. All right. So IS over VS is what? Well, go back to Ohm's law. V equals I times R, right? So R equals V over I, right? But what do we have here? We have I over V. So this is like 1 over R, right? So 1 over R, right? So this is equivalent to 1 over RS. And what's RS? RS is the equivalent resistance of these two resistors in parallel, right? So this is the equivalent resistance. All right, so now let's go up here. So now I have 1 over R1 plus 1 over R2 equals 1 over RS. And this is kind of the result here. So 1 over, that color is just not bright enough. Let's use this one. 1 over RS equals 1 over R1 plus 1 over R2. Okay? This is the result that we wanted to compute. So this says that the parallel combination of R1 and R2 in parallel is equivalent to 1 over R1 plus 1 over R2, or 1 over the parallel combination is equal to 1 over R1 plus 1 over R2. If you play around with this algebra, all right, what you end up with is this. RS equals R1 times R2 over R1 plus R2. And this is what we wanted to get. So the parallel combination of two resistors, R1 and R2, is simply their product over their sum. So, and that's it. So if you want to compute their parallel resistance, it's the product over the sum. Now, in this case right here, so what we're saying is that these two resistors are equivalent to one resistor. We're calling that RS for calculation's sake, and we're saying it's the product over the sum. So that would be 5 times 10 over 5 plus 10 equals 50 over 15, of course, which equals 50 divided by 15. 50 divided by 15 equals 3.33 ohms. So when you have these resistors, there's a couple observations. Whenever you put anything in parallel, the parallel combination of resistors is always going to be less than the smallest resistor that you put in parallel. And also this generalizes, so if you had 100 resistors, 1 over the equivalent resistance equals 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over Rn. All right, but typically we try to do 2 at a time because anything more than that is too complicated. Okay, so now that we know all this, let's go ahead and delete that. And now let's just do a simple example. Okay, let's do a simple example. Here we go. So let's say that we have a circuit, and let's say that that circuit is 5 volts here. All right, and let's say this comes down here. All right, and first let's use some common sense. All right, so here's R1 and here's R2. Now, what is our equation? We know that R parallel or R equivalent or R total, so we'll just call it R parallel, equals, for two resistors, R1 and R2, R1 times R2 over R1 plus R2. All right, and then another way that this is written is R1 in parallel with R2 equals. You say put parallel lines. All right, so this is our equation. All right, and this gets it done. Okay, so now let's figure this out. Let's say that this is 100 ohms. Let's say that this is 100 ohms. All right. Now, what I want to do is I want to use common sense here first, and then we're going to do the math. I've got two 100 ohm resistors. Okay, so now if I just had one 100 ohm resistor, forget the two, if I just had one 100 ohm resistor, what would be the current in the circuit? It would just be 5 divided by 100. Okay, so I would equal 5 volts divided by 100 ohms if we just had one of those resistors, right? So 5 divided by 100 is 50 milliamps. 50. So the 5 volts divided by the 100 ohms is 50 milliamps, and that would be if there was just one resistor in there. So 50 milliamps if there were one resistor in there. Okay, now, so we have the one resistor in there, and 50 milliamps flows through that side of the circuit. All right, the voltage here, so now this is super key. The voltage here from this point to this point is 5 volts, plus to minus 5 volts. Now, what do we know? There's 50 milliamps flowing through this right now. All right. Now, we go and we add this other resistor that's identical to it, right? And it's 100 ohms. All right, so it's basically we've got this battery powering this circuit, and we just add something else to it. So what's the voltage over this resistor? Well, it's still 5 volts, right? It's still 5 volts. There's 5 volts right here. It's got to be, right? 5 volts. So what's 5 volts divided by 100 ohms? It's again going to be 50 milliamps. So again, we're going to get 50 milliamps flowing through this part of the circuit. If we got 50 here and we got 50 here, what must be coming here? 100 milliamps. And then what must be coming out? 100 milliamps. So even though there's 100 milliamps coming in and 100 milliamps coming out, it's splitted 50-50. And we constrained it by just saying, pretend there's just one part of the circuit, then let's add the other part of the circuit. So let's try and figure out what the equivalent resistance is of this. Okay, so here we go. So let's use Ohm's law. We're going to tricky do this. All right, V equals I times R. Do we know what V is? Yes, that's 5 volts. Do we know what I is? Yes, it's 100 milliamps. And we're trying to find R. So we divide both sides by the 100, right? Equals R. So equals R equals 5 divided by the 100 milliamps. So 5 divided by 100x minus 3 equals 50 ohms. 50 ohms. So the equivalent resistance, this R parallel, equals 50 ohms. We figured it out. It equals 50 ohms. So basically, every time you add another resistor, you're creating another current path, all right? And so since different currents are flowing through these different paths, the equivalent resistance of the whole system is, of course, going to change. And the equivalent resistance is going to be less. Now, here's our equation. Let's see if it matches. So our equation says that R parallel equals R1 times R2. What's R1? 100 ohms times R2, which is also 100 ohms, divided by R1, 100 ohms, plus R2, which is 100 ohms. 100 times 100 divided by 100 plus 100, okay? Just let the calculator do it. 100 times 100 equals, divided by 100 plus 100 is 200, equals 50 ohms. So look at that. All right, so we kind of did this without knowing the equation or the formula for the parallel resistors, came up with 50 ohms as the equivalent resistance, then we went and used the formula and we got the same thing. So we basically have proved that this works no matter what. And so now, here's the thing. When you want to simplify a circuit, so let's do one last example. All right, one last example. All right, so let's draw something fairly complicated. All right, here we go. So let's say, and we'll do this in the next lecture. We'll actually, not this exact circuit, but we'll draw something, or maybe we will. Maybe I'll keep it up here. All right, and let's say we have this, and we got this, and then we got this, and we got this, and now we got this. All right, and then we got this. Okay. All right, and this is plus, this is minus, this is V1, this is plus, this is minus, this is V2. We got R1, we got R2, We got R3, let's call this R4. We got this R5, and this is R6. And this would be plus to minus, plus to minus, plus to minus, plus to minus. And we'll call this, each one of these will be the same plus to minus. And let's just make our voltages, why don't we make them blue? We'll call this V1, call this V2, we'll call this V3, V4, V5, V6, all right, and then we've got some currents here, all right, and the current, and this is where it's going to get messy a little bit. So the current, so what do we have here? We've got current coming out here, right, coming out of our sources, and then this current is going to split, right? So we got this current here, and now this current is going to split, all right, and some of it's going to come down here, and then some of it's going to come down here, and then it's going to come back together. And then that's going to be that same current again, coming back through here. All right, so now the question is, if I start giving you some of these values, can you compute what all the voltages are and all the currents are based on your circuit analysis techniques, KVL, KCL, and knowing the rules for parallel resistors and series resistors? So look here, we know how to add these resistors up, we just sum them. Now, what about this? Well, we've got series and parallel, but first you do the series, turn these into one resistor, then do that combination with this one as a parallel, then that combination with this one as a series. Then you can turn this whole thing into one simple value, then compute the current, and then with the current, then you can start running through and doing this. All right, so anyway, let's leave this for next time. We'll do this as a circuit analysis to kind of refresh, and then we'll talk about the next material, and then we'll move on. So anyway, I'll see you in the next lecture. Bye. All right, welcome back. We are on the next lecture, and in this lecture, we are going to continue talking about circuit analysis techniques. We left off last time with a circuit, and we were going to kind of simplify that. And so we're going to do that first, and then we're going to kind of move into another topic, voltage dividers, which we already actually know how to do, but we're going to kind of formally look at their construction and then how to make the computations to figure out the voltages on the voltage divider. And we'll figure this out in a minute and what that even means. But first, let's go back to our drawing here. Now, hopefully you're starting to get pretty excited because we have a lot of tools now, and now you know, we can really start to figure out what's going on in these circuits, at least with the DC analysis. We don't know too much about doing analysis with capacitors or inductors, but we're getting there. And now the cool part is that when we're doing digital electronics and we're kind of setting things up, we can use a lot of these techniques to do more or less 90% of the work we need to do with any kind of analog-ish setup for our digital circuits, you know, power, supplies, current limiting for LEDs, I/O devices, and so forth. So we really do have a lot of information. And it's important to be able to do these simple techniques, or at least know how to do them, and maybe you have to go back and figure it out. Anyway, all right, so let's take a look at what we have here. So let's see what we got going on. So we ended up and we drew this circuit. And so, you know, the question might be, given a circuit that looks something like this, and you know, and here's the thing, like when you're doing a course like this, we're just making circuits up, right? And no one's really ever going to say, hey, I've got two batteries and I got these two resistors and I got all this, compute all the currents and the voltages. But the techniques are applicable to something that might look like something like this. So for example, say like you have you know, two 6-volt batteries and you want 12 volts. So you say you're going to put those in series. And then maybe, you know, you have two different resistors for some reason. Maybe one's a load resistor, maybe something is a is a heating element, who knows, and then you need to split the current. And so, you know, the whole idea is maybe this would represent something that you have to do. So anyway, you know, we have to make something up to analyze, and this is just one way to do it. All right, so first thing is, let's go through here and let's just put some numbers on things. So if we want to do actual calculations, we will be able to. So let's go ahead and let's say that V1 and V2, let's come up with some battery values here. So we know that our standard, our standard AA, AAA, quadruple A, C size, and D size are all 1.5 volts. We also know that we have the 9-volt prismatic cell, and then you've probably also seen the big 6-volt lantern batteries, all right? So we've got all those different voltages, you know, kind of off-the-shelf batteries. So why don't we say, just for fun here, let's say that we want something with a fairly high voltage. So let's make these both 9 volts prismatic cells. So these are the 9-volt batteries that we've used in some of our experiments. So now we're going to get 18 volts here when these two things add up. And let's start putting some values on these resistors. So let's go ahead and let's say that this is, say, 10 ohms. And let's say that this is 20 ohms. And let's say that this one over here is 100 ohms. And then let's say that this one is 200 ohms. And let's say that this one is 1K. And let's say that this one is, say, 10 ohms. All right. So we've got all these different resistors here, and we've got our power, and we've got a circuit that has both series resistors and it has parallel resistors, but they're kind of in a mess because we've got series and parallel. So it's like, where do we even start? So our goal would be to be able to analyze this entire circuit and tell exactly what the currents are everywhere and the voltages are everywhere. All right? All right. So what I'd like to do is I'd like to kind of do this in pieces here, and we're going to see if we're going to have enough room to be able to do this on here, but let's see how this goes. All right, so the first thing is, whenever you have voltage sources in series, as long as their polarities are correct, the voltage is going to add up, right? So what we're going to get here is at this point right here, and let's create a ground here. We'll call this ground. All right. And so at this this point right here, you know, and we could call this node ground, right? Or we could just call it the ground node. This is going to be 0 volts, we're going to say. So if we're at 0 volts right here and we go through this battery, we're starting at a low voltage, we're going to a higher voltage, we got 9 volts, and now we add another 9 volts. So up here, and let's actually label this, we'll label this node A, and we'll label this node B. All right, and again, what does node B look like? Node B is right here, but it encompasses everything here, that entire surface, right? Okay, so there's node B, and we need another node right here. Okay, so let's call that node C. And we know that this is at ground. Where's another place we need a node? We need a node right here, huh? So let's put another node right there, and we'll call that node D. Okay, all right. So we have all our nodes here. Okay, up here we have, very simply, we can by inspection, we can say that this is 18 volts. All right, so there's 18 volts right here. That's the voltage here. All right, so we've got 18 volts there. All right, now, what we want to do is this. First, we want to figure out what this current is right here. So this outgoing current right here. So let's give this a label. So I'm going to call this, I'm going to call this let's call this I12 because it's going through resistor 1 and 2. So we're just going to call that I12. Now, the current coming back through here, all right, that should be the exact same as this current because the same current that goes out is going to come back here. So we can call this current I12, which should be equivalent to, if we wanted to call the current going through R6, we could call that I6. They should be equivalent. So we only need to figure out this one current right here. So if we can figure out the outgoing current here, and then if we could somehow simplify this whole business right here, and then do the computation, we could then backtrack and figure out what everything else is. Okay, so let's look at some techniques here. So let me show you some stuff. So the first thing is, can we collapse these two resistors into one resistor, right? So we can take these two right here, and we can say by series resistors, we simply add R1 and R2. So we can say that this combination right here, R12 equals R1 plus R2 which simply equals 10 plus 20, which equals 30 ohms. So that's one resistor and R12, and that's 30 ohms. That was easy enough. Now we've got R3 and R4, and we could just, again, add these two resistors. We'd call it R3, R4, right? So we could come here, and we could call this R3, 4, and that would simply be R3 plus R4, which is R3 plus R4, which equals 200 plus 1K, or 1.2K, all right? Okay, so now those have been collapsed into a single resistor. And now we just have R5, which is 100 here. We've got R6, which is 10. Okay, now we've got one resistor here. We've got this R34 here. We've got R5. Now let's do R34 and R5. So let's put those two together as a parallel combination. So what I'm going to do is I'm going to call this R34 in parallel with R5. All right, and how do we do that? It's their product over their sum. All right, so R34 times R5, so R34 times R5 over R34 plus R5. That's the parallel combination. So this giant resistor right here, right, this entire combination, so now we can maybe, let's use a different color here. So this entire thing, all right, this entire thing here is just this value right here, R34 in parallel with R35, all right, whatever this is, okay? So we could call this R345. Let's just do that. So we're going to call that R345, all right? So that's all of that. Now we have this R6, which is again now in series. So now let's look at what we got. So we have one resistor right here, which is just this R12. So there's one resistor. Now we've got one resistor right here, which is this R345. And then we have one resistor right here, which is this R6. And then we have one voltage source here. So what does our equivalent circuit look like? Let's draw it down here, we'll draw it small. So what we really have now is we have one voltage source, like this, coming through this resistor here. What's this? We're calling this R12, and this happens to equal 30 ohms. Then we're coming down a resistor here, and that's this big combination here, which is R345, which we're going to compute in a second. We'll actually do the computation, R345. Then we've got R6 here. There's R6, and then there we go back around. There's R6, which just is 10 ohms still. All right, so, and we know what's this battery, this equivalent battery is 18 volts, all right? And the current going through this R12 thing, this current going through here, right, is the same current that's going through this entire combination of everything. All right, so no matter what, we're getting the same current here. But once we get inside of this, we're going to have to split it apart. But right now, doing this computation, it's the same current, right? And that same current is this I12, all right? So this is I12, same current, which is the same as I6. All right, so now let's do some calculations here and let's figure this out. And is that the right color there? Nope. I think it's this one. Yeah. Okay, so what do we have left? We have R12, we have R6, we have our battery here, which is V1 plus V2. We're looking for this R345, so let's go deal with that. So R345 is R34 in parallel with R5. So R34 was 1.2K. So it's this formula right here, all right? So let's write this down. R345 equals R34, which is 1.2K ohms, of course, times R5, which is 100 ohms, over the sum of these two things, which is 1.2K plus 100. All right, so let's get our calculator out. So we have 1.2K times 100 divided by, now be careful, you know, if you don't use a calculator a lot or you haven't used one in a long time, when you say divide, right, it's going to first divide by 1.2k. We want to divide by the sum of 1.2k plus 100. So you can use parentheses. So most calculators have parentheses, and I don't know if you can see it here, but I'm going to parenthesize the denominator to make sure that the order of operations is what I intend. So divided by 1.2k plus 100, all right, equals 1300 ohms, if you can see that. All right, so 1300 ohms, all right, is the parallel combination and series combination of that entire thing there. And let's do that one more time. 1.2 x3 times 100 equals divided by 1.2 x3 plus 100. Okay, yeah, and so that's incorrect. I made a mistake. And so why I did that was whenever we have a parallel combination, it should always be smaller than the smallest resistor. So when it said 1300 ohms, I'm like, huh, we have a 1.2K, so how can we have something that's larger? And so again, when I was telling you that, I pressed the parenthesis wrong and got the wrong answer. So our answer for the parallel combination better be smaller than the smallest resistor in the parallel combination. The smallest resistor is the 100 ohms, so it better be smaller than 100. So when I do it correctly, I get 92.3 ohms. That is the correct answer. So if that's what you got, that's what we should get. So we got 92.3. So we got 92.3 ohms. Now, this is way too much precision. These resistors are probably going to be 5 or 10%, so I would probably just call that 90 ohms, but we'll just keep it 92.3. There's no need to throw away the accuracy just to throw it away because we're just doing math. All right, so we're going to do 92.3 ohms here. This way everything will kind of add up. Okay, so now we've got this equivalent circuit, and the whole idea of it is what we just did was we kind of, let's get a different color here, we kind of said, what does a circuit look like to the right of this dotted line? And what does it look like to the left? And if we can just figure out what the impedance is to the right as one big bulk resistor, then we can compute what the current going out is. And we know that that current's going through at least R1 and R2, and we know it's going through R6. So we can figure those things out. Then we can deal with what's going on in this parallel combination here, all right? Okay, so let's go back here and let's keep doing the math. So here we are. So now we just have a series combination of resistors, and we've got a voltage source. This is easy, right? So series, we're just going to add these things up. And so we've got 30 ohms plus R345, which is 92.3, and try and follow me with this. So hopefully you catch a mistake and you can telepathically through time make me fix it like we just did, which was good. All right, so we have 132.3 ohms. So 132.3 is the total resistance here. So I'm just going to say this R total is 132.3 ohms. And let's see if just kind of do a little, fact check here. So 10 and 30 is 40, 40 and 92 is 132.3, so that's right. Okay, now we want to figure out what the current is, and let's put down Ohm's law here. Just scratch that down. V equals I times R, so we want I, so that's V over R. What's our V? 18 volts divided by that value. Okay, so we're going to have 18 volts divided by 132.3, right? And that gives us 0.136 amps. All right, and I think I'm going to want that in milliamps, so that's 136.05. I'm just going to call it 136 milliamps. So this current right here is 136 milliamps. All right, so the current right here is 136 milliamps. The current right here is 136 milliamps. Now, given that, we can use KCL or KVL, Kirchhoff's current laws or Kirchhoff's voltage laws, and we can start pinning down our solution here. All right, so I know this is getting messy, so just bear with me and just kind of focus on it. And this is what all electrical circuit analysis looks like. And then when you go to AC analysis, boy, it gets way worse. It's just a mess. Okay, so let's start off here, and now what I want to do is this. We know what the current is right here, so let's write that down. It's 136 milliamperes, right? So let's just write that down, 136 milliamperes. And we know right here it's 136 milliamperes. Given that it's 136 milliamperes, we can compute what the voltage drop is over these two resistors, and we can pin down what this node B voltage is, right? So if we know that we're at 18 volts here and we're going to drop over these two resistors voltages, then we know after those drops that voltage is what's going to be on node B. So let's do it. All right, so we can do these simultaneously or we can do them separately. So let's just do them separately so we can figure out what the voltages are. All right, so again, V equals I times R. So 136 milliamperes times 10 ohms. That is going to be the voltage V1, all right? So 136 milliamperes, let's do that. 136 x negative 3 times 10, all right? So that's 1.36 volts, right? 1.36 volts. That equals V1. This is 20 ohms, so it should be 2 times that, right? It's twice the resistance, same current, twice the voltage. So that should be 2.72, right? 2.72. 2.72 volts is V2, right? And just multiply by 2.72, just check ourselves. When you're doing this stuff, a lot of times you'll make arithmetic errors, you'll make sign errors, and you just get stupid. So check your math. All right, so 2.72 volts. Now, if we're at 18 volts right here, all right, then if this drops 1.36, then we're at 18 minus 1.36, and then at this point we're at that minus another 2.72 will be this voltage here. So 18 minus 1.36 is 16.64. So right here, this is 16.64 volts, all right? And then right here, then minus another 2.72. So we've got 13.92. So this is 13.92 volts. All right, so now we're doing pretty good. We've got this thing almost completely constrained. All right, so now let's avoid this for a second. This is nasty in here. Let's go down here. So now, do we know the current going through here? We do. It's 136 milliamperes. We know that something happens in here. It's going to split up. But here, we know that's 136. What's the resistance here? It's 10 ohms. What's 136 milliamperes over 10 ohms? Oh, it's 1.36 volts. So we know that V6 must be 1.36 volts is what's going to drop over this V6 right here. Okay, now let's go in the opposite direction. Let's see if we can figure out what the voltage is at this node. So what's the voltage down here? Right here, well, that's just 0 volts. And if we drop 1.36 volts to here, to ground, that must mean that we must be at 1.36 volts at node C. So node C actually equals 1.36 volts. The voltage drop over the resistor is the same voltage as this node because the other end of the resistor is at our ground reference. All right, so now we've really got this thing constrained. Up top here we got 13.92 volts. Down bottom we got 1.36 volts. So the voltage differential over this series parallel combination is 13.92 minus 1.36. So now we really got this thing. So 13.92 minus 1.36. Now, I want to bring something to your attention. We're doing this, but do you see me formally doing KVL and KCL? No, I'm not writing equations down, but I'm actually using the techniques piece by piece intuitively, and it's very easy. Just work at it, right? Just step by step, and you don't have to write a bunch of equations down. I'm just working the problem and kind of, like figure this out, constrain this, and so it's much easier. See, it's not very hard at all. It's like very easy. 13.92 minus 1.36 equals 12.56. Okay. So over this this area here from node to node, we've got 12.56 volts, all right? So let's just put that, let's see, where can we put that? We are running out of colors, we're running out of everything. So let's just put that, let's not use that color, I want to use a different color so we can actually see it. How about red? We never use red. All right, so here's some red, we'll go like that. So we're going to put that as 12.56 volts. All right, bear with me. 12.56 volts. Okay, now we're in business here. So now we have our R5. What's the voltage over R5? Well, it's 12.56 volts. What's the resistance of R5? It's 100 ohms, right? Okay, so let's figure out what the current is. Current, V equals I times R, so current equals V over R, right? What's the V? 12.56, 12.56 divided by R, which is 100, right? And let's get that into milliamps. So that's 125.6 milliamps, 125.6 milliamps. All right, so through this branch right here, and let's just put it in yellow, all right, is 125.6 milliamps. That's this branch right here. 125.6. Okay, this is almost too easy. Now, I'm sure you've got your hand up and you know exactly what to do. If 125.6 goes this way, let's use Kirchhoff's current law intuitively. So we got a current coming in, and then we got two currents coming out. What's the current coming in? It's 136 milliamperes, right? So the current coming in minus the current going out equals 0, right? So let's just write it right here. So let's write it right here. 136 milliamperes, right? And then we could say minus the currents going out, but instead, let's just say equals the two currents going out. Let's call this current right here, let's give this a name. We're going to call this I34, which is what we want to find, plus the other current, which is, it's I5, but we know it's 125.6 plus, and then this thing's kind of in my way here, so I'm just going to say 125.6 milliamperes. Therefore, we can compute what I34 is. It's just this difference of it, and that makes sense. Whatever current doesn't go through R5 must go through the R34 branch, okay? 136 minus 125.6 equals 10.4 milliamps. So this current right here is 10.4 milliamps. All right, so we have got 136 coming in, 125.6 splits off this way, 10.4 splits off this way. When they come back, they recombine. Again, we get the 136 coming through here, and then that's it. We have all the currents, we have all the voltages, and now if we wanted to compute the voltage, we know what the voltage is over here, that's 12.56. If we wanted to compute the voltage over V3 and V4, well, what's that? That's just the current times the resistance, right? What's the current? 10.4 milliamps. 10.4 milliamps times V3, which is 200 ohms, all right, 10.4 milliamps times 200 equals 2 volts. So we got 2 volts over this guy. So this is 2 volts right here, and 2 volts over this. And if there's 2 volts over this, there better be 12.56 minus 2, or 10.56 over this, roughly. But let's just do the math, right? So we've got 10.4 milliamps times our resistance of 1K, and we've got 10.4. Oops. And so we've got 10.4 volts, right? And 10.4 volts. And so there's a little bit of a discrepancy. Why? Because we've been rounding off and truncating some of our values, right? We haven't been going all 3 decimal places. But that's it. So now we've completely analyzed the circuit. We found every current, every voltage, everything. We know it inside and out, and that's exactly what it's going to do. So if you were to build this on the bench, plus or minus the tolerances of the resistor, these are the results that you would get. So anyway, you know, I want to keep going, but let's take a quick break. Let's come back in the next lecture, and we're going to talk about voltage dividers. And then we're going to move on to some other stuff. But I think this was, you know, we really, you know, burnt our brains on this, and I want to take a pause and take a little break, and then come back, and then we'll go right back into voltage dividers because it's very similar to what we just did. But anyway, you know, watch this video again if you have to kind of follow the whole thing. But this is the process. And the process is use KCL, use KVL, use Ohm's law, but do it intuitively. You don't have to start writing equations because then you're like, oh, what do I write? I don't know. So, but you just start, what do I know? I know a voltage, I know a current. If I could figure this out, I could figure out the total current, then I could figure out at least a couple voltages, then I could, you know, and you do it this iterative kind of hierarchical way, and then you can solve it very easily instead of just going for it and writing a bunch of equations, all right? So it's not as bad as it looks. Now this looks horrible. If you came into a class and saw this, you'd be like, oh wow, what is going on here? But notice there's nothing more than arithmetic here. Very, very simple, but you got to do it step by step. All right, so anyway, so good job. I'll see you in the next lecture, and we're going to pick right back up with voltage dividers. All right, bye. Okay, so welcome back, and now we're going to kind of continue on with our discussion of circuit analysis. And we actually already have done voltage dividers, and we've seen them in a couple different examples. And the analysis that we just did, that big analysis, let's take a look at that. That's still up here. So we just did this analysis. We actually did a voltage divider. So this section here relative to this section is a voltage divider, and this section relative to this section is a voltage divider. So now what we're going to do is we're going to kind of formally take a look at this in a simplified way so that we can use voltage dividers as a tool. And you probably heard this term before, voltage divider, when people are talking about electronics or engineering. And they're a very simple tool, nothing that you don't know how to do already. So, but it's just a certain configuration of voltage and resistors that you can use to kind of, get an output or get a voltage that you want. All right, so you can go ahead and the notes, you have the notes that you can read here. So you can read through these if you like, but we're just going to kind of jump right into this and take a look closely at it. So one thing is that when we're doing voltage dividers, we're typically talking about just two resistors, all right? So we've got an R1 and we've got an R2. All right, and so the problem is say you have a voltage. Maybe that voltage is 10 volts, maybe it's 5 volts, maybe it's something else, and you want to reduce that down somehow, and so that you can use it in maybe a different part of the circuit, or maybe an amplitude of something is too high and you want to scale it down. That's what a voltage divider is for. So let's take a look at this circuit here, and let's see if we kind of can analyze what's going on here. All right, so we've got a voltage V and it's plus to minus, and we've got the nodes A, B, and C here. All right, we've got two resistors, R1 and R2. All right, so right away we know that we can compute what the current is. So V equals I times R, so I would equal V over the sum of R1 and R2. All right, so we could immediately compute what I is, and then we could compute what the voltage drop V1 is and V2 is by multiplying that I times R1 and R2. So that's very simple. That's just Ohm's law. So that just, we know how to do that. So that's what's kind of going on right here. We're just saying that I equals V over R1 plus R2, all right, because these are series resistors. All right, then similarly, we have, again, we rewrite to Ohm's law here, and then we can say that the voltage over V1 is simply that current, right? And that the current is the V over R1 plus R2 times R1. And the voltage over R2 is simply that current, which is V divided by R1 plus R2 times R2. Everything is the voltage, the current times the resistance, current times the resistance, and that's it. So now if you look at this model here, right, and you've got these two resistors, R1 and R2, then it's kind of like, oh, you can kind of simplify this a little bit and kind of make up a little, rule of thumb for converting voltages and creating new voltages. And so when we do that, we can kind of simplify this and we kind of come up with these equations right here that says that V1, the voltage drop over this R1 resistor, and then V2, is simply R1 times V over R1 plus R2, and V2 is R2 times V over R1 plus R2. So that's it. So really we didn't do anything. We just observed, right? If we compute the current in a two resistor loop, and then we figure out what the voltage drops are over each of those resistors, then these simple equations can kind of tell us what's going on. So so you can write those down if you want. They're very easy to derive. So let's go ahead and let's see if we can use these equations to kind of solve for something, all right? So let's go ahead and see what we have here, all right? And let's see if there's anything exciting here. All right, so let's go ahead and let's do an example, and then I'm going to show you some other things about it. But let's do a couple examples and let's actually go and build something here. All right. So first thing is let's take these and let's remember what these are. So this says the voltage drop 1 is simply R1 times V over R1 plus R2, and the voltage drop 2 is simply R2 times V over R1 plus R2. And this is just the current each time, right? Okay, so let's go ahead and let's go back to our drawing program here. Let's delete all that. And let's run through and see if we can actually do this in a real example. Okay, so the first thing is let's draw something. And let's draw with a voltage source this time. And let's be tangible. Let's call this 12 volts. Okay. And now let's say that, we've got this 12 volt signal maybe, or this, DC 12 volts, and we want to get, say, like a lower voltage off of this. All right. We need like a 5 volts or something like that. So we say, hey, let's use a voltage divider. All right. And we go through here, and then we've got R1 here, and we've got R2 here. All right. And we know that we're going to have some voltage drops over here, V1, and we're going to have V2. And then, of course, we're going to have our current that flows through here, flows through both resistors. Let's not go through the symbols there. Let's try and get a little bit cleaner. And let's just call this I. And we could call this I, 1 or I2. They would be the same, right? So we'll just call it I. Okay. So now, what do we know? Well, let's write down Ohm's law again. And let's compute what this I is in the circuit. And we can call it lowercase I or uppercase here. We'll just call it I. And it equals the total voltage, V, which is 12 volts, over the total resistance, which is R1 plus R2, right? R1 plus R2. Let's go ahead and let's put some values for this. So let's say that R1 is, let's say that this is 20 ohms. And let's say that R2 is 100 ohms. All right, so that would be 20 ohms plus 100 ohms. All right, that would be our current. So let's get out our calculator. So 12 divided by quantity, 20 plus 100 equals 100 milliamperes. All right, so we've got 100 milliamperes there. All right, 100 milliamperes. All right, so that's our I, and now we can figure out each of these voltages if we want. It's just 100 times 20 and 100 times 100. So 100 milliamperes times our 20, so if we just take that times 20, that's going to be 2 volts. So we know that V1 is 2 volts, and now we know that the voltage drops in a complete loop, sum up to 0, right? That's Kirchhoff's voltage law. So we could just say 12 minus 2 equals 10, or we could do it, right? So we know that that's going to be 10 volts, or we could just take the 100 milliamps times 100 ohms. That's going to also give us 10 volts. So everything is as it should be. So we just figured this out by kind of an analysis. Now let's see if the equations work themselves. So the equations say that V1 equals R1 over, or actually R1 times V over R1 plus R2. And V2 equals R2 times V over R1 plus R2. All right, so really all this really is if you think about this, it's just a ratio. It's just a ratiometric calculation. And if you have these two resistors, the voltage drop over this R2 is going to be the proportion of R2 of the total sum. That would just be R2 over R1 plus R2 times the total voltage. And the same thing is with this one. This would, the voltage drop over this would just simply be R1 over the sum R1 plus R2 times the total voltage, right? And that's all these equations do. So let's plug them in here. So V1, let's just do it right here if we can, is R1, which is 20 ohms, times V, which is 12 volts, over R1 plus R2, that's 20 plus 100, is just 120 ohms. And the next one is R2, which is 100 ohms times 12 volts. And again, over the same denominator, 120 ohms. So let's do the math. The first one is 20 times 12 equals, divided by 120 equals 2. So this equals 2 volts. So sure enough, that checks out. And let's do this one. 100 times 12 is, again, 100 times 12, we know that that's 1200 divided by 120 divided by 120, and that's 10 volts. 10 volts. And that checks out, right? And so both of these give the exact same results as the analysis. So these little modeling equations, right? If you have a circuit that looks like this, you can just use these to compute what these voltages are here, all right? And now, and then likewise, Notice one thing that's kind of interesting here. No matter what the values of the resistances are, if the ratio of the resistances is the same, you're going to get the same voltages. So for example, let's go and let's change it to 200 ohms and 1000 ohms. All right, let's get rid of these and let's redo the calculation. We'll redo it over here. So let's go ahead and do it. Let's V1 equals R1. What's R1? 200 now. 200 ohms times V. What's V? Still 12 volts. Over the sum of these, which is 200 plus 1000. So let's just write it out this time. 200 plus 1000 ohms, or 1K ohm. All right. That equals whatever it equals. V2 equals, what is that? R2. What's R2? 1000 ohms. Times 12 volts over the same denominator, which is 200 ohms plus 1000 ohms. All right, so let's do the math. 200 times 12, 200 times 12, 200 times 12 equals 2400 divided by the sum of 200 plus 1000, which is of course 1200. So that gives us 2 volts. Again, let's do the bottom calculation here. 1000 times 12, 1000 times 12, of course, better be 12,000, divided by the denominator, which again is 1200, 200 plus 100, 1200, and that better be 10 volts. And again, notice that they are the same. Right here, there's our 2 volts, and there's our 10 volts. All right, and the exact same as we calculated. So the ratio doesn't matter. So, okay, so wait a minute. This should set off some red lights. So if the values of the resistors don't matter, then what's going on here? Why are there an infinite number of resistor values? The reason is the voltages will stay the same, but the current changes. So this current I does indeed change, but since that same current drops over each one of these or goes through each one of these resistors and generates a voltage, right? The voltages stay the same, but the current is actually less. Let's figure out what the current is. Now in the first case, when we had the 20 and the 100 ohms, right, we figured out that it was 100 milliamperes. So we increase the resistances by a factor of 10. Our intuition should tell us that V equals I times R is a linear equation. The current should now increase by 10 or decrease by 10. Decrease by 10, because we're going to increase the resistance. Let's see. So what is the current? Well, it's simply the voltage divided by the total resistance. What's the voltage? It's 12 volts divided by what's the total resistance? 1200 ohms now. 1200 ohms. And now when we do this, we have 10 milliamperes. So now when we do this same equation, I equals 12 volts over 200 ohms plus 1000 ohms, we get 10 milliamps. All right, so we had 100, now we have 10. So we decrease the amount of current. So what use is this? So obviously, if you have a large signal or a large voltage, you can use a voltage divider to decrease and scale the voltage. You can scale it down. You can never make it bigger, right? We have to use amplifiers or transformers to do that. So you can't make it bigger, but you can make it smaller. Now, when you pick your resistors to do this voltage divider, the question is, well, how do I pick them? Do I just pick one of them, and then solve for the other one? And then what scale should I make them? The answer to the question is, well, how much current do you want flowing in the circuit? All right. So one way to do this is to say for example, we wanted to set the current to, let's say that we wanted to set the current to 1 amp. Okay, so we want 1 amp of current in the circuit. So that's what we want, all right? And so let's just write that down. We want 1 amp is what we want. We know that V equals I times R, and we know that we have a voltage of 12 volts, so let's just figure out what the resistance would be. So 12 volts equals our current, which is 1 amp, times our resistance, and therefore divide both sides by 1 amp, and we have our resistance equals 12 ohms. So we know that the total resistance of R1 and R2 needs to be 12 ohms to set up the current of 1 amp. Now all we need to do is figure out what the values of R1 and R2 are. And there's a lot of ways to do this. we've got, some ratios here. We've got, a number of different ways that we can do this. And so, I'm not going to go through all of them. We'll just kind of look at the most obvious way. So, one way to do it is we can simply look at one of these equations here, right? Either one of these equations will do the job. And so the first equation says that V1 equals R1 times V over R1 plus R2. All right, so V1 is, we want to maintain the voltage ratio. So the voltage is going to stay the same. So we're going to get 2 volts equals R1. That's what we're looking for. What is the R1 that makes this true? Times V, well, that's just the 12 volts, over the total resistance R1 plus R2, but we actually know that that's 12 ohms, right? So we already know what that value is. All right, so now we can simply simplify this, and we have 12 volts over the 12 ohms, that's just 1, and then we've got R1, and then this is going to, this is 2 volts here, so R1 is going to end up being 2 ohms. All right, so so in this case we could run this through if we want, but regardless, the volts are going to cancel out and we're just going to be left with ohms here. All right, so R1 is going to equal 2 ohms. All right, then we can do the same thing over here, and we have V2. So what's V2? It's 10 volts, and that's what we want. And then R2 we're trying to find, and times V again, which is 12 volts, over the total resistance again, which is 12 ohms. And again, if you just move these things around, you're going to end up, the 12 and the 12 cancel out, the volts cancel out, and the ohms invert, and then we just get, this just turns to 1, so we just get R2 equals 10 ohms. All right, and that makes sense. If we had 100 milliamps, if we now just decrease the resistors again, instead of 20 and 10 ohms, 100 ohms like we did them, now they're 2 and 10 ohms. All right, so and again, you can look at these ratios and figure things out as well. So the whole thing here to remember, let's erase all this. Let's just erase all this so we can see here a little bit better. The whole thing to remember about voltage dividers is this simple little fact here. You've got 2 resistors like this. We've got a voltage V, which is the same voltage over here, right, to ground, right? This is V right here as well. And we're calling this R1, we're calling this R2. This is going to drop plus to minus. This is going to drop plus to minus. We call this V1. We can call this V2. The bottom line is this, is that the current through here is a function of the sum of these 2 resistors. So the voltage drop is linear. So whatever we have as the voltage over here, part of it's going to drop over R1 and part of it's going to drop over R2. The part of it that's going to drop over R1 is simply R1 over the total resistance, which is R1 plus R2. The total, the voltage that's going to drop over R2 is R2 over R1 plus R2. This is just very, very simple ratios. It's just R1 over the total sum and R2 over the total sum. And then we scale that times the voltage. V times that, right? And this whole thing here is going to equal V2, and this whole thing here is going to equal V1. So again, just realize that it's just simply the resistor over the total resistance, the other resistor over the total resistance, and times the voltage. That percentage of the voltage is going to drop over each of these resistors. Now, I want to bring your attention to something specific though, and that is the voltage at this node right here. You want to be a little bit careful about this. These voltages we compute, V1 and V2, they're the voltage drops over each one of these resistors independently. But they're not the voltage at the nodes. That's always relative to ground. Now, if you have a circuit like this where R2 ends up at ground, then V2, right, is identical to this node voltage, right? So whatever V2 is, say for example, that V2 ended up being, say 3 volts and V1 ended up being, say, 5 volts, then we know that there must have been a total of 8 volts here. 3 volts dropped here over R2. But since this is at ground, this node here must be at 3 volts. If this node is at 3 volts and we know that 5 volts dropped over this resistor, then this node must be at 8 volts. And it has to be because it's the same as this node here, which always has to be at 8 volts relative to the ground here. So, so anyway, keep that in mind. If this voltage here is not ground, then you have to adjust these things so that your calculation is correct. And just be careful. All right, but very simply, it's just a ratio. It's the resistor that you're looking for the voltage drop over the total resistance times the voltage, and it's the other resistor over the total resistance times the voltage, and that's it. That's all a voltage divider is. Super simple. Now, one reason that you might want a voltage divider, let's get rid of this, is we may want to, so let's say, all right, so let's jump ahead of ourselves a little bit here, all right? Let's jump ahead of ourselves a little bit. Let's say that we have some signal here, all right? Let's say that we have some signal here. And and let's say that this is kind of a digital signal, all right? So let's say that this is a digital signal. In fact, let's do this. Let's kind of draw this sort of how this would kind of be. So say we have this digital signal here, all right? And let's kind of do a fun example, all right? And let's say that our digital signal is going to go up to 5 volts, and here's 0 volts right here, and 1, 2, 3, 4, 5, 6 onward. Let's say that this is time here, all right, the time axis T. All right, and then let's say that our digital signal is looking something like, and we don't care what the scale of it is, how fast it's going, but we're just doing this as an example. And let's say it's 0, then it goes up to 5 volts, and then it goes back down, then it goes back up, then it goes back down, then it goes back up, and so on. All right, it just does this. All right, and let's draw that a little bit better. Oops, well, let's do it again. All right, let's go up. These are totally flat. All right, even though I'm not drawing them totally flat. These graphics tablets are surprisingly difficult because you're looking at the screen and drawing on something else. You got to get really used to it. Okay. All right, so we have this scenario right here. All right, and then this signal, right, whatever this is, let's just call this, we'll call this signal, S1 for signal 1. And here it is here, it's S1. So here comes S1, and it's, coming down. And S1 is relative to ground. Okay, so it's relative to ground. We have this S1 signal, which represents, we don't know, we don't care. And now the problem is we need to scale this down because maybe the thing that we want to talk to is a 3.3 volt system. So this is a 5 volt system here, and we want to talk to a 3.3 volt system over here. All right, 3.3 volt system over here. And let's just draw that again, 3.3 volt system over here. All right. So we want to scale this voltage down. Now there's lots of ways to do this. There are things called level translators and all kinds of things, but we can do it with a simple voltage divider. All right, so here's what we're going to do. So when the voltage is 0, we want to get a 0 out. And when the voltage is 5, we want to get a 3.3 volt out. All right. All right, so let's see if we can do this with a voltage divider. All right, so we're going to take our circuit here, and we're going to put a resistor here, and we're going to put another resistor here. All right, and we're going to call this resistor R1, and we're going to call this resistor R2. All right, and again, we can label things here. We'll call this V1. We can call this V2. But the thing that we're really interested in is this node right here. All right, and I'm going to call this, we're going to make this another signal, and this output right here, and we're going to call this, how about we're going to call this is S1, so we're going to call this S2. And matter of fact, let's draw that in a different color so we can kind of see it better. And how about orange? Okay, so this is S2. So S1 is from a 5 volt system, S2 is a 3.3 volt system, and we want to make sure that if we send the signal in here, we get out 3.3 volt pulses and not 5 volt pulses, okay? So that is the statement of the problem. Now, one thing is we're going to connect this, say, digital I/O, right? So the term here is, you might call this a general purpose I/O or a digital I/O, GPIO. You might hear that term when you start doing microcontroller stuff, general purpose I/O. All right. And one thing is these GPIOs can only source and sink so much current. All right. So typically their current limits are on the order of about 10 to 25 milliamps. All right. So whatever we do over here, we're putting a circuit to ground here, and we want to be careful that we don't draw too much current, right? In one case. In another case, we want to make sure that we can pull enough current from it so that it can be useful to drive something else maybe. But let's say we're going to make one kind of concession. We're going to say whatever S2 connects to has a really high resistance. So it's a lot of current is not going to go in this direction. So in other words, this IS2 is going to be very, very, very small. All right. So really all we care about is generating the proper voltage, and we don't care about how much current is going to go this direction because we know it's going to be very small. But maybe we want to get like 1 milliamp or 2 milliamps, something like that. So what we want to do is we want to set up enough current in this circuit so we can pull off some of this current without distorting this 3.3 volt voltage divider. So this is a very common problem that voltage dividers are used in, and if you want to do a simple kind of hack. If you want to do this correctly, there's other ways to do it with transistors or FETs and all that, but we're going to just do this. So again, we're not going to mull over this too hard. We're just going to say, all right, let's set this up so that we have a total of 10 milliamperes flowing through this, all right? So when this thing turns on, it's going to burn 10 milliamps. All right, so that's number one. So we're going to set it up for 10 milliamperes. All right. If we're going to set it up for 10 milliamperes, that's what's going to flow here. So our first problem is we need to find what the total resistance is to get 10 milliamperes out of the circuit. All right. So we have 5 volts here. So let's write down our equations here. Let's put our we'll put our Ohm's law up here for reference. And again, it's always nice just to have it. Okay. We want to compute R. So R total equals V over I. V over I. In this case, what's the voltage? 5 volts. What's our I? 10 milliamperes. This is going to tell us our R total, and R total is basically these two guys right here. And this is how you do circuit design. You kind of first figure out the big part of the problem, and then you kind of break it into pieces and drill down to what you want. So 5 volts divided by 10 milliamperes equals 500 ohms. Okay. Equals 500 ohms. So we know that our total is 500 ohms in total, all right, if we want to flow this 10 milliamperes right here, okay? All right, and let's see here. Okay, so now we can basically use a number of different techniques, but let's use the voltage divider equations to kind of see if we can solve for this, all right? So let's get a different color here. Let's get this color. All right, and what did our voltage divider equations say? So they said that V1 equals R1 times the total voltage, V, over R1 plus R2, and be careful, that's in parentheses. And it said that V2 equals R2 times V, and that's always V source of the source, over R1 plus R2. Okay. So, and these are our voltage divider equations. So voltage divider equations. All right. Okay. So we know that when the system is high, we're going to have 5 volts right here. All right. We're going to have we're going to have 5 volts up here at this node right here. Right. We're going to have 5 volts right there. And so that's our V. All right. And then we know that at S2 we want to have 3.3 volts. Okay. So now we more or less have everything we need to know. So this has got to be 3.3 volts when this is 5 volts. We also know that the total resistance has to be 500 ohms. So let's see what we know here. So what do we know? Do we know what V2 is? Yes. V2 is 3.3 volts because we want it to be 3.3 volts relative to ground. So that's easy. Do we know what V1 is? Yes. V1 must be 5 volts minus 3.3 volts, right? Or 1.7 volts, right? So we can say V1 equals 1.7 volts. All right, okay. So now we have everything we need to know. Let's take a look at one of these equations. Can we use one of these to solve? So let's use the one that actually has R2 in it, because that's what we first want to find out, right? Let's figure out what R2 is. So this one right here, V2 equals R2 times V over the sum of R1 plus R2. So let's start plugging things back in. Do we know what V2 is? Yes, it's 3.3. 3.3 volts. Do we know what R2 is? No, that's what we're trying to find. Okay. Do we know what V is? Yes, we do. V is the total V of the voltage divider, which is 5 volts. All right. Do we know what R1 plus R2 is? We don't know what R1 is. We don't know what R2 is, but we know their sum needs to be 500 ohms. All right, and I think you can see where we're going with all this. Okay, so 3.3 equals R2 times 5 volts divided by 500. All right, so all I'm going to do is I'm going to do this algebra and then figure out what R2 is. All right, so we're going to take 5 divided by 500. All right, and then I'm going to take that number and then I'm going to invert that. And I'm going to multiply that times 3.3, and that's 330 ohms. All right, so equals 330 ohms. So R2 is 330 ohms. 330 ohms. We could do the same calculation and use this equation here, but we don't need to because we know the total is 500. So we know that R total equals R1 plus R2, right? Which we know that 500 equals R1, which we're trying to find, plus R2, which is now 330 ohms. Therefore, R1 must be 500 minus 330, right? 500 minus 330. And again, just play dumb when you're doing arithmetic. You'll make mistakes. Let the calculator do it in your head, and then let the calculator do it also. And that way, you'll usually, between the two of you, you'll be right. 170 ohms. So where are we here? We'll write it right here, 170 ohms. So that's it. So if you build this circuit and you put a 5-volt signal oscillating like this through the circuit, and you put a 170 up top and you put a 330 resistor in the bottom, you're going to get pulses. Instead of 5-volt pulses, you're going to get 3.3 volt pulses. So you've in essence did a level translation from a 5-volt system to a 3.3. So this might be 5-volt TTL to low power TTL, 3.3 volts. All right. So I think now, and then one little, let's talk about one little thing here, and I think we're ready to go on the bench and play around here. We've done enough theory. One thing I wanted to talk about was we said that the current going through this node here, going out S2, was going to be very, very small. In other words, and I want to use some terminology here. In other words, whatever we connect here, this resistance to ground, and that's a horrible ground. This resistance, I'm going to call it RL for R load, okay, or R load. The whole idea here is we've created a voltage divider, but if we put another resistor in parallel with R2, we're going to change what R2 is. Now, R2 is 330 ohms. So if we put another resistor that's 10 times larger than R2, then the effect this RL will have on R2 will be very, very small. So in other words, it's not going to change its resistance too much. So we're not going to load it too much. So this voltage isn't going to change too much. All right, let's do an example. So let's just use common sense here. So if I, for example, use a 10 times larger resistor, so say that our load resistor was 3.3 k ohms. So what's the parallel combination of 330 and 3.3 k? Let's do it. So 330 parallel with 3.3 k. So remember, it's the product over the sum. So the product, 330 times 3.3 k over the sum, 330 plus 3.3 k. Let's get our calculator and let's do this. Now watch this. 330 times 3.3 k divided by, make sure you use your parentheses, 330 plus 3.3 k equals 300 ohms. So the result of adding this impedance, this load resistor, over here of 3.3 k modifies this resistor and decreases it to 300 ohms as the equivalent resistance. Therefore, the voltage drop over it's going to be a little bit less than 3.3 volts. It's going to change. It's going to be 3.2, 3.1, right? It's going to decrease because the voltage divider action is going to change because the voltage divider, instead of seeing 330, is now going to see 300. But this is tolerable. It only changed it by 10%. So that's okay. 10% we're fine. However, what if we made this instead of 3.3K, what if we made it 100 ohms? Okay? What if we made it 100 ohms? Well, let's do that calculation. So now we have 330 in parallel with 100 equals 330 times 100 divided by 330 plus 100. Let's do the math. So 330 times 100 equals, divided by quantity, 330 plus 100. 76 ohms. So that equals 76 ohms, all right, 76 ohms. So, hopefully you can see this is not getting covered. 76 ohms. The point is, when we add the 3.3K, we get a resulting impedance or total R2 with a load of 300. But if we change the load to 100 ohms, this drops down to 76 ohms. In other words, we don't have 330 anymore, we have 76. This voltage is going to radically drop, and we're not going to have what we want anymore. So the point is that when you do these voltage dividers, whatever the load is you're going to put on it, make sure that the load is at least an order of magnitude larger so that the voltage divider maintains its voltage divider action or its stiffness. And it's called stiffness, like a spring, because if you add something to it, it doesn't change it that much. Ideally, you want it to change 0. That would mean you'd have to have an infinite impedance here, right? So we can't really do that. But anyway, we set the current up, and these resistors are pretty low so that this thing, does what it does. Now, if we needed this to be stiffer, we could increase the current to 100 milliamps and turn the total resistance to 50 ohms. Then we could change these two resistors to 17 and 33 ohms if we wanted to. Then it would be 10 times stiffer. Then if we added smaller resistors, it would still maintain the voltage divider action, but we're burning 100 milliamps every time the GPIO turns on, right? So we don't really want that. Okay, so now that we've kind of done this, we've talked about voltage dividers, we've done the math, let's actually do an experiment right now. Let's get onto the bench and let's build a little voltage divider and let's put a voltage to it and let's do something very similar to this right here, and we can see if we can find a 330 and something around a 170, and we'll do a 5 to 3.3 divider, right? So meet me over on the bench and let's go do that. Okay, so we're over here at the bench, and what our goal is to kind of mimic what we did over there. We're going to have a 5-volt supply. We're going to have a voltage divider with 2 resistors, and we're going to try and turn 5 volts into 3.3 volts with magic. All right, so let's go ahead. And so I've looked around, and I wasn't able to find 170 ohms, but I think I found 180 ohm. So first, here is our 330 ohm. So let's take a look at that under the zoom camera. All right, let me zoom in there. And that's orange, orange, brown. And let's, let's sanity check ourselves here. All right, and all right, so that's going to work. And let me get the meter there so you can see it. All right, and there we go. We've got on resistance and 0.3 K. And let's just, this particular meter, yeah, I think it has a maximum range of 200 ohms, so you have to put it to the K range. Yeah, so this kind of sucks. You have to put it to the K range. I don't really like that. Let's use a different meter. And like I said, a lot of times these meters have ranges, and if something's in between the range, you got to go to the next range, and you may not like it. So again, that's another reason why I have many meters. All right, so now it's in auto range mode. So let's go here and let's measure this. All right, and it's auto ranging, and there we go. 327, 330 ohms is supposed to be what it is. So, okay, all right, so we got that, and then now we've got our other resistor right here, and this is 180 ohms, supposedly. Let's take a look at it. And 180, this would be brown, like gray brown, I believe. All right, and let's measure that. Let's measure that over here. Okay. And get our meter here again. Okay. And we're looking for 180 ohms. Perfect. 180, 178. Okay. So the circuit that we're trying to make here is we're going to come in from the power supply. All right. And the power supply is going to be up top here. And that's going to be where we're going to bring in our 5 volts. Then we want to have our smaller resistor, our like our 180. All right. And we're going to put that right there. And then we want to have our larger resistor, which is like our 330. Okay, and then we're going to take that and we're going to go to ground. Okay, so, all right, so that's as simple as it is. All right, so we're going to get our meter here. And so we're going to apply 5 volts to here. And then the question is, will we have 3.3 volts over our resistor? So let's give it a try. So we'll put the meter into voltage mode. All right, I'm going to turn the power supply on. The power supply is on. And all right, so first let's verify that we have 5 volts coming into the system. We have 5 volts, good. And we should have 3.3 volts or roughly 3.3 here. And we sure do, 3.25 volts. Okay, now let's go ahead and let's load this. So let's load it with, say, let's find a 10K resistor. Let me find a 10K resistor. Here's one right here. All right, so say we want to take this signal and we want to send it someplace in our circuit. And that impedance of that, wherever that's ending up, is say 10K. All right. So now we're going to take that signal, and let's use this right here. All right. So now remember, this is the node. This is the output right here. Be careful. All right. So there's the output right there. All right. So now we still want to maintain this 3.3 volts here. So let's see what it actually is. So is it 3.3 volts? We know that it's not going to be. We know that it's going to be slightly less because we've loaded it, but we loaded it with a very large resistor, and the resistor is 30 times larger than the R2 resistor of 330. So we're loading it basically by 3%. So we should see very, very little deviance from the 3.25 volts, but let's check it out. So here we go. We're going to go from ground here, and we're going to go right here. It's the same node. And sure enough, it's 3.21 instead of 3.25. So the 10K load is just fine, no problem. So 10K load is just fine. Now let's go to a 1K load. 1K load. Here's a 1K load, brown, black, red. On the zoom camera there, brown, black, red. There we go. And we'll just move our load and put our new load in here. All right. So we've got that. Let's put our meter back so we can see what's going on here. Now we expect to have much, much greater deviance. The reason why is this load is only 3 times bigger than the R2 resistor in our voltage divider, so it's going to destabilize this quite a bit. So let's see what it does. So here we go, and now we've got 2.9 volts. So almost 3 volts. Now, if this is a 3.3 volt system, we'd still be fine. It would still register as a digital high, so we would be okay. All right, now let's go and really load it. And let's go ahead and put a 100 ohm resistor here, 100 ohms. Now we're done.